So my talk will be devoted to antiferromagnetic square lattices. If we will try to compose or to draw a square, we will see that in fact such lattice is non-frustrated, because if we try to put arrows in each corner of this square, there is no frustration, no competition between possible antiferromagnetic exchange interactions shown by blue. My arrow is not seen in the view graph. Okay, so there is no competition between exchange interactions between these arrows. Possible quantum ground state for this model is L1, which means that all arrows are directed opposite to each other. How we can invent frustration in such lattice? For this, we can invent additional exchange interaction via diagonal. It is shown on the right side of this slide, and you can see that now blue lines will compete with the green ones. If we try to put the arrows in accordance with blue ones, the left lower arrow up will not be in good condition with the upper right arrow. In this case, if we introduce these diagonal exchange interactions, there can be, in fact, competition between nail and stripy states. And of course, there are some special cases for special ratios of diagonal to main exchange interactions equal to 1/2, when the system doesn't know what state it wants to realize, in fact, nail or stripy state. And there were many efforts to find compounds from this area. Of course, if we change the sign of magnetic exchange interactions along runs of this square, it can be a ferromagnetic state, besides that which I mentioned above. And there were found many compounds from this phase diagram of square lattices, which were based on spin half. And in this case, the magnetic ions were vanadium 4+, and here you may see the nice diagram which was prepared by Sasha Zirlin and Helge Rosner, and it is very informative, of course. What we will have with square lattice antiferromagnetic layer in case of spin 1. In this case, the situation will be closely the same. We have the competition between the rank exchange interaction shown by blue line and diagonal exchange interaction shown by green line. And of course, it can be, again, the competition between nail and stripy states, as in the case of spin half lattice. And some special point for this lattice is related when we make extremely low rank exchange interaction, we can transform this square lattice into in fact, in one-dimensional spin-1 chains, which are in fact gapped, and the situations will be, of course, with the quantum ground state really different. Why? We mention, first of all, spin half and spin 1, discussing low-dimensional objects. In fact, in such low spins, we mention them because only for such low spins there can be realized quantum effects. So in our nitrates, when we found this very complex compound, you may see its formula written in the slide. So chemical name will be nitrazonium nickel nitrate. We found that in fact its crystal structure contains nickel ions, which are shown here in octahedra, the blue one and the red one, and they are in 2 types distance. You may see the shorter one, 5-point-something angstrom, and the longer one. So in fact, it is a 2-dimensional layer, and these layers are separated a little bit more distantly from each other, and this is in fact can be seen, or we can imagine it to be a realization of square lattice for the spin 1. So the question was if we could compare it with the behavior of spin half. Of course, the usual spin half cation is kappa 2 plus, and it could be fine if we could compare it with kappa counterpart, but unfortunately, it is not the same structure. It was studied earlier, and you may see that in this structure, kappa ions form one-dimensional chains. So, well, in this case, we could not use this counterpart to compare the behavior of such lattices, but fortunately, we have found that there is isostructural compound to the nickel one. It was with cobalt. So both compounds demonstrate same structures, and you may see that all distances between magnetic ions look very similar. And in fact, the octahedral coordination in these compounds is also the same. And of course, cobalt 2 plus, it is 3d7 ion with spin 3/2. But nowadays, in last theoretical predictions, people theorists suggest to consider it as J-effective half with extremely large or large anisotropy, so it should be something like Ising type. While nickel 2 plus, it is spin 1 cation, it is classical spin 1 cation, which from time to time can be both Heisenberg or Ising type. So we wondered what type of behavior we may find in these 2-dimensional layers. Let me first introduce what we have found for cobalt member, and here you may see that, well, at low temperature this compound orders antiferromagnetically, so no low dimensionality. We see the only thing we see is usual 3-dimensional order, and at about 13K. And of course, we tried to fit its temperature dependence of magnetic susceptibility. We found a large theta, relatively large theta, which allowed us to assume that there should be antiferromagnetic exchange interaction in the systems, but maybe they are almost the same in all three directions. What we have found in magnetization loops when we measured are the metamagnetic type of behavior. Here you may see that magnetization increases almost linear in low fields, and then it bumps. Well, this is typical behavior of metamagnet, and probably this is due to the strong Ising anisotropy, which is assumed for the cobalt 2 plus ion. Surprising was that when we studied nickel 2 plus ion, it is formally with spin 1, so larger spin, but in this case we found signatures of low-dimensional behavior, which you may see in temperature dependence of magnetic susceptibility, shown in the left panel, and here you may see that at relatively high temperatures of about 50K, there is a broad maximum. Broad maximum is, of course, usually produced by low-dimensional nets presented in the structure, and maybe it can be produced by either layers or chains, which we can find in the structure of this compound. We also found that there are strong antiferromagnetic exchange interactions due to antiferromagnetic theta found at high temperature, and found reasonable G factor, which is G equal to 2.27, typical for nickel 2 plus ion. What we have found in magnetization curve, it was the signature of spin flow-like behavior at 6 Tesla. Well, this signals us that we have deal with most probably Heisenberg type anisotropy of nickel 2 plus ion presented in these two-dimensional layers. We also tried to estimate exchange interaction parameters presented in the layer or in chains, whether depending on how we would consider them in the structure, and we found that it is something like 10 or 20 K. Reasonable, but the temperature of ordering is rather high, which is surprising. Trying to look inside to the quantum ground states of these compounds, we also measured specific heat, and it was tricky because these compounds are waterless, and you may see that, or you may assume that in air it is not stable. So it is a tricky game to measure its specific heat, and we provided some special technique of mounting the sample in nitrogen atmosphere. Both dependencies of these compounds show lambda type anomalies at same temperatures where we saw the kings of in magnetic susceptibility. So we also detect the formation of long-range ordered state in these compounds at same temperatures at about 13 and 24 K. And in order to estimate exchange interaction parameters, we had to fit the low temperatures parts of this specific heat. And estimated parameters for cobalt and nickel compounds differ. You may see that they differ 3 times. So for cobalt compound, it is 12 K, and for nickel compound, it is about 30 K. So this can be the reason for the different type of behavior which we find in our systems. Of course, we cannot estimate exchange interaction parameters more or less quantitatively. We do it, of course, qualitatively, because when we feed our thermodynamic data, we use formulas based on mean field theory. So we applied to theorists to calculate the energy spectrum parameters for our compounds. And for one of these compounds, it was possible. So the nickel-1 compound was possible to calculate, and here you may see that they found 2 extremely strong exchange interactions presented in the layer. They are both antiferromagnetic, and they are about 30 K. And here you may see that it is in good consideration or estimation of exchange interaction which we obtained from specific heat. Surprising for us was that they found the ferromagnetic exchange interaction in between the layers. It is extremely small. I would say that it is of about digit of mistake, which is or reliability of the DFT calculations. And they found reasonable anisotropy for the nickel compounds. So in fact, in this, from the first point of view, 3-dimensional objects, as I showed in the previous view graphs, it was composed of octahedra of nickel oxygen or cobalt oxygen 6 octahedra, which were connected by nitrate groups in 3 dimensions. We were able to find the 2-dimensional layers, and these 2-dimensional magnetic layers demonstrate their low-dimensional behavior at high temperatures, and unfortunately, they order at lower temperatures. producing three-dimensional antiferromagnetic order. And basing on the thermodynamic characterization of our compounds, we may conclude the following. I think I can not to read it. The following considerations. Thank you.
Thank you, Professor Belkova, for the interesting presentation and for being on time. And now we open the floor for questions. Any question? Okay. Yes. Mike first. Yeah.
I can speak loud.
Okay, so we can start, please.
Yeah. From your measurements, can you exclude the Jyloczynski-Maria interaction is present, so that you get canting?
For Jyloczynski-Maria, we should find some ferromagnetic component, but in fact we do not find it, for example, in magnetization curves. So we cannot exclude it, of course, but we did not find any signatures or.
Well, was there neutron scattering measurements?
Unfortunately, not.
Okay. Thank you.
So, excuse me.
So very nice talk. So did you identify the magnetic moments of the nickel and the cobalt system? You have measured values of the moments?
You mean saturation moments?
Yes.
We were not able to achieve saturation, it seems to me. No, of course, we were too far because exchange interactions are more than 10K, and we have, okay, if we are lucky, we have 30 Tesla. But we were not able to achieve saturation moment even in 30 Tesla.
But from maybe from susceptibility?
From the susceptibility, the effective moments are in good, reasonable. So the G factor is actually calculated from the effective moments, and so it is more or less true value of
from
G
two
factor.
plus ions.
From 2 plus ions, yes.
Okay. And the calculations were done with how were the calculations done?
They were done in group of Tanusri Shahadas Gupta.
I see. Okay.
So I think.
I know. Okay.
Yeah.
Thank you.
Here. One of you.
I have perhaps a too simple question, but there is no angular dependence in this response, magnetic response?
We measured on the powders, so we
okay,
cannot.
okay.
It could be interesting to make the angular dependence, but in this case, unfortunately, chemists. By the way, one of chemists who produced these compounds is in this hall, and it was great effort from them to produce these waterless nitrate compounds, and it is a special technique. So unfortunately, in this case, they were not able to produce single crystals, and so.
Okay, thanks for this talk. You showed that the low-temperature magnon excitations are well described in spin wave models with a specific heat data. Doesn't this exclude low-dimensional models?
Of course, at low temperatures, it is in both cases antiferromagnetically ordered state.
So you find this normal. So which exponents do you find?
The estimation of the exchange integrals are shown here.
And this is the T by the 3 model.
T cube. It is coefficient before the T cube, which can be transformed into the exchange integral in the mean field theory.
Can you go up there? Yes. Go up first.
Thank you, Professor. I have two questions. So the first one is that the frustration factor you showed from the Curie-Weiss temperature and the order temperature is not that high. And basically I would expect only like one exchange interaction. But you showed
Sorry, what,
that...
again, what? So the rate, the frustration ratio is low, and the question is?
So J2, do you have any signature for J2 in the experimental data? I see it only in the calculation.
No, in the experiment we see no indication for J2, that it is different from J1. But in crystal structure we find there are two distances between the magnetic ions, so we may assume that intra-layer exchange interactions may be different.
But if we calculate the sum of J1 and J2, it should give us a value which can be calculated from Curie-wise temperature as well as a sum of the exchange interaction.
Yes.
And in this case, is it the same value?
I understood. So you ask whether this theta equals to the sum of these exchange interactions. Yes.
So we can consider that J2 is existent, but we don't see any signature in the experimental condition.
But in fact, crystal structure, the pathways are almost, they are not the same, but they are similar. So we may assume that there should be J2.
Okay, we'll take the last question, please.
Okay. Can you go back, please, for the slide of specific heat?
Yes.
Low temperature fitting?
Yeah.
Okay, if I understand correctly, this fit, to clarify, this antiferromagnetic system is following a spin wave behavior. Yes?
The last.
Okay, yeah, last point. This fit just to see how our system, this system is following the spin wave theory.
Mm-hmm.
Yeah, this is the message from this fitting, or how we get the G exchange interaction here? Because
if we fit the low temperature part with T cubic term,
exactly.
there is some coefficient before this T cube.
Yes.
So this coefficient is correlated with the J. There is a equation. I did not introduce it in the slide,
okay.
but in the mean field theory there is an equation, and it's an old one. So we make a very rough estimation of J from the coefficient, from this coefficient of
Okay,
the cube.
thanks a lot. Maybe I come later to have
Yes,
some
great.
more elaboration about
Yes,
this, because
yes,
this is
no
new.
problem.
Thank you very much.
Last question.
Like maybe later.
Sorry, we are out of time. You can ask her later. Thank you, Professor Vilkova, for the presentations. And now we are going to our next keynote speakers, Professor Krillner, the director of the Institute of Physics at Goethe University Frankfurt. He held several positions actually in various periods of time. As a professor, Krillner was the director of the Institute of Physics at Goethe University Frankfurt, and also member of the extended faculty committee at the member of the faculty, which was the first thing that Professor Krillner held. He worked as a professor at experimental physics at Goethe University Frankfurt, and worked as research at Max Planck Institute CBFS, and was the leader of interdisciplinary research project. Please welcome Professor Krillner. The floor is yours.
So thank you very much for this introduction, and thank you very much for inviting me here to Jordan. It's my first time in Jordan, and I really enjoy it. So just need to skip that. This one's okay.
Which one?
Okay, so welcome again. In my talk, I will present you some details about crystal growth, because my my main research topic is crystal growth on intermetallic systems. I will introduce to you why that is important, and then I give you 3 selected examples where I show how crystal growth can improve our understanding of modern solid-state physics. And to start, in general, in modern solid-state physics, we nowadays look mainly for collective phenomena in emergent materials. What does it mean? In general, one can also say this in the words of Aristoteles: the whole is greater than the sum of its parts. And of course, this is used in many in many cases, but in case of solid-state physics, this means the parts are our chemical elements. So we start usually with the elements from periodic table, and the whole is the emergent phenomena which we observe at low temperature, high magnetic field. And prime examples, you already heard about that yesterday, is superconductivity, and I think later on today we also have focused talks on magnetic ground states. So these are examples where exactly this happens, that the whole is greater than the sum of its parts. And as it was mentioned yesterday, superconductivity is a prime example where material science plays a very important role in solid-state physics. We heard yesterday that probably not many materials were predicted by theory, but usually they were discovered by experimentalists, by material scientists, which were looking for correlated ground states. The history of superconductivity started more than 100 years ago by discovery by Kelvin Equation. This was not so much a materials discovery, because this was more an effort to get these low temperatures to realize this ground state. But later on, the first unconventional superconductor was discovered in 1978, roughly, the year where I was born, by my later supervisor for the PhD thesis, Frank Steglich. He discovered serum copper 2 silicon 2. It was superconducting at very low temperature, but it was very special because in those days it was the first superconductor which at the same time the same electrons also show magnetic order, and therefore was coined the name unconventional superconductivity in those early days. Very quickly later on, high-temperature superconductors were discovered in the cuprates by Bertnolds and Müller. We heard about that yesterday. Also, this was a clear materials discovery, not predicted, and also only after some time really believed by the community. Then, this was the time where I already was in science, was the discovery of iron-based superconductivity in Japan by Hideyoshi Ozono. And also this is a family of unconventional superconductor. A bit off, but above the other superconducting temperatures is the hydrogen sulfur. And I think in the next talk we will hear about metallic hydrogen and these type of materials under high pressure. Now I like to motivate why do we need single crystals. So in the previous talk you heard about measurements on powder. This is always a good starting point to look for new phenomena. But if you really want to go into detail of the physics behind of the anisotropy, etc., and the real properties of the materials, you need single crystals. And you need single crystals in very pure form, and sometimes also in quite large size. So you need, for us as a crystal grower, the largest collaboration partners with the largest demand on crystal size are the neutron scattering people. Also there, because those becomes better, the resolution and the flux at the neutron sources gets better, but still there, often they need cubic centimeter sized crystals. We need very pure crystals when you like to determine the band structure via quantum oscillations, and you need many crystals if you are interested in the surface of your crystal, because usually in ARPS measurements or STM measurements, you cleave your crystal, meaning that you destroy your crystal during your measurement, and it holds maybe for 2-3 hours, and then you need a next one. So let me start with the first example on a ferromagnetic quantum critical point in a new material. For this, I need to introduce the concept of quantum phase transition. So this workshop also has the name quantum in it. We heard it also yesterday several times. But I think the quantum phase transition is a prime example to illustrate what happens if quantum effects play the dominant role in your material. You just make a Gedanken experiment and look at this phase diagram. You have temperature and you have an external parameter. On the x-axis can be pressure, magnetic field. And then you just have a normal magnetic transition. This is thermally driven, as we have seen before. You can nicely describe it. And then you somehow drive this transition down to lower temperatures by this external parameter. And then at a certain point, you reach temperature range where the quantum fluctuations play the dominant role. And then you have a transition, if you come there from the left to the right, from magnetically ordered state to magnetically disordered state, where quantum fluctuations play the dominant role. And this transition is called quantum phase transition, and the point where this happens is the so-called quantum critical point. And as I said, this is a Gedankenexperiment, and you can say why I should care about this. You should care because above this quantum critical point, there's a lot of entropy around, and usually the systems try to find a new collective ground state. And the most prominent one is superconductivity. So in many of those unconventional superconductors I introduced before, you have such a quantum critical point underneath. Therefore, it's really important to understand the physics behind these quantum critical points. You can also have spin liquid ground states, non-fermi behavior, etc. This general phase diagram is established for antiferromagnetic systems, and it was not established for ferromagnetic systems. And there were several possibilities what can happen if you have a normal ferromagnet and bring it down to lowest temperatures. But usually, nature tries to avoid something like a quantum critical point and makes different things. You see it here. You have these famous rings in manganese silicide. You can have smearing out of the ferromagnetic transition as function of pressure towards glassy behavior. You can have change to antiferromagnetic behavior. But what's not observed is this clear transition towards low temperature, towards a quantum critical point. And the first example where this was observed was ytterbium nickel 4 phosphorus 2. And I'd like to shortly introduce that. If you are more interested, I will not go now into much detail on that. If you're interested in that, we can discuss later during the coffee break. What you see here is now a susceptibility as a function of temperature over 4 orders of magnitude. So you start at room temperature, you have a small anisotropy for the 2 directions, so you need a single crystal to measure that. And then you see at around 150 millikelvin, already well below 1 Kelvin, you get ferromagnetic order. So this is already a very low-lying ferromagnetic transition, which was promising. It's a quasi-one-dimensional crystal structure, and we get interested in this compound and grow crystals. But you have many problems to do this, because phosphorus and ytterbium have very high vapor pressures. This means if you just would heat them up, they just would evaporate. And you never would got them into a melt and to grow crystals from this melt. And furthermore, if you get them somehow in the melt, this melt is very aggressive, so you can't use any crucible. So you need to do something else. So we check the phase diagrams. This is usually what you do. Phase diagrams in the sense of composition phase diagrams. You find the melting points, and then you think about which type of technique you will use. And what we used is the so-called Czochralski crystal growth. You maybe notice from silicon crystal growth, you have these big crystals which are cut into wafers, and these are then inside your mobiles. We used a similar technique, but with a smaller scale, so this is 1 centimeter size there, and you heat up your material in an overpressure of 20 bar, and then this melt, which you see here, starts to levitate because it's inductively heated. So you don't have contact with any crucible, so it starts to levitate, and from this levitating melt, you pull out your crystal, and in this way you get a very clean, large single crystals. And this you can then cut in any direction you like to have, and then you are in the place also to make neutral measurements on these cubic centimeter sized crystals. And furthermore, if you make your own materials, you can also manipulate the materials. And in this way, we further wanted to suppress this ferromagnetic transition. And this we realized by putting arsenic on the phosphorus side. Because this makes the lattice larger, this acts as negative pressure. And with this, we can further suppress the magnetic transition. And our record temperature, this is the lowest ferromagnetic transition ever observed, was 28 millikelvin, so 0.03 Kelvin. And we made detailed thermodynamic measurements in Dresden at the Max Planck Institute and could confirm that indeed we have here the first ferromagnetic quantum critical point in this material. And we still study this material because it's not clear how this non-ferroliquid region, what I mentioned before, around this quantum critical point behave. This is now what we focus on at the moment. As a second example, I will come to a different crystal structure, and it's a very famous crystal structure. It's the so-called thorium-chrome-2 silicon-2 structure type, and some people now name it the perovskite of intermetallics. I think this term was coined by Bob Carver some time ago, and you see here all these members which sometimes dominate really physics and strongly correlated community. You already have seen cerium copper-2 silicon-2, the first unconventional superconductor. It's the famous hidden order compound, uranium-ruthenium-2 silicon-2. It's the mother compound of iron-based superconductors, strontium iron-2, arsenic-2, and it's also ytterbium-2 silicon-2, which I will focus on now. The crystal structure consists of 3 elements, and you see here the periodic table, and what you see, the green elements, they all can fit on the first side. The blue elements, transition metal, can fit on the second side, and the X are the yellow ones, they can put on the third side. And if you made now a combination of all these possibilities, you already realize that you can have a lot of materials in this crystal glass. And I think up to now there are 800 or up to 1,000 different materials crystallizing in this crystal structure. Ytterbium-rhodium-2 silicon-2 is also a quantum critical material, and it's a prototypical one for antiferromagnetic quantum critical point. Before we had discussed ferromagnetic critical point, now the ytterbium-rhodium-2 silicon-2 is a prime example for antiferromagnetic critical point. You see this here in this famous phase diagram, temperature as a function of magnetic field. The blue phase is the magnetic phase, the orange phase is the non-ferroliquid phase, and then you see here this very nice quantum critical point at a certain critical field. And also there, we start to grow crystals, and if you want to study quantum criticality, you really need very clean crystals. Yeah, because all the scattering inside your crystals you want to avoid, or most of the scattering that you really can study the pure non-ferroliquid behavior. And we have the same problem as mentioned before. Ytterbium has a very low boiling point, 1,200 degrees C. The rhodium has a very high melting point, 2,000 degrees C. So you need something to get them melt together. And in this case, we need indium as a flux. So it's a separate element which has a low boiling point, low melting point. We put all together in this flux and then grow crystals in closed crucibles at around 1,500 degrees C. We do this in a Bridgman furnace, something like this. So you put all your elements in the crucible, then you move up the furnace, you generate a temperature gradient in your crucible, and then the crystals start inside the indium flux inside this crucible. And with this, you reach not centimeter-sized crystals, but millimeter-sized crystals. Very nice, shiny crystals, because it's a two-dimensional crystal structure, and with very low residual resistivity of order 0.5 micron centimeter, which is important to study this quantum critical behavior. And you see what role of quality can have on this specific heat data as function of temperature. So this is the magnetic transition at around 70 millikelvin. I mentioned it's a quantum critical material, and the black curve was an older generation with a residual resistivity ratio of 70, and if you increase quality, you dramatically sharpen the transition, and then you can really study the fluctuations around these transitions in detail. I, as a crystal grower, also really like this image, because often we just characterize our crystals with X-rays, then we work in reciprocal space, but I also like to see things in real space, right? And this is an STM image from a perfectly greaved crystals, so atomic resolutions. You really see here the rhodium atoms one by one on a large area, so we really see that these are very clear materials. And with this, you can also make spectroscopy to study the excitations in this material. More recently, it was discovered that also this compound is a superconductor, but at very low temperature, at 2 millikelvin, so 0.002 Kelvin. At very low temperatures, not many places in the world where you can measure this. It also takes quite a long time, but it's now clearly accepted that below the antiferromagnetic transition, you have a superconducting transition. And this somehow shows that this concept of quantum criticality connected to superconductivity is a very general theme. And this was the first ytterbium compound at such a quantum critical point where we have observed this superconductivity. But it turned out, because the temperatures are so low, the nuclear moment of the ytterbium plays an important role. Usually we only talk about electronic moments, but here really the nuclear moment of the nucleus ytterbium plays an important role. And therefore, we as a crystal grower, we could help to understand this by making crystals with isotope pure ytterbium. So you can buy this from Russia as oxide. 1 gram costs about 20,000 euro, and then you have to reduce it to a metal, and then you need really precise procedures that you don't lose your material. And we were able to make 3 different isotopes, so we could really switch on and off the nuclear spin. So we have 3 ytterbium nucleus which with different nuclear spins. We were able to grow the crystals. The low temperature properties look similar like the pure one, and now they were studied at very low temperature, how this impacts the superconductivity. Okay, I have 10 more minutes?
We have
5?
5 minutes.
Okay.
5 minutes for questions.
Okay. Then I switch to other compounds in this class. I mentioned before there are many different compounds crystallizing with this method. And now we have established a crystal growth method, and we use that to grow also other raw earths with this crystal structure. And it turned out that for all these different raw earths, you can grow with the similar method these type of crystals. And now the nice thing is that every raw earth behaves a little different concerning magnetism. Yeah? For example, the gadolinium, which is in the middle of the 4F shell, has the strongest magnetic moment. The shell is half filled, so you have 7 4F moments pointing all along the same direction, and you have a very strong local moment. And we use now that these crystals are very easily cleaved for ARPS measurement. And then we have the following effect, which is going more towards application of spintronics at the surface of these type of materials. What is happening is the following. Here you see the band structure measured by ARPS. And what you see is a surface state, which, if you are above the magnetic transition, just is a normal surface state. But if you go below, here at 20 Kelvin, this surface state splits and gets spin polarized, because you have a very strong local magnetic field of the gadolinium atoms. So you just cleave your crystal, and then you have a very spin polarized surface which you can tune by temperature. So this is a very nice effect reported some time ago, and we have studied this for several crystals of these materials, and every raw earth behaves a little different, and we studied this in much detail. And a second type of measurements then were done in collaboration with an ultra-fast spectroscopy group in Berlin. They now wanted to study the dynamics of this magnetic order. And they really take the advantage that we have the whole series of rare earth with very different magnetic interactions, but the crystal structure and the phonon interaction are all the same. This means also the relaxation procedure to the crystal lattice is all the same. And in this experiment, together with theory, Ericsson was involved. We could really study the ultrafast dynamics in these series and could see that we have a direct magnetic exchange between the 4Fs beside which is coupled to the RKKY interaction. And we made use of the materials we had at hand to systematically study it. In the last minute, I like to show one step further, because now we only have discussed materials with 4Fs. But of course, in this structure, you could also imagine that you have two different magnetic species, one 4F and one 3D. And this exactly is happening in the series with Cobalt. And this was also motivated by recent high throughput calculations by the Bernavik group, which proposed that cerium cobalt 2 phosphorus 2 is a so-called high-quality topological materials. So since 3-4 years, the community really is searching for magnetic topological materials. We can discuss later what that means. And their band structure calculations really play an important role, because they can predict if a material have properties like this. And they predict that this material is such a one. It was probably predicted in Nature 2 times. And we made a material, but we did not find that this is a topological insulator. It's a rather reasonable metal. And, but usually if you study a new material, you sometimes also find other interesting things. And also this was the case here. We made RPS measurements to search for the surface states, and we found surface states, but in a little different manner, because we had here a very rare scenario that in the bulk of the material we only have cobalt ions, but at the surface this cobalt magnetism, which order at above room temperature, polarizes the cerium atoms, and they order ferromagnetically only at the surface, and the bulk is non-magnetic. With this, I like to acknowledge the people. You see here a big list, and it should be even longer, because as a crystal grower, you usually have a lot of collaborations with different measurement groups in the world who then measure on your crystals. And I hope I could convince you that crystal growth is a nice tool to make new discoveries, to help understand phenomena in physics. And with this, I like to thank you for your attention.
Thank you very much, Professor Krilliner, for the provided presentation. And now we take questions. Please.
Loudly.
Yeah, it's very close to you.
Okay. Can you go back, please, for slide 12? I have just a brief question about the fitting in this. Okay. Yeah. Could you tell us a bit more about this fitting? Where is this exponent?
So maybe one has to here, I was of course very quick. You see here specific heat as function of temperature. Yeah. For a normal metal, you would expect a constant. Okay? And what you see here, that you have an increase, and this increase can be best described with a power law. And with this, you learn something about the fluctuations around this quantum critical point. And this is then better seen if you look at the Grün-Eisen ratio, which is the relation between heat capacity and thermal expansion. And also there you see power law behavior, which then you can use to describe the fluctuations around this quantum critical point.
Okay, so then we have Grün-Eisen ratio. What is the dominating energy scale here in this graph? What is driving?
So it's really the quantum fluctuations around this quantum critical point. I mentioned the order is 30 millikelvin, and then directly at this point above this ordering temperature, you have dominant quantum fluctuations from your 4F moments. It's only the 4F local moments which make the physics here. They fluctuate, and this can be described with this power law behavior. Okay, which is theoretically not yet understood why exactly this power law behavior is observed. Because from theory, a ferromagnetic quantum critical point is not to be expected.
Okay, thank you.
It's still unaware.
Any other question? It's fine. Yes.
Thank you, Professor, for this nice talk. I wanted to ask, in the beginning, the introduction, you said that in the quantum fluctuations and quantum critical point figure, the system, when have quantum critical fluctuations, usually goes to the superconducting state. this is the preferred state? Or are there any theories which explain that? Or how can we predict whether it will be like a spin liquid or superconductor? Can we?
That's a very good question. So, of course, this is all empirically driven, that you have many different material classes where you observe superconductivity in the vicinity of quantum critical point. But so far, we have no theory which really proves that this is a general case. So therefore, one cannot really say that at every quantum critical point you will observe superconductivity. But the other way around, maybe it's better to coin. If you search for unconventional superconductivity, good places to search are around quantum critical points.
And in this case, I have another point. So usually when we have the quantum critical fluctuations, should we, when we have it in oxides, usually it does not go to superconductivity below. It goes to something else. But is it related to the orbital contribution or the type of exchange possible in the antiferromagnetic?
I guess you are speaking more in direction of quantum magnets where you have insulators, right? And of course you need, like in the cuprates, a transition towards the metallic state to enter superconductivity. And usually in these quantum magnets with copper 2+ ions, it's so stable, the Hubbard U, that you don't enter this metallic state. Yeah, therefore, in this type of materials, this not yet superconductivity found. If you find it, you will be the hero.
Thanks.
Thank you very much, Professor Krillner. And at this moment, we finished the first session for today, which is shifted from yesterday. And we are going to move directly to the first section for today, actually. And we'll call Professor Mohammed Adam to share the sessions. Please, Mohammed.
Thank you very much. Good morning. I am Dr. Mohammed Adam. I am Assistant Professor of Mathematics at Palestine Polytechnic University in Hebron, Palestine. And I am also a steering committee of the Arab-German Young Academy of Sciences and the Humanities, AGYA. I am very happy and honored to be here with you. It's my pleasure and honor to start introducing our distinguished speaker, Professor Isaac Silvera, who is a professor of physics at Harvard University. Professor Silvera received his PhD at the University of California, Berkeley, and then after a postdoctoral year in Grenoble in France, he worked at the North American Aviation Science Center in Southern California, where he studied superconductivity and solid molecular hydrogen. In 1971, he accepted a professorship in the physics department at the University of Amsterdam in the Netherlands. During his 11 years in Holland, he started research in producing metallic hydrogen and succeeded in producing a gas of atomic hydrogen. Spin polarized hydrogen, this was the first stable Bose gas that started the effort to produce Bose-Einstein condensation, now a major of physics. In 1982, he accepted a professorship at Harvard University, where he now teaches and leads a research group focused on low temperature and high pressure physics. He and his students and postdoctoral fellows have studied solid hydrogen to extreme pressures. Recently, cumulating a 45 years effort, they achieved the highest pressure ever on solid hydrogen, 4.9 million atmospheres, and transformed hydrogen into a metal. Solid metallic hydrogen was predicted 81 years ago by Wigner and Huntington, and has been the ultimate goal in high pressure research. Metallic hydrogen may be a room temperature superconductor, among other important properties. Professor Silvera has published almost 300 research papers, mostly on hydrogen. He is a fellow of the American Physical Society and the American Association for the Advancement of Science, and a foreign member of the Royal Dutch Academy of Sciences. He received a White House appointment from President Obama to the board of the Vietnam Education Foundation in 2011 and served as the chairman. Please join me to welcome Professor Silvera. The stage is yours.
Thank you very much. So I may need a little help here because I'm used to Apple computers, and this is a Windows machine.
I think this is yours.
This is mine here.
Okay. Yeah.
And how do I advance?
Here.
Yeah, okay. 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 Thank you very much for the invitation and the introduction. Okay. So let's see if I can get the cursor. How do I get the cursor here? Okay, I see it. Okay. So we've come a long ways here, almost halfway around the world from Boston, Harvard University's in Cambridge, which is adjacent to Boston, over here to Amman. I have a small group working on this right now. It's been changing over the recent years. We get support from the National Science Foundation and the Department of Energy. And I have an ongoing collaboration with a former postdoc, Ranga Diaz, who is at the University of Rochester. So I start out with the Rosetta Stone of pressure. A lot of people don't know the units. We use gigapascal, and 100 GPa, 100 gigapascal is 1 megabar. So that's something that you should remember because some of the figures are shown in GPa. There's a relationship of metallic hydrogen to this forum on sustainability. And as I mentioned the other day, we are involved in fundamental research, which is an understanding of the laws of nature, or the laws of the universe. And in the end of my talk, I shall make contact between what we are doing on metallic hydrogen and what may lead to aid in the sustainability of the universe. And as I mentioned the other day, in talking about the relationship of fundamental research to applied research, in 1947, the transistor was invented at Bell Labs, and this was by Schrieffer, Brattain, and Shockley. Yeah, and today, they made the transistor, and it was about this. They had transformed from using vacuum tubes in amplifiers, which were this large, to transistors, which were about the size of your thumb. And we've advanced to where transistors went down to the size of a cross-section of a hair on your head to extremely small dimensions that I won't get into today, but they're very small, and so you have millions of them packed into an iPhone or a smartphone that we all keep close to our bodies nowadays. I want to give a little bit of history on metallic hydrogen. So in 1935, Wigner and Huntington, Wigner was a Nobel Prize winner for his many theoretical predictions, but they predicted that if you compressed hydrogen to a high enough density that it would transform from a molecular solid where you have molecules bonded together to an atomic solid. That's atomic metallic hydrogen. And in 1935, they did not know the equation of state of hydrogen. The equation of state is the relationship between the pressure and the volume, or the pressure and the density. And so they used the compressibility at zero pressure and predicted that you would get the transformation at 25 GPa, or a quarter of a megabar, which was almost accessible in recent decades. But no one started working on this until Ashcroft in 1968 predicted that hydrogen might be a high-temperature superconductor, and everyone loves high-temperature, I don't know, it just turns people on, high-temperature superconductivity, and it could even be a room-temperature superconductor. So that was the 68 contribution of Ashcroft. Then later it was predicted that you might have a high-temperature transition to atomic metallic hydrogen in the metallic state. That is, you heat it up into the melting temperature, and I'll show some more of this in a minute, and it dissociates and you get liquid atomic hydrogen. This is sometimes called the plasma phase transition, or the PPT. There were also predictions of molecular metal that before it dissociated to metallic atomic hydrogen, it might ionize and you might have metallic molecular hydrogen. And finally, in this review, Brabant, Kagan, and Kolos in 1972 predicted that hydrogen might be, metallic hydrogen might be metastable. That is, that if you make metallic hydrogen and then take the pressure off, it stays metallic. The idea is something like this, that you might, would be a configuration diagram and the free energy, and you might be in a region here, this would be molecular, and a lower energy might be metallic. If you tunnel through, you could get into the metallic state, but you might be stuck in the molecular state, or if you heat it up, you could get over the barrier into here. And if you start taking the pressure off, you reverse the diagram. Modern calculations for the critical pressure for metallization are 4 to 5 megabar. It's been predicted that it may be a room temperature superconductor. It may be metastable, it's been predicted. And if you could make it and make a lot of it, it would be the most powerful rocket fuel in existence, not by a small amount. People I know from, so currently the most powerful is a mixture of molecular hydrogen and oxygen that burns, and that has a specific impulse, that's how they measure it, of 550 seconds. And friends of mine at NASA tell me that they would kill to increase it by 50 points, because it would have such a big impact on the payload. And if you calculate the specific impulse of hydrogen, it's 1700 seconds. So it would burn so hot that there are no containers for rocket propulsion to contain it. Before we can discuss superconductivity in metallic hydrogen, you have to make metallic hydrogen. So I want to show you an early experimental theoretical phase diagram of hydrogen. And that's here. Here we plot pressure versus temperature. And you can see that there are two pathways to metallic hydrogen. One is the Wigner-Huntington transition, which predicts that if at low temperature, their calculation was in the low temperature limit, that you would get here to metallic hydrogen. And what we found experimentally is that there are many phase transitions on the way up where you stay in the molecular phase, but you change the structure of the solid. On the other hand, hydrogen has a melting point with an unusual melting curve with an unusual peak, and then it decreases as you go up in pressure. This is an extrapolation here. If you go above the melting line, you have liquid molecular hydrogen, and if you cross this transition, you have a first order phase transition where the molecules dissociate and you get liquid atomic hydrogen in this region here. So there are two pathways, or we call them pathway 1 and 2. And we've observed both of these transitions. First, we observed the liquid-liquid phase transition. That's the diagram here. And this shows some of our data points for that transition, where we could actually heat hydrogen up to a few thousand degrees. We did laser heating to heat it up for very short periods of time and found all these data points here. The other way was the Wigner-Huntington transition to metallic hydrogen, which is coming along this pathway here to atomic metallic hydrogen. And if you look at the liquid-liquid phase transition, then this is what we think Jupiter looks like. Jupiter is about 90% hydrogen, 10% helium, and as you go in from the atmosphere, you get a gas of hydrogen and helium, and then you get you go through a region here where it converts to atomic metallic hydrogen, and it's this whole core of metallic hydrogen, which if it's moving, it creates what's called a dynamo effect, and it gives rise to the magnetic field of Jupiter, which has recently been observed in space probes. Well, because of the limitation of time, I'm not going to discuss both of these. We'll focus on this low temperature phase transition here, the Wigner-Huntington transition. So I'll start out describing what a molecule of hydrogen looks like. You have two protons, and these almost circles here represent the electron density. So you see that a molecule of hydrogen does not look like a dumbbell, as you might think, but it looks almost like a sphere. Not quite. It's got a little bit of ellipticity in it. If you look at the electron density, you find that there's a high you're in a state where the electrons are anti-parallel, so you can have electrons piled up in between the two protons, and it's the Coulomb force of these electrons here that are in between that hold the molecules, not the molecules, the protons together. So it has a binding energy that you could calculate, that has been calculated, of 4.74 electron volts, or 55,000 Kelvin. That's a pretty strong bonding. But if you want to break it apart, you have to take into account that this is a quantum mechanical system, and so it has 0-point energy. If you subtract off the 0-point energy, to dissociate the molecules, you need a lower energy of about 51,906 degrees Kelvin. And as you get far out into the wings, the density of hydrogen in the solid, it's a very low density, so you have very little overlap of the molecules. So this is what it looks like if you're at a two-dimensional picture. It's really three-dimensional. But if you look at hydrogen at zero pressure, the two protons are about 0.74 angstroms apart, and the molecules are almost 4 angstroms apart, 3.8 angstroms, which is a very large separation for a solid. So the molecules at zero pressure can freely rotate and vibrate, but you have collective excitations in the system. If you press it, they get closer and closer together, and eventually an atom here can't decide on whether it should be bonded to this atom next to it or the one in the adjacent molecule. And so it probes out, the system fluctuates, and it finds that it can lower its free energy. If the pressure is high enough, it can lower its free energy by dissociating and forming atomic metallic hydrogen. And if we call the density at zero pressure 1, then when it becomes metallic, it's about 14 or 15 times compressed. Okay. And this is where you expect high temperature superconductivity, and it's also been predicted that you might have high temperature superconductivity in the molecular metal. So we get these high pressures using diamond anvil cells, and this is a picture of our cell here. It's about the size of a Coca-Cola bottle, and in the center, down in here, you have two diamonds, and in between the diamonds is a gasket with a hole in it, and the sample's in that hole. This diamond anvil cell is such that to generate the pressure, one diamond is fixed in position and the other can slide back and forth. So if you turn a screw, a wedge comes down, it pushes this arm out, and it pivots about this point here and pulls this other part in here. So it's really a high-tech nutcracker. You put a nut in between and you squeeze on it and you get extremely high pressures. So in the center right here, it looks something like this. You have the two diamonds. You have a gasket here. This is a picture of the gasket. The diamonds have a flat on. This is called a coulet. It has a flat right here, and we use flats with it, which are about 30 microns in diameter, and the sample starts out in the hole here. You load it into the hole, and then you squeeze on it. As you squeeze, the hole gets smaller, so the density goes up. There have been, if I put on all the theoretical papers in the last several years, I need 2 or 3 pages. So I just have a couple of them listed here. But there have been dozens of papers, and what they find is that density functional theory, which has been used for many heavier systems, doesn't work for hydrogen because you have a lot of zero-point motion. So the best calculations have been done using quantum simulations of hydrogen. They use quantum Monte Carlo and techniques like that. And they've predicted transition pressure of 400 to 500 GPa, and this is a space group, I41/AMD, for, or a possible liquid ground state, as Kolos, Kagan, and Kagan predicted. The experimental search for metallic hydrogen started after the late Neil Ashcroft predicted this. What prevented the observation of the Wigner-Huntington transition to atomic metallic hydrogen? People weren't getting to a high enough pressure. As they went up in pressure, the diamonds would break before you reach the acquired pressure. Prior to our success, the reported pressures on hydrogen and its isotopes, deuterium and HD, were about 3.5 megabar, and the diamonds broke. But research groups continued with the same procedures and had difficulty exceeding that pressure. There was one group that said they had 106 loadings of hydrogen in diamond anvil cells, and only 6 of them got up to 350 GPa. Well, a remark once sometimes attributed to Albert Einstein is insanity, doing the same thing over and over again and expecting different results. Well, we weren't insane. we tried a number of things. We'd worked with hydrogen for a long time, and we changed our approach and eliminated procedures known to lead to diamond failure. We used synthetic diamonds, which are chemical vapor deposition grown, CVD grown. Natural diamonds tend to be inhomogeneous and have inclusions, and I'll show you that in a second. We also removed, when you get a diamond, they can be very rough, and so you have to either cleave them or polish them. And when you polish them, you can create defects in the surface. So we would etch off the surface using reactive ion etching and anneal to about 1200 degrees Kelvin to remove residual stress in the diamonds. So this shows an X-ray tomography. It's like a CT scan of diamonds, okay? And these are natural diamonds which with bright field microscopy look beautiful, but if you look inside you find all kinds of deviations, variations of density and so forth. And so sometimes you start a run planning to go to very high pressures and the diamonds unexpectedly break at 0.5 megabar. This is a CT scan or a tomography of a natural synthetic diamond, and you don't see any of these defects. So we started using synthetic diamonds. And this is an atomic force microscopy scan of the surface of a diamond. This is one that wasn't polished in the right direction. Diamond polishes very anisotropically, about 100 times faster in one direction than the other direction. So if you polish in the wrong direction, you can create a lot of defects like this. Whereas if you polish in the right direction, you get this is a fairly smooth surface here without defects. And if you pressurize it with a defect in your coolant, that's where you can catalyze failure of the diamonds. The other things that we've done is that precision alignment is very important. So if you take two diamonds and you align them so that the coolants are opposite each other, and as you put the load on or the pressure, if they shift or tilt, then they're going to kiss and they break. And so we developed techniques where we could put the diamonds before we loaded, put them on very heavy load and make sure that they stayed aligned during that whole process. It's been found that if you take diamonds to room temperature in the presence of hydrogen, the hydrogen diffuses into the diamonds brittle, and they break early. Early means low pressure. So we coated all of our diamonds with alumina, Al2O3, and this acts as a diffusion barrier against hydrogen, preventing the hydrogen from diffusing into the system. Nevertheless, we had some evidence that at higher temperatures, you still had diffusion through alumina, so we maintain the hydrogen in diamonds at liquid nitrogen temperature. We do cryogenic loading at 77 and never go above about 77 or 80 Kelvin to inhibit the diffusion. And then the group of Art Ruoff at Cornell had loaded 15 sets of 15 DACs with diamonds, and they got up to pressures of about 300, 350 GPa. And every time they shined a laser in, they were trying to do Raman scattering to study it, study the phase transition. Every time they shined diamonds in, the diamonds broke. Okay. Every time they shined a laser in of sufficient energy, the diamonds broke. So you have to be very careful because light can interact with defects in the diamonds and they break. So we never shine laser into the diamonds until we get to really high pressure, then just to measure the pressure. And so we use FTIR infrared spectroscopy to study the system. So how are phase lines determined? Because you want to see those transitions. It turns out that hydrogen at zero pressure can have phonons, which is a vibration of molecules against each other. They can have rotons, which are these quasi-rotational excitations, or vibrons, where the protons within the molecule vibrate against each other, and they're collective excitations, and they're called vibrons. And so it turns out that various excitations are either allowed or forbidden. You can do a space group analysis, and you find that when the IR absorption or Raman scattering are allowed or disallowed. So we use, we try, as I said, we don't do Raman scattering. We use IR illumination. And here I show a picture going up in pressure. So this is, we're plotting here the absorbance as a function of frequency. And as we go up in pressure, local, this is 304 GPa, we see a vibron shifting. And then you get up to about 350, 360 GPa. And the spectrum changes. You get new modes over here. And that means a phase transition has taken place. And we call that H2 pre when we saw that at about 350 to 360 GPa. And we've measured it 3 times, and in the second run, we made metallic hydrogen. Okay, so the experimental observation of metallic hydrogen is shown in the next transparency. At low pressure, so I call low pressure here, oh, something's missing here. It's supposed to show the pressure. This is about 200 GPa here. Hydrogen's transparent, that's backlit. This is about 420 GPa, and when you get up to these higher pressures, the hydrogen turns black, and the shiny part around it is the rhenium gasket, which is a metal and reflects the light. But the hydrogen is evidently a semiconductor, and it's black molecular hydrogen. Some people think it might be a metal. We don't think that's the case. And then you go even higher in pressure, and it starts to shine like a metal. So then you measure the reflectivity of the hydrogen. So this is reflection, these points here. These points we had to throw away because we found that the diamonds themselves were absorbing light in this region, and so you could not really measure, accurately measure the reflectance. Here we have data on rhenium that shows that we're making nice reflectance measurements on the rhenium. So we could take these data points and fit it to a Drude free electron model, and that model gives rise to something called, if you fit it, you get something called the plasma frequency. So the plasma frequency, omega plasma, is something that's 33 electron volts that you get out of the fit to the Drude model, and it depends on the square root of the density of electrons, or the density of electrons given the plasma frequency can be calculated to be about 81 in these units here, 10 to the 22 per cubic centimeter. You can calculate what's believed to be the density of protons. It's in this region, so you see that we have an overlap of 1 electron with 1 proton, and that means that you have atomic metallic hydrogen.
Professor Silvera, it would be great if you could if we could end in a couple of minutes.
Yeah, I'm almost done. Okay.
Great. Thank you.
This is the phase diagram that we found then with metallic hydrogen here at about almost 5 megabar. And we thought that colleagues working in the field of metallic hydrogen would be delighted with the fact that we made it. But turns out that in this field, people are very contentious, and they put several criticisms on the archive. Criticisms like, no one has ever achieved this high pressure with conventional diamonds. And our response was, 25 years earlier, these people here saw pressures of 560 GPa, but not on hydrogen. And we've achieved high pressures on the system. Another one was pressure was not measured and must be much lower than claimed. All we claim is that we got to higher pressures than anyone else had, and what does it matter if you don't know the pressure accurately if you made metallic hydrogen? The most important one that we agree with was that the observation should be repeated. And we've done that. We've had a couple of runs. We didn't publish it because we didn't measure anything new, but this is one where we made metallic hydrogen, heated it to room temperature, and it continued to shine. And this is another one here where we made metallic hydrogen in another run. And after it became black, it started shining. So how can metallic hydrogen contribute to sustainability? If it's metastable and we have metallic hydrogen at ambient conditions, and if it's superconducting at room temperature, well, we lose about 20 to 30% of the power in the electrical grid by dissipation, heating of wires. So you could replace the grid with superconducting metallic hydrogen wires. MRI, magnetic resonance imaging magnets, currently need liquid helium, so they can't be used all over the world where you don't have helium. You could replace the superconducting magnets for MRI with, you could replace the current magnets, which are superconducting, with superconducting metallic hydrogen wire wound magnets, and you wouldn't need liquid helium. You could, currently in integrated circuits, most of the dissipation is due to the interconnecting wires. You could replace them with superconducting metallic hydrogen. And rockets with metallic hydrogen fuel could enter orbit with single stage for space exploration. So these are our current objectives: to remeasure it, extend measurements into the infrared, study superconductivity, metastability, and try to determine the structure. And for that, I thank you for your attention.
Yeah, thank you very much, Professor Silvera. Yes, it's amazing and interesting talk. Thank you very much. I would like to have just a couple of questions. Yes, I know we have scientists, prominent scientists from this amazing and promising field. So just to meet the time schedule, so I will try to concentrate on the students. If there's no questions from the students, I will go to our esteemed colleagues. No, you are not a student. Mahmoud.
I'm still a student.
Yeah. Okay. Students. And any question from the students, let us say first.
So.
Yeah. Mahmoud, sorry, I will come back to you. Because you are our co-president.
Hello. So first of all, thank you for the talk. I was just wondering, so how critical is the purity of the hydrogen? For example, not having deuterium or something else. So how does it change the whole procedure of?
I don't think that. Well, we use ultra high purity 4-9 hydrogen, but if you have a little bit of deuterium impurity, it's not going to have a big effect. Vice versa, if you have make metallic deuterium, which we plan to do, a little bit of hydrogen is not going to be a problem. If you take HD, we've studied that and found an interesting thing that at about 200 GPa, HD starts deteriorating and becomes H2, D2, and HD. Okay, it kind of dissociates and recombines. So if you get HD molecules dissociating, the two H's can recombine, the deuteriums can recombine, and you get a mixture.
Thank you.
Okay. I will move the mic to Mahmoud and then here. Okay. Mahmoud.
Thanks, Aik, for the nice presentations. My question's on the published Nature paper by Ranja on CSH. So there is a criticism by Jorge Hershey from University of California that there is something wrong with the magnetic data. So, and even he also do not believe in the BCS theory. So what about your opinion about his criticism, and what about your opinion also on the paper in general? Thank you.
So to repeat the question, my former postdoc, Ranga Diaz, and his group, he's now at the University of Rochester, made a compound called CSH, carbon sulfur hydride. So hydrides have high temperature superconductivity, and they showed that this was a room temperature superconductor at high pressure. There's a theoretical physicist at the University of California in San Diego, Jorge Hirsch, and he was objecting to it, saying that there were problems in the susceptibility. So Nowadays, if you want to show that a material is superconductivity, it is not sufficient to show that the resistance is zero. You also have to show the Meister effect. And the Diaz, they measure the Meister effect, but Jorge Hirsch, he doesn't believe in BCS superconductivity. So I've looked at the data, and I think the data, and others have, and I think their data is perfectly good in the analysis. The problem that you have in measuring the Meister effect, you have a very small sample in a diamond anvil cell, and at high temperature, you're trying to measure the susceptibility with a wire wound around the diamonds, not around the sample. And so you have a very low, poor filling factor, and you get a lot of Johnson noise, which gives rise to currents due to fluctuating electrons. So you get a very big background, but on that background, you can see a kink where you go through the phase transition. So I think it's correct, what they have, the room temperature superconductivity. It's a valid measurement.
Okay, last question here, and yeah.
I have a kind of student question. Was it considered alternative way to reach such huge pressures, something like explosion, or it is nothing to think about?
Yeah, okay, I'll give a student answer. Yeah, there are two ways of reaching high pressure. One is static high pressure, which I showed, and the other way is, originally it was shock wave physics, where you basically take a sample and boom, you hit it with a projectile and it sends a shock wave through it. Currently, people have developed techniques where they can do controlled collision so that they don't have real shock waves, and they can get up to high pressure, but they always go to fairly high temperature. So it's good for studying the liquid-liquid phase transition, but not for metallic hydrogen. Okay?
Yeah, thank you very much.
Thank you.
Please join us to thank Professor Silvera.
Okay, yeah, I'm sorry for the time limited, but we have Professor Silvera and all of our colleagues and prominent scientists. So we have them around, so we could discuss with them, network with them, exchange with them. This is really amazing and unique opportunity. You should beneficial from it. So now we are ready to welcome our next distinguished speaker, Professor Alejandro Silanek, professor at the Université de Liège and head of the research group Experimental Physics of Nanostructured Materials. He obtained his master's degree in physics in 1997 at Universidad de La Plata in Argentina, and the PhD degree in physics at Institute Belisario in Argentina in 2002. He spent 8 years as a research associate at the Catholic University in Leuven in Belgium, and about 2 years at the National High Magnetic Field Laboratory at Los Alamos in America. Since the end of 2011, he is a professor at the Université de Liège and head of the research group Experimental Physics of Nanostructured Materials. He has co-authored over 190 publications in diverse topics, including nanostructured superconducting, metallic semiconductors, and magnetic systems, planar plasmonic metamaterials, biomicrofluid devices, heavy fermions, and quantum critical points. Professor Silneka group is active in the domain of low-dimensional systems, including magnetic and superconducting materials and hybrid structures. The main experimental facilities include a platform for nanofabrication by electron beam lithography with a multi-purpose physical deposition system, magneto-optical technique and electrical transport properties of materials at low temperature. Topics of current interest are fluctuation and low-dimensional superconductors, controlled electron migration, manipulation of flux quanta, and thermomagnetic instabilities in superconductors. Professor Alejandro, the floor yours. I could help you, but perhaps we should.
It's fine. I guess I close this one and I combine here. Where is the mouse? Okay, thank you very much, Mr. Chairman. With this long introduction, I think I will very, very quickly on the first slides. So I'm going to talk today, we'll change gears here and with a completely different topic. I'm going to talk about electronic erosions in nanocircuits. So has little to do with single crystals. And I'm going to start by showing you a little bit of our university. This is a university in Belgium. Belgium is the small country you see over there. It's about 3 times smaller than Jordan, okay? And we have 3 official languages over there. So German, the red part is French, and the yellow is Netherlands. So I live on the yellow part, and I work on the red part. And they don't like each other, so it's about 100 kilometers one place to the other. So this is a bit of the environment of our university. It has been founded in 1817. So at that time was Napoleon, actually, who gave the order to make the university. So actually, university is older than the country itself. Okay, Belgium existed after that. And was relatively big university for what is Belgium, I would say. So our activities are on different topics. I was just mentioned by the chairman, so I will not go through again. But perhaps one of the activities I want to mention is magnetic landscape of superconductors and ferromagnets. And that is where we have a strong collaboration also with Mahmoud. And we have published a couple of papers on that topic before. So what I'm going to talk today is, if you allow me, is basically this topic over here, which is called electromigration. Okay, so I'm going to make a smooth introduction to the topic, and by starting, posing the question, what is the maximum current density we can apply to any cable? And so if you go to household appliances, at home, you will find that actually you hardly ever go above 10 to the 4th amps per square centimeter, because if you go above that current density, you just melt the cable, and that's the way a fuse works at home, okay? But this is not always the case. That's what I put here, size matters, because if you go to small dimensions, and then I'm talking about the wire, which is in an integrated circuit, the heat can be very easily dissipated, and then you can go to much higher current densities, 10 to the 8 amps per square centimeter. And if you do that, the wire, this maximum current actually is not because you're going to melt it. Even if you go to that value, you're far below the melting temperature, but the cables break anyway. And this is a serious problem in any computer. And IBM has spent billions of dollars trying to solve this problem, okay? So what's happened if you don't melt it? How the system breaks? The way the system breaks is by generating small cracks, or sometimes small overgrowth. So it depends, okay? So either you remove material or you add material. And this phenomenon has been known from the 60s, and it continues to be a big problem, particularly when you switch to flexible substrates, or when you, introduce high density of cables in your integrated circuit. And the physical reason has to do with the fact that at such a high current density, there is a wind of electrons flowing in your metal, which is pushing the atoms away from their position. So this is a very, very cartoon-like representation of an array of atoms, ions, positive, and then you have an applied electric field going from right to left, and that gives a force on the ion, but on the other hand, you have electrons flow in the other direction. I mean, assuming electrons are the carriers, and they are producing a sort of a force which moves these atoms away. And so when you go to very, very high density of current, you have a lot of this wind which can move these electrons away from the position, and then you can remove material. So just to give you an idea how stressful this is for the materials, I'll show you a small calculation of the current we need to electromigrate to move atoms in one of the compounds I'll show you later. For this resistivity, this is more or less the current density we use. We have a power which is about 5 gigawatts per cubic centimeter, and this is about the power generated by our nuclear plants in Belgium, but in a 1 cubic centimeter. So it's a lot of stress we put on the sample for a short time. So the idea is to use this technique to do something useful. I mean, so far it has been painful for people doing computers, but we try to do nano fabrication with that. So I'm going to see if I can run this small video here. Doesn't matter. Supposed to be a video there. Oh, it's working. Okay, I don't see it here. So what we do is we apply very high current and we heat up locally, and this is an activated, thermally activated process. You need to heat first and then you start moving. It's much easier, right? The problem is that when you have, I mean, here we make an indentation to start electromigration at a certain point, and then we apply, we have a lot of current crowding, and we start to move the material, so we have more current crowding, so the temperature goes even higher, and then the resistance starts to change in time, and that makes the void is even smaller, and then we have still more current crowding. So this is a positive gain feedback loop, and that makes that if you try to do that at home, if you monitor the resistance function of current, you have an increase of resistance, which is just Joule heating, and suddenly, bam, the system just explodes. You have no time to react. So I show you an example of me trying to electromigrate without any break, and then you see the original device, and after trying to electromigrate, it's just exploded. Okay, so not fun. So we'll try to control that. And to control that, we use a feedback. So we monitor all the time the resistance of the sample, and this is the result. So this is a real curve. This is the resistance of our device as a function of the current we apply. So the black curve is the experimental data. You just follow it. You heat up the system. Nothing happens. This is just Joule heating. You turn off. You come back on the same curve, fully reversible. But once you get there, to this point, the system wants to explode, and then you start to decrease the current to avoid the system to explode. But you keep stressing. So the system starts to move the atoms, and then you keep decreasing the current, and in that way, you're able to modify the device. So if you take a picture, you have the original device which is there. When you get to that point and turn off the current, you come back to a different resistance because you modify. You look at the system and you have a small hole. You do it again, and you have another small hole. And that way you can go all the way to a single atom. We have resolution to the quantum conductance on the system, so you can do it very, very precisely. I mean, of course, the temperature here, we start at 1.5 Kelvin, you end up at 230 Kelvin. This is a small movie of how does it look like under the SEM in real life for one particular material. Of course, we take a few images only because otherwise you contaminate and the images get very, very poor. So we use that to modify, to make small nano gaps in the system, which is very difficult to do by normal electron beam lithography. And I'll show you here there is another advantage of this, and it's the fact that it's reversible. So let's have a look on this curve. Resistance of our sample is a function of current. So once again, this very smooth increases Joule heating, and this is very noisy because this is a fight between me trying to stop explosion and the system trying to explode. Okay, so this is why it's like very, very noisy. But then we increase the resistance of the sample for the factor of 3 or more, and then if you stop there and you make an image of the sample, you get that, okay, I remove part of the material with the current, okay? But then what I do is I reverse this current, okay? I reverse the polarity of the current, and what happens is I can put back the material I took off. So I'll show here the curve. You should see it, is the red one. So we start from here, we reverse the current, and we go down in resistance. When you look at the image again, you see that you fill in this part that was there. And then you can do it again and again. Okay. Yeah, so go back and forth. And actually, we tried to use that and propose that as a way to make a small memory device. So what we do is we make a small indentation, and we just increase the resistance. This is the blue curve. Reverse the current, decrease the resistance. Reverse the current, increase the resistance. Reverse the current, decrease the resistance. And then you can do that. This is just a zoom. You can do that thousands and thousands of times, and very, very stable in the system, as long as the amplitude. So it was like a sort of a, yeah, I don't know, room temperature poor memory device. So what we have done more interesting is to modify superconducting devices, because in that case, you have a resolution which is atomic-like. You want to do it with lithography is extremely difficult or on top of that is very, very expensive. Here you just make a device, and then you apply current and you modify it there where you need. So we have a superconducting squid in niobium here, does not work reversibly as we want. We electromigrate, bang, we modify the junctions, and it works perfectly. And that works also for aluminum. More recently, we have extended that to 3-terminal device. There is a lot of interest now in the superconducting circuitry society for making multi-terminal Josephson junctions. There's a lot of applications, and here we just recently showed that you can do that also with 3, 4 N-terminal devices, and this is a very cheap way to do it. So now the question we posed lately was, okay, so far I show you what happened with a single metal like, I don't know, nickel or aluminum or, let's say, niobium. The question we wonder was what happened if we take a very complex material where we have a whole family of different atoms. Which atom are we going to move? So I came to my roots and say, let's go to YVCO. There should be something interesting there, and there is nothing more complex I've seen in my life than YVCO. And so we took that, and the first thing, I mean, of course, for all those who are physicists, you know that if you pose a question today, there is always a Russian who posed the same question 30 years earlier, okay? So I found some colleagues that did some initial work on that direction, but we tried to go farther than that. So this system is composed, for, as you might see, of several atoms. There are basically 2 conductive paths in this system. One are what is called copper oxygen planes, which are these plaquettes here and here. And there are these copper oxygen chains, which are there. So the first question when you want to move atoms is to understand where the current is flowing. So we go to the old papers, and we found out that these guys, Friedman and company, they measure single crystals of YVCO, and they concluded that if you apply the current along these copper oxygen chains, this is the B axis of the material, actually current flows in the chains and also in the planes. However, if you apply the current in this other direction, the electrons cannot hop from one side to the other, and only the planes contribute. And out of this simple calculation, they estimate that 60% of the current goes to the chains, okay? And this is something interesting, because in the chains you have these oxygens which are there, and if you move these oxygens with the current, they might come to this place here, where is my cursor now, and which is an equivalent place, without not much effort. And if they are there, you can actually move around without much problem. And this is indeed what has been predicted. So this is a top view of the material. So the idea is like you might be able to move this oxygen from there to there, and then it's rather simple to diffuse in this direction. So theoretical predictions and some experiments have shown that the diffusivity of this oxygen along this axis is a lot larger than along this other axis A, and much faster also than along the z-axis. So what is interesting about that? So first of all, we are saying here already anticipating that with the current, if we apply high current in this system, we will move the oxygen, okay? So the other thing is like, why is that interesting? Because if you move the oxygens, you change the length of these copper oxygen chains, and that's gonna have an impact on the doping of the material. Basically, you dope the copper oxygen planes, and by doing that, you can actually build up the whole phase boundary of this material. So this is temperature axis, this is hole doping. So you can go from antiferro to this quantum critical point we were listening today. And the interesting thing is you can do that with the current. So that's the tuning knob you have to modify this. That was a cool idea to try. So some people, of course, try to do that with the electric field, not with the current. So they need huge electric fields. I show 3 examples over here. And on top of that, they really need a very, very difficult sample preparation. You know, you need to put overlying layers and a lot of nanostructure. So in our case, we just did very simple samples. We just take, you know, this is the yellow stuff is YBCO, the gray is just to have ohmic contacts, and if you zoom in at the center, we have these narrow constrictions and 2 neighboring bridges to see where the oxygens are going, let's say. That's the idea of this device, okay? So, and if you measure the resistance function of temperature of these 3 devices, you see the device blue is blue curve, the central is green, and the left is red. If you measure the 3 of them, of course you need to normalize because the central bridge is narrower. You see that the initial system behaves really like a monolithic. The response is exactly the same. Doesn't matter when you measure, the transition is exactly the same. And then we apply a huge current, and we realize that we change the properties of the material, but in a directional way. So first of all, I reproduce the black curve here is the same that all this bunch of curves here, okay? This is the pristine sample, the black curve. If you look at the right bridge, you see almost didn't change at all. It looks very much the same. You even improve a little bit the resistance, okay? It maybe went down. But if you look at the central and the left, you have a huge modification. And this is because we move the oxygens from this side to this other side, let's say, from the central to the left. Then we took images of the bridge, and we noticed that this can be traced by reflectivity. So you see, I mean, there has been a prediction already here in this old article. They show that you have an increase of reflectivity where the oxygen content has been depleted, and this is exactly the side. This bright part you see over here is where the oxygen vacancies are, okay? And the oxygen, we put it on this other side. Okay. So, and then we try to, do that by steps. So we measure the critical temperature of the sample for these 3 different bridges you see with the color code here. So this is initially is monolithic. You make a very small electromigration. You see that basically the blue stays the same, and the red the same. The green starts to be modified, and you do more and more and more current stress. You see that the blue does not change. Okay, so you're just adding oxygens over there maximum, and while the red and the green are really getting a lower TC, and that means you're missing oxygens in that part of the material. So if you do whole measurements, now is this tiny red and this tiny blue, you might infer also the carrier density, and you see on the blue sides is, I mean, if it's something is a little bit increasing perhaps, on the right side you are decreasing. So you clearly removing oxygen from that. And so based on that, we propose, well, why not to try to build up a TC versus carrier density phase diagram, or your tendency. And these are the dark points you see over here, and we compare with the one of the most complete works done on YVCO, but using different samples. Okay. The advantage in our case is this is exactly the same sample, so it's very easy to compare. Error bars goes down. So we propose this is a nice way to tune a quantum critical point by current, because comparing samples is always a little bit difficult. And that has been done very, very recently. I will not show the data, but by people in Chalmers, group of Floriana Lombardi, and they have followed our, let's say, suggestion and done that. So just to show you, try to convince you that we indeed move the oxygens. We did some micro-Raman measurements. So we took, at these green spots you see over here, we measure the Raman response. And the idea is we focus the attention in a vibrational mode of the oxygen. The apical oxygen is here. So these blue arrows here show how is the oxygen moving. So this is not the oxygen of the copper oxygen chain. So that's not the oxygen we are moving with the current, but it tells us how we are modifying the unit cell. So basically, if you look at the size of the unit cell as a function of the oxygen content, so as you remove oxygen, you move in this direction, increasing delta, basically the unit cell become larger, and therefore these vibrational modes become softer, okay? And this is what we try to track over here. So if you look at the pristine sample, it's rather constant. Once we electromigrate, you see in the central section, we see a decrease, softening of this mode. And when we electromigrate again, it looks like it propagates on the side. So we did further visualization, and this is my last before slide. And we tried to see how that goes. So this is the device. We apply the current from here to there, and then you see how this yellow part propagates, and then at that moment we reverse the current in this direction, and it moves on the other direction. And yeah, we'll do that several times. You don't see it very clear, but there are sort of waves. That's what we do differential imaging, so subtracting one to the other, and then you can see different propagating waves of oxygen on the sample. We have done this also in manganites, like lanthanum, strontium, manganite oxide. And these are working very nicely as well, and there you can change the magnetic properties. So to finish, I'll come to my conclusion. I think we show a powerful technique to target modulation of properties of some materials, and you can do plenty of things. We have done like weak links, we have done also change of doping. You can use it to clean your graphene. You can use it to generate nanogaps and contact molecules. You can do to generate heaters out of a superconductor. So many, many different possible approaches. Perhaps an interesting is the one to try to fine-tune a quantum critical point, or make real devices like resistive switching. This is a very accessible physics. So I will propose you, if you are interested, I'll give you a hand and send you a kit, and you start electromigrating tomorrow at home. Okay, thank you very much for your attention.
Thank you very much again, Professor Alejandro. We have time for a couple of questions. Okay, let's start from here.
So very interesting. Did you look at the finer details in the migrated samples using probes like XAFs and things like this, so you can detect the local structure of oxygen atoms before and after being moved? Do you have any deeper understanding of the structure before and after?
No, that's a very good question. We do not access, or we didn't try to one of the limitations is always to get to this small size. We are talking about a cross-section of 2 microns, and sometimes you need to collect the signal from that. So as long as you can focus the signal on that scale is good. We have done more microscopy images. I don't show, and show is very inhomogeneous for this scale already. Okay.
Okay, I will move to this side. Yes, please.
Very nice talk. Couple of short questions. So first of all, when we did this a long time ago, measuring just bulk single crystals, the problems were usually the ohmic contacts. So can you use to improve the ohmic contacts in IPCO and other materials with migration? That's the first question. The second question, have you tried to make Josephson junctions on this IPCO using this way?
Yeah, so indeed, you can improve. I don't know if you can do ohmic contacts, but definitely you can improve bad contacts by doing this. This is very well known also for those doing nanowires for transparent conductive materials. They do nanowires and they actually apply high voltage, and they talk about melting, which is not melting. I mean, sintering it has to do with the electromigration, and that works very well. Yeah. So concerning the other question was about the I didn't show the curve because I thought it was too technical. But indeed, in this, the first thing we did is a Josephson junction, and now we are doing this. I show you these 3 contacts. That I can show you. We can address individually each of them and make a Josephson junction in one, not in the others, and select which one and which degree. There's a lot of control on that. Yeah.
So, thank you for this interesting presentation. So I have 2 questions. First, when you change the oxygen content, you decrease the TC. So it is a negative effect for TC. Second, for the magnetic system, as you said, what about the TC and colloidal magnetoresistance if you change also the oxygen content?
Yeah. So here we deteriorate a bit the material. That's what we are looking for because we wanted to see the phase diagram as a function of oxygen. But interestingly, before you deteriorate the material, you get it better systematically. For example, YBCO, if you have like not a super top transition superconducting, you apply current, and if you're moderate, you don't reach yet, you always improve it, always. We have niobium of TC of 7 Kelvin, we do process with the current and we get it to 9 Kelvin sometimes. So there is a regime I didn't discuss, which is before deterioration, where it gets better. Okay, and in the case of LSMO, the magnetic materials, we of course deteriorate that, the TC.
Thank you very much. I will have time just for one question from students. Where is our students? Female students, I prefer to have female students. Any questions? Just for gender balance.
There were 2 questions of a student, or 3.
Okay, no questions?
Yeah, there are questions here.
Okay, here.
Thank you so much for this interesting presentation. I was just wondering, related to the experiment you presented, about the destroying of the materials. Does it really being calculated or it's by sudden? That's my first question. Related to the second question, what about the kit? Where could we find it, please? Thank you.
You would. I'm sorry, I didn't understand any of the 2 questions.
Okay, my first question.
Let's go for the first.
Okay,
yeah.
My first question was about the experiment you discussed at the beginning of the presentation, related to the materials and how they are destroyed. Are those and exactly about how is it really destroyed? Is it destroyed by calculations or by sudden? So you calculate when it's really destroyed, or you don't know where exactly does it destroy? That's my first question.
So the question is, where is destroyed?
Yes, exactly.
The location.
Yes.
Yes, yeah. So that's
is it calculated?
Calculated. Oh, that's an interesting question. I don't do calculations. Okay? Perhaps someone can calculate. I don't think so. This is a very complex problem, and it is very material dependent. For example, if you go to aluminum, most of the process goes through the grain boundaries, and I didn't tell, but it's a lot more than electromigration. It's thermomigration, because we produce a huge thermal gradient, and that is more important. For example, in this sample was made. Oh, I didn't see it. This sample is made of aluminum. Okay. So, and we made this small constriction you see over here, okay? So all the current go here, and you expect to electromigrate there because it's the highest current density. And sometimes you electromigrate over there. There is almost no current density over there. And that has to do because there is a huge thermal gradient, okay? And it becomes really, I mean, unpredictable, I would say. There is other materials as nickel, niobium, where it works exactly where you want, where it's narrowest, okay?
Okay, thank you very much. We'll take another question from there. Yes, please.
When we are talking about this small scale of structures, how does this method of treating matter affect quantum tunneling, for example, in the gap where we're talking about?
I have no idea.
Okay.
Okay, thank you very much. It really is a very nice, amazing talk and very concise answers. Yeah, okay, so join me to thank again Professor Alejandro. Thank you very much. Now we come to close this session, and now we have coffee break for 20 minutes. So please be here at 11:45, strict 11:45, please, 20 minutes, enjoy.
which will start with a panel discussion about unconventional water resources, in which I'll be the chair and the keynote speaker. And I welcome the speakers with me. Dr. Randa Bouzreq, the Director of Nanotechnology Center at the University of Jordan. Dr. Maha Halalshe from the Water, Energy and Environment Research Center at the University of Jordan. And Engineer Khaldoun Khishman is the General Secretary of the Arab countries Water Utilities Association, and he was the General Secretary of the Ministry of Water for more than 18 years. So just not to waste time, I'll just start with my presentation. And here I will be talking about desalination at ambient temperatures and pressure by a novel class of biporous anisotropic membranes. Briefly, I will just start with introducing you to the concept of membrane distillation. Maybe not all of you is familiar with that concept. Membrane distillation is a physical separation process in which a membrane acts as a physical support separating a hot feed solution from a cooler chamber. In membrane distillation, the membrane is hydrophobic, which means that only air or gases exist in the membrane pores, and the membrane pores should be dry all the time. The membrane distillation process, simply, it's distillation through membrane. So we have a temperature gradient through the membrane, and we call it the transmembrane temperature gradient. When we have a temperature gradient, here we heat, and here we cool. So there is a temperature gradient between the feed side and the permeate side of the membrane. This temperature gradient generates a vapor pressure gradient, and this is the driving force for the vapor migration through the membrane pores into the permeate side. Only vapor, because the membrane pores should be always dry. The liquid cannot penetrate the pores because it is a hydrophobic membrane. That means it repels water. That's the concept of membrane distillation. This concept is not a new concept. It was discovered by Professor Bodel in 1963, where he filed his first patent. That was followed by a publication by Professor Findlay. And here I just would like to tell you something. Professor Bodel filed his patent in 1963. The first publication came out in 1967 by a different researcher. And here, as a researcher, we always suffer from this problem. We only tend to read our own publications. So sometimes somebody else is doing the same, but we are unaware because we always tend to read our own publications. So in order to do research, we need to read others' research in order to be on the same page with other researchers in the scientific field. I will just mention to you quickly what was in that paper mentioned. It was mentioned about the possibility of evaporation through membrane and distillation through membrane, and the requirement of the membrane was mentioned here in that paper. A high resistance to heat flow by conduction, a sufficient but not excessive thickness, a negligible permeability to liquids and non-volatile matters, a low absorptivity of moisture, a uniform thermal conductivity, etc. This is the first things about membrane distillation. Research started in 1967, the idea came in 1967, but by that time reverse osmosis was booming, so all the membrane researchers shifted their interest into reverse osmosis membrane, and there was a period of hibernation of membrane distillation till early 80s when RO could not treat all the water that we want to treat. Membrane distillation came back to the picture, but unfortunately there was no knowledge about how to design or engineer a membrane that is specifically for membrane distillation. Membrane distillation has several advantages according to the concept that I've just explained. 100% theoretical rejection of all salts and non-volatile matters, lower operating temperature because you don't need to boil the water to get the vapor out of the membrane. We just have to apply a thermal gradient, temperature gradient between the feed side and the permeate side of the membrane. So 10, 15, 20 degrees Celsius, the larger the feed side temperature, the larger the vapor pressure, the larger the water flux. Lower operating pressure, not because the concept is not in RO. In RO, the separation technique, the membrane works in what we call solution diffusion mechanism. So we have to apply a pressure that is higher than the osmotic pressure to do the transfer of the water through the membrane. Membrane distillation, the concept of the separation is quite different. We have evaporation through porous medium, and this porous medium is hydrophobic. So we don't require pressure simply. We could work at atmospheric pressure and reduced vapor spaces compared to the conventional distillation processes. When I read first these advantages, I was wondering why this process is not commercialized for larger scale industry. And here came the answer. Membrane distillation suffer from certain drawbacks. One is the lower permeate flux, which we addressed in our earlier publications and patents. And the other one is the danger of membrane wetting. I would like to remind you here, in the beginning of my presentation, I told you that the membrane pores should be always dry. So if it's not dry and liquid penetrate through the pores, then the whole separation just collapses and salt will be transferred through the membrane. And the high cost of membrane used in membrane distillation. And here came something. We started, after we addressed the issue of the permeate flux, we wanted to understand the wetting problem more. So I was doing some modeling to predict the durability of the membrane. And I came across this fascinating equation. Actually, this fascinating equation is called Kelvin Equation. It's been known since like 100 years. But I found out, while I was doing the derivation, that Kelvin equation relate between the vapor pressure at the curvature of the drop and the vapor pressure of the flat surface. And I found out that the vapor pressure, we all know it's function only of temperature. If we increase the temperature, the vapor pressure increase. But Kelvin equation tells me here that it has many parameters that could help or do something about the vapor pressure. One of them is the contact angle between the water droplet and the membrane surface. And the most important is the pore radius. So I started doing some calculations, and I found out if we decrease the membrane pore size in the top surface to be in the scale of nanometers, and if we could engineer a membrane that is super hydrophobic to make this cosine theta, the contact angle I wanted to be above 150 degrees, I could increase the vapor pressure without increasing the temperature. And this is the result, this figure is the result of the modeling that I've made with my team. And we found out that if we could design a membrane that is super hydrophobic with the hydrophobicity angle of the contact angle between 130 degrees and 180 degrees. And if we make that pore between 0.5 nanometers and 2 nanometers with a very small thickness that is supported by another membrane, then we could really desalinize water at room temperature. That's what the model was telling me. So I proceeded and I calculated the gain in the driving force because of the capillary effect. And I found at 0.5 nanometer, even at feed temperature 25 degrees, but the actual vapor pressure is similar to that around 59 degrees. So the operating temperature is 25, but the actual vapor pressure because of the capillary effect is around 59 degrees. If we go the 40, there is 82 degrees. And if we increase the pore size to 1 nanometer, we still have the capillary effect. For 1 nanometer, for example, the room temperature vapor pressure will become around 43 degrees. And if we increase the pore size to 2 nanometers, then the gain in driving force decrease. So the smaller the pore, the better the capillary effect, even at ambient temperature. Now, we did the engineering of the membrane, we did the modeling. The other challenge was how to make such membrane. We were successfully, did that membrane, we were successful in doing that membrane, But unfortunately, I can't disclose more information because the patent is still pending, but I can share with you some characterization. This is the AFM results of our membrane, and you can see the thickness of the membrane was 1.3 nanometer. The contact angle was around 158 degrees. The good news is the membrane performance. At room temperature, this is 25 degrees Celsius. The flux of the membrane, water vapor flux, was around 40 liter per square meter per hour. And I made a comparison with the commercial membrane. At 25 degrees Celsius, the commercial membrane had produced zero flux, no flux whatsoever. But our membrane produced 40 liter per square meter per hour. If we increase the temperature further, then the commercial membrane start to appear in the picture around 4 or 5, but our membrane reached around 70. And if we increase up to 60 degrees Celsius, the maximum flux that the commercial membrane produce is around 48, but our membrane produced 225 liter per square meter per hour. I care about this one because one of the challenges of membrane distillation is that when we do the large scale, because it's a big module, there is a lot of heat losses. So it enters at 80 degrees Celsius, the water, for example, or 60 or 70, but when it leaves, it's around room temperature. So there is no flux whatsoever because it comes similar, the driving force just keep decreasing. But if we work at room temperature, then we will not have heat losses, and we were able to increase the vapor pressure without increasing the temperature. That's the breakthrough we believe we have made. Finally, I compared here the experimental data with the modeling data, as you can see, and it perfectly fit because the membrane we manufactured had a pore size of 0.7 nanometer. I will just finish with my conclusions. We have successfully engineered and fabricated a novel biporous anisotropic membrane. The new membrane enabled the operation of membrane distillation at room temperature and atmospheric pressure. This novel membrane can make membrane distillation and desalination in general a high energy efficient process and suitable for large scale module conditions. Here I would like to finish my presentation and thank you so much. All right, we will have the questions after we finish the panel discussion. So I will invite the speaker with me, Dr. Rand, Dr. Maha, Engineer Khaldoon. Please join me on the stage.
صح كنت بدي أكون بالنص.
So we have a diverse speakers. Me and Rand work more into nanotechnology. She is the director of Nanotechnology Research Center in University of Jordan. Dr. Maha and Engineer Khaldoon more into water governance and water, let's say, management. So I will direct my question to Engineer Khaldoon and Dr. Maha. You have seen something that is deeply technical. What do you think, where we are from the technical side in solving the water problem?
Okay. Okay. So, of course, it's always when we talk about this science policy interface, how to transfer what is in science to real application. So I usually think of putting myself in the shoes of a decision maker. Direct question would be on many questions came to my mind while you were presenting, like what would be the cost of such application if we want to scale it up? How much operation and maintenance is complicated? And then at what cost? And the reject, like how much would be the reject, you know, the reject of the process and how to manage that. So these kinds of questions, they usually come to the mind of any decision maker before deciding on the implementation. But from policy perspective, I would like to emphasize that in the region, desalination is coming. We don't have options to manage our water resources. There is increasing demand for water and high demand for going to unconventional water resources, including both the desalinated water, but also to the reuse of treated wastewater. And both, they are highlighted in many policies that are that you can see it not only in Jordan but also all over, looking for example to Egypt and to the countries in North Africa, but maybe Engineer Khaldoun can add on that. But in general, it is coming, the desalination of water for different purposes to cover the demand on the supply side, but it is part of the policy. But then the question is whether this is feasible or not. And this is the question of the million JD, maybe.
It's good that you didn't ask me these questions while I'm presenting. Engineer Khaldoun.
Thank you, Doctor. Thanks for this good new things to me, that it was what you presented over here. I think the name of our, or the theme of our session is the future of the water, unconventional water resources. Yani, as I will say in my presentation, we utilized all the conventional ones, ground and surface. What's remaining is unconventional and a part of the conventional, but in another way, using efficiency in that. When we talk about the new resources, of course, desalination and reclaim, I would like to call it reclaimed water. That المياه المستصلحة بالعربي, that comes out of the treatment process, this water treatment process. I think they are the future of the new type of water resources. Now, when we talk about wastewater, then we have to talk about applying the international practices and know-how, what we call it, and working now with Dr. Mara together in the sanitation safety plan. If you want to make reallocation of resources and take the fresh water to somewhere else, either industrial or municipal, then we have to improve the treatment to the tertiary level that we can use it in unrestricted uses, especially in agriculture and producing food. For desalination, yes, it's the only way for the future. But again, we have to look deeply about the energy cost. Because till now, I know that there is a decrease in the cost of the desalination due to the new techniques, membranes and others, but still the energy issue is the concern. And the energy now is increasing, day by day. Any crisis happened, like the current one we are facing, will increase the electricity and the energy. This will be reflected in the cost of production in water and all over, and desalination in particular. Having seen this, then we talk who will bear the cost of that. Is it the governments or is it a customer? In our region, I think only few governments in the Gulf can have this. Can have the cost of energy in producing desalinated wastewater. But in our region, in our countries like Jordan, I think also the customers can do, unless you bring some private sector to implement these projects and finance these projects. And you know, for the lending money, the high investment is very high. So what we need from the scientists, especially in this particular, is how to work in more and more reducing the energy by improving the membranes, continuously the membranes. Could be the nano, the future, to my small knowledge, could be new types of membrane that you worked on. And we have to give up this traditional type of desalination process like in the Gulf, especially the thermal one. The third unconventional, which is, I believe, is the efficiency in utility. We are losing more than 50% non-revenue water. Yani, I don't think it is a logic that the cost of desalination per cubic meter could reach $1, and again, its operational cost, you need another $1 within the network, and again, I'm losing 50%. Why counting this in Amman? I did a master plan for Amman, Aqua, I mean, not myself, my organization, and also a master plan for the water sector in Jordan. In Amman, we are losing, we are about nowadays 43 to 45% of the water. It's not physical. It's apparent losses. It's illegal. It's you don't know your customer. It's the cost of energy. It's the losses in not integrating all the systems. The business plan, we did it and it was approved by the cabinet, but nothing came in the ground. That by investing near about 150 million JDs, then we can reduce about 50 million cubic meter of water. And 50 million, if you want to make investments to produce another 50 million, and mainly it will go for desalination. We agreed no more conventional, then you are talking a lot of millions and a high cost of capital cost. We have to look, should we spend 150 million to reduce non-revenue water, or should we build another desalination plant, which is, I think, you know much better how much it costs for 50 million cubic meter per year. I think we have to go both, but again, we have to look for efficiency of utility, which I believe the governance in controlling and managing the utility, it will help in reducing the gap between demand and the available resources. Thank you.
Thank you so much, Your Excellency. Dr. Rand, because you're specialized in nanotechnology in water treatment, could you just highlight to us what's the future of nanotechnology in solving the water problem?
Thank you, Dr. Muhammad, for this opportunity. In fact, I'm happy to be here, especially that I'm seeing a lot of students and young researchers. So I'd like to start by giving some examples of using nanotechnology for water desalination and treatment. As you know, when we're talking about unconventional water resources, we're talking about water desalination, water treatment. And nanotechnology here is here for enhancing these treatment methods. There are some examples. For example, we have adsorption. When we talk about nanoadsorbent, we're talking about materials that have very small size, very high specific surface area, so it has higher capacity, more efficient than the conventional adsorbent. Examples of these are carbon-based materials such as carbon nanotube. We're talking about single wall and multi-wall carbon nanotube, which are very efficient in removal of heavy metals from wastewater. Also, we have some polymeric adsorbents such as dendrimers, and these are very efficient in removal of organics and also heavy metals. Also, there are the metal and metal oxides nanoparticles that, especially if they are super paramagnetic, they are very efficient in the absorption in general. Other techniques that can have nanotechnology is the membrane technology. As Dr. Muhammad showed us before, we can enhance the performance of the membranes by using nanomaterials. We can have either mixed matrix membranes, or we can have the coating on the membrane using nanoparticles. And this nanoparticle would change the performance of the membrane by changing either the surface chemistry of the membranes or by changing the structure by changing the porosity, the pore size, the pore. Also, it can work as enhancing the mechanical and thermal properties such as the carbon nanotube, the nanoclay. They can also work as antibacterial agents, so that would decrease the biofouling problem. So we'll have membranes that have, it would have longer shelf life. It will, less cleaning will be required if we use these anti-biofouling materials. Also, the nanotechnology can be used as a photocatalyst. Nanoparticles as nanophotocatalysts are very efficient in degradation of lots of organic materials in the wastewater. And also they can work as disinfectants, such as the nanosilver, which is known to break down and kill the viruses in the water polluted with virus. So we have a lot of material that can be used in water treatment. And if we can scale up this material, we'll end up with water purifiers that are smaller in size, more efficient, and more affordable. However, this is something that it's not straightforward. We need to think about it, because I think it's important to do risk assessment for this kind of technology. We need to study the life cycle of nanoparticle from synthesis to the product. We need to know if any release from, for example, the membranes, is there any nanoparticle released to the water? And this, because we're talking about very small size, so it could enter the biological cell, the human cell, the plant cell. So this is something that needs to be assessed and studied in deep. And so if we look at the literature, we can see that there are some studies with different results. Some would say that it's totally safe, others say it's toxic. So I think that we need some standards to work on and make sure that, okay, we are providing good solution for water treatment, but we need to make sure that it's safe to our environment and to human. So that's.
Thank you so much. It was interesting, the diversity of the talks of the speakers. So I will just open the floor for questions, if there is any. Well, when there is no question, that means one of two things. Either you understood everything, which I doubt, or you didn't understand anything. I hope it's not the latter, though. Dr. Abir.
Thank you, Dr. Muhammad. Thank you, all of you, for your idea. I was wondering when I see that the first patent appeared in '63, and I'm wondering when in the Arab world we start working the membrane, right? And how long would it take us really in the Arab world, or hopefully in Jordan, to really scale up the membrane and work with our own membrane? The research that Dr. Rand listed is very, very important. And I think we have a number of publications and a number of projects between Jordanian and non-Jordanian with the membrane synthesis, scaling up, let's say training graduate students. But when do you really think, so this is a question for all of you, we can really start using the membrane, not as a project, as a really stats in Jordan or around? Thank you.
Okay, I might be able to answer the first one. The problem with membrane manufacturing, it's easy, it's not easy as well to develop a small sheet of the membrane to test it. That's what researchers usually do. But to scale up, there is a lot of complicated processes involved. And there is a sophisticated know-how. No wonder why there is only like few companies who manufacture membranes in the world. And that sophisticated know-how, it's kept into those companies. And this is sophisticated know-how, it's about scaling up. I've been involved myself in scaling up a project for my earlier patents. And I spent 4 to 5 years to be successful after 400 patches in scaling up a process. But it takes that long. I think nowadays there is a tendency in Kingdom of Saudi Arabia to manufacture the membranes. But actually they get the license from Dow Chemicals to open a factory in Saudi Arabia to start producing the RO membranes, specifically the thin film composite membrane. For any researcher, the challenge, and this is the other challenge, is not only about time, it's about money too, it's about funding. Because this is called deep tech. You know, like technology has 3 categories: low tech, high tech, and deep tech. Deep tech requires a lot of time, a lot of money, because you need an investor who's willing to invest in buying casting machine, which costs around $1 million, and a researcher, he will pay him his salary and the team for 5-10 years, and they might not be successful too, you know, so the risk is high with the deep technologies. That's the challenge. So it's not limited to Arab countries, to be honest, it's everywhere in the world. I hope I answered your question, and for your second question, I will leave the floor to our speakers to answer.
As Dr. Beshad said, the funding is the big problem. And in Saudi Arabia, last week I met one of the companies, one Jordanian guy working with them. I think they have agreement with one Japanese company, Toray, and they start trying to manufacture that in Saudi Arabia. I think it could be the start. But in Jordan, let me ask, still we don't have any vision what we have to do in dissemination. We were talking about Red Dead, we are talking about national carrier, we were talking about small scale in Aqaba. We have, treating the saline water, that's the groundwater. We are not talking about that. Then which investment we can do? Who's then the funding agent will come and do big business and no certainty that this is the future and to which scale. But in the Gulf, yes, I think it should be the start. As Dr. Beshad said also, we have to own the knowledge also. I think doing this by linking the researchers with the Arab researcher, with the needs, I'm talking about utilities, and the funding agents. I think in Jordan, many things we can do because we have the money. You may surprise. Our money in the social fund, our social fund, it's our money, 10 billion. We can invest in that. And it was my proposal when I was in the ministry to invest in DC, not to buy real estate and do it in the future. Because of one thing, water and the water utility is a supermarket selling one good, and it's monopoly. So the water you produce will be sold of good price. So I think we have the money, but we don't have the attention and the real strategy on developing really the unconventional water resources. Let me go out a little bit from the dissemination, go back for the reuse. None of our dissemination, wastewater treatment plant is tertiary. Then how we can produce our food? And then we are using more than 60% of our water resources in agriculture. Now if we'll go more for tourism, for industrial, for keeping the water, groundwater from pollution, we are over abstracting. Then we need to go and upgrade all our wastewater treatment plant. And I can't see this in our water strategy in Jordan. Some people, they say, no, we need new water resources. Funds is needed. Private sector Jordanian could do, banks can do, other engineering fund can do, our social fund can do, which is owned by everybody in this, except our guests from foreign countries. Everybody has a share. So the return will come for everybody. And we have good researchers. We have in the 3, I don't know how many, but I know 4 of them, they are good researchers. And we have many Jordanian from here and outside. And I think it to go for more than pan-Arab. That's why we in the NGOs in the Arab region call for joint forces within all the researchers in the Arab country. We had one, we were together in the MENA research centers, but unfortunately it was a fail. I think by doing this, we'll go in the right track. Thank you.
Thanks for your honesty. I'll have one more question there.
I said that good evening. Also, and thank you for this opportunity to have this kind of event here in Jordan. My name is Rami Fudayli. I'm usually working in the water treatment before. So the thing that I faced here, using actually the RO systems in houses, we face some problems. So the question is, so what is the capacity necessary to reduce the preparations of potential impurities in the water to make it suitable to be drank directly? So is there any plans to do this, and is there any plans that to save the normal people from buying these kind of RO systems and fit it on them houses? So is it possible to make this water to be drink directly? Thank you.
Chairman, give the floor to
Well, I did not really hear you well.
Yeah.
Because the microphone
So the question is, what is the capacity necessary is it actually to reduce the potential that
But listen, just don't move the mic.
Okay. So what is the capacity necessary to reduce the preparation of potential impurities of the water to make that water to be drink directly? And sir, that actually the measurement for that water, it is over the 300 ppm by the time that we're measuring it.
You come from industry? Yes. That's why you are asking for 300 ppm. The limit is above that. And we are drinking, I think, 500 to 600. But I can tell you, you go and drink now from the tap. You don't need RO. I used to be the Secretary General of the Ministry. I'm not now in office to defend the Ministry of Water. And before a few minutes, I give some criticizing the strategy of the government in general. You go and drink from the tap, you don't need more capacity. You don't need. If the network is okay, and if your top tank is clean, so there is no problem. We used to, in the Ministry of Water, we used to have a policy. If there is any suspicion in any resource, We have to stop it directly and prove it is safe. This is number one. All the standards and parameters, chemical, biological, physical standards are according to Jordanian standard, which is more tough than some in progress country and more tough than the WHO guidelines. But why people are using this? Actually, after one of the breakdown in Jordan in 1998, when there was contamination, so people start going there. And by the way, I have one in my house. I bought it at that time when the breakdown was there. But it's not healthy to have 0 TSM water. It's not healthy unless you eat more salts from other resources. Then you have a blood pressure. No, we can't. In Jordan, we can't. Why? Because you don't have that big resources. You have a limit from the WHO. You have a limit in your Jordanian standards. I don't think it is luxury to go for 200. Second, it means you have to stop half of your available resources. But what we do blend that little saline water with more saline water. Now in DC we have it 250 near about. But by the future, since it is fossil water, it will increase. When we started taking water from Al-Hallabat and from Azraq was 250, now it's 400. There is a drop down of 0.9 meter every 1 or 2 years. You are not having Guta River in Sweden, which I have seen, or Thames water. You are the second poor country in the world. You have to use all water resources once it is potable, according to standards. I don't recommend to go for 200 as expert in water, unless it will satisfy your industry or your company. Thank you.
Thank you. Thank you. We'll have one last question.
Thank you. It was an honor to meet with you. I would like to ask, what would be our role as students, undergraduate students, to contribute to build sustainable communities? Would awareness be enough?
Can you just repeat the question, please?
Yes, sure. What would be our role as students, undergraduate students specifically, to contribute to build sustainable communities? Would awareness be enough?
Awareness is one of the most important part, yes. Like, I just want to go back to the question that was raised with the necessity to go down less than 300 ppm, and the answer, it is usually used by the industry to encourage people to have their business successful, and to encourage people to buy such units, which is fine. But at the same time, it is not necessarily the best way to manage the water resources. But I can give also an example from wastewater management, because what Jordan is doing now is using not more than 90% of the treated wastewater for irrigation, and this is sometimes may raise some questions within the community, and here it comes the role of awareness, because the people have to be exposed or to know what exactly going on with the wastewater, how we are treating it to a high level that meets standards. Many of the people, many of the residents or most of the community, they really do not know, except few bad examples from malfunctioning wastewater treatment plants, for example, and they take it as an example and generalize it for the whole community, which is not true. So awareness is very important, but I would also put other points that is considered as enabling environment to come up with scale up, which is I consider it the regulations, the regulatory framework for encouraging such investments to go on with, or to move from science, research outcomes, and then bring it to the market. So I can just put it in two frames. The first one is maybe with commercialization, we need to go for industries and convince them that such technology can be adopted from their size within their labs, going with them into putting it into the market. And the second part is related to the existing regulations within the country. The regulations has to encourage the implementation of such technologies by, for example, putting some incentives, like reducing the tax on such new technology. Maybe some other type of incentives has to be into has to come out, but this has to be done within the frame, an obvious regulatory framework that has to be put by the government. On the other side, we can look also for the government who can invest in some programs that encourage the scale-up. So maybe the government of Jordan decides that we can take some fund from the social fund and invest on scaling up of some topics that we think it is critical. And of course, we do not have question that water is not critical now for Jordan. It is very critical. And then we reserve this fund for programs that invest in scaling up the research outcomes into a big scale or scalable technology. But as a postgraduate student, awareness is part of in your hands, because at the end this what will put pressure on the government and move or come up with a social acceptance for a certain technology to be seen in the market.
Yes. Thank you so much.
Thank you, Dr. Maha. Engineer?
Just a small comment. Your role is, you are the future, by the way. And after some time, we'll be the past. Myself. Well, I remember before 15 years, there were something called water clubs in schools. Now it's no more. نعم دكتور. يعني country which has the, by the way, 2 governments were designed in Jordan because of water contamination. But none of the governments was kicked due to bad economic performance. This is, in Jordan, this is the most important crucial issue. We don't have money and we don't have money. We don't have water, we don't have power. And you have to subsidize everything. What I am surprising, in Jordan German University, there was water resources program. Now it is finished. Yani, really, I don't know how things are going on. I believe that there should be more engagement for non-governmental organization, for civil society organization, for women organization. In Aqua, we did 2 things targeting women. The role of women in integrated water resource management, and we did it with UNESCO Cairo, and the other one with our project with EMI. We are targeting the role of gender in the wastewater treatment. Many of the women in the Jordan Valley, they are managing their lands, and they are using wastewater, treated wastewater. I think you need a policy at the top level to support the NGOs local. I'm not talking about regional. I'm not looking for money here. To support them and give them the guide and try to give them not only the public awareness, the principle of water demand management. Do you know which category is consuming more water in the houses? It's the maids, Filipinian maids in Jordan. Or nowadays there's Ethiopians. They are consuming the most water. We have to target those people. Before 20 years, we used to make, through media in Sri Lankan language, if you remember, pamphlets, teach the student. You may find this in the small, good nursery, which we pay a lot of money for. But in universities, I think we have much to do. I am asking from this podium, His Excellency, allow me to go back and ask that we have to bring the water and environment issue in the universities as complete subject. I'm sorry to say that we are going back in this. It seems that there is no good vision for the governments towards the water sector. They need a lot of support. Thank you.
Thank you. Okay, one last question.
Sorry. Hi, everybody. I have a non-technical question to Engineer Khushman.
Sorry.
Okay, that's okay. I have a non-technical question. It looks like a personal one, but I think it might be of interest for some of the audience as well. At my house, I have a softener, but we don't drink from the tap, and we rely on rainwater. We collect it. Which source is healthier, the rainwater or the softener?
I will ask you personally, because I have the three things you said about in my house. I have roof tank, which is about 120 cubic meter. I have a softener, and I have an arrow. And I have a dripping system. And all the devices in my house are water-saving devices.
Which one do you use? Which one do you rely on?
I rely on all. I make softener just to protect my washing machines, my heating system. But it's not a drinker. But once it goes through the RO, it will be drinkable. Is it okay?
Yeah.
You have an RO?
Yes.
Khalas, you are safe. For the rainwater, sometimes some friends like you, when I was in the ministry, they were asking me, please check in your laboratory, is it safe or not? Most of the time it's safe, and sometimes it's not safe. First of all, collecting the wastewater, you have to make flushing from the first rain, second rain, third rain. Again, you have to clean your reservoir every year. Every year. Myself, I use it in cleaning the terraces and in irrigating my small garden. And I'm satisfied with that. I have a big house for me and my family, but I'm paying a very reasonable bill. Very, very reasonable bill. So use the three of them.
Okay, thank you very much.
All right, thank you. We come to close the session, and actually we will have a lunch break now, if I'm not mistaken, so we can continue questioning the speakers. But before you leave, please, two of our speakers weren't yesterday with us, so we didn't honor them, and I'll ask Professor Naif to join me to honor the speakers. I would ask you to join me for a round of applause for Dr. Maha Halalshe. And my colleague, Dr. Rand Abu Zreq. And here, the session comes to close. Thank you for being with us and this diverse talk. Thank you. Thank you so much for the speakers. Yes, we will take a picture.
Yes. No charge.
Dr. Mahmoud, can you start, Mahmoud? Or?
Yes.
Okay. Good afternoon, everybody. My name is Abdulwahab Hassan. I am assistant professor in physics at Fayoum University. This is the first session after lunch break. In the sessions, actually, we have 3 speakers. The first speaker is Professor Ola Eriksson. He received his PhD degree from Uppsala University, and since 2002, he is professor in physics at Uppsala University. His research interest is the theory of material science, and he published almost 800 papers in high impact factor. Please let me to welcome to Professor to start his presentation, please. Please, can you ask?
Assalamu alaikum. So I'm obviously very happy to be here and to share with you things we do in trying to understand materials from a theoretical point of view. So I'll tell you a little bit about the things we do and some of our successes, but also at the very end of my talk I'll tell you something where we absolutely, completely fail. So before starting with the scientific aspect, this is my hometown. In the month of February or so, that's the cathedral in downtown Uppsala. It is 118 meters tall, and in the winter shroud it looks like this. So the results that I will show you is, I think I basically have generated 0 of these results myself. I'm the guy that presents them to you and tell the story. And so this is the list of collaborators I have on this project. The results you will now see and others. So the overview of my talk is, I'll tell you a little bit about what the density functional theory means, what it does for us. And then I'll go into applications, structural properties, magnetic properties, correlated electron systems, and the remaining problem. So density functional theory in a nutshell. So I am, as many of you, try to understand materials from a quantum mechanical viewpoint. And so that means we have to identify the Schrödinger equation. What we all do is we make the Born-Oppenheimer approximation. We consider the nuclei as fixed. And the only thing that moves around in the material that contributes to the chemical bonding, its superconductivity, its structural properties, everything is that of the electrons. So the Schrödinger equation can be written down. It's at the top of the top equation that you see, and it describes interaction, the kinetic energy, and the interaction between the electrons and the electrons with the fixed nuclei. So the first term is the kinetic energy of the electron. Right there. The second one is the Coulombic repulsion between electrons, and the third one is the attraction between the electrons and nuclei. So opposite charges repel and equal charges attract. The first and the third are easy to solve. That's not the problem. The problem is the guy in the middle. And the problem is not that we don't know what that interaction is. We know it perfectly well. I've drawn a cartoon of it here. So all straight lines are now the Coulomb interaction, repulsive Coulomb interaction between electron pairs, but in a solid, there are of the order of Avogadro's number of electrons that one has to keep track of. And the very fact that there are so many of them makes it impossible to solve this straight offhand for a material of interest for an experimental investigation. So we have to come to approximations and take some shortcuts. So even though we know precisely all terms in Hamiltonian, we have no solution for it, but in approximate ways we can find solutions. And one way to do this is density functional theory, and that is a mean field theory. So it means that each and every electron in the material interacts with the mean field generated by all other electrons. So if you take now a red electron, for instance, and allow it to work and interact in the mean field of all other red and blue electrons, it will live in an environment that is now a mixture of red and blue, and the mixture of red and blue becomes the color of purple. So here's my didactic way to explain density functional theory for you. So this red guy now is a singular object. I only have to worry about this one electron and the mean field that it lives in. And that purple mean field, that's something that's generated by all other electrons. It is, of course, not at all an obvious thing that this is a terribly good thing to do, but Walter Kohn could show with mathematical precision that this description is equivalent to solving the full many-body problem, at least in principle. In practice, we have to make more approximations, but the mapping of the full interacting system onto this system is an exact one. The practical question becomes, what is the nuance of purple in this picture? What is the best mean field description that I should use in order to describe things as accurately as possible? And so there are, as of today, of the order of 300 or so different nuances of purple in this view graph. There are some people that spend their entire academic life in trying to find the exact nuance of purple in this view graph. And what does that mean? It means that the one electron equation that we can now solve for this one electron problem in a mean field, I just have to find the right effective potential for that electron. So I have now replaced the full many-body problem with a single electron problem. Now it's only one kinetic operator operating on one electron. This guy there. It lives in a mean field effective potential here. The purple of neons there. It operates in a wave functions and give back an energy in a wave function again. So the parameterization of the effective potential is something that is a key parameter of density functional theory. And so when you read papers about density functional theory, you'll see things like the local spin density approximation, the generalized gradient approximation, the LDA plus U, all different nuances of purple in this graph here. So this is a cell-consistent equation. I won't go into that, but at the end of the day, you can calculate all kinds of properties from this now one electron problem in this mean field. So for instance, the total energy, magnetic moments, lattice properties, whatever you want. So for solids, there's another complication that enters in solving this equation, and that's something that came out of Felix Bloch's thesis, 1928, and he identified that the form of the wave function has to be of a particular kind. It has to have a plane wave part, and I'll point to it in a second, and it has to then have a part that is periodic with the same periodicity as the underlying crystal lattice. So that first part is the plane wave part, and the second one, U of R, has the periodicity of the lattice. And because it has a prefactor, it has a K index in the exponent, we typically label all the calculated properties with this K index. This is now a index, a vector of reciprocal space. We refer to this as a crystal momentum. It is not exactly the same as a classical momentum that you think of for a classical particle, but for free electrons it really is. But in general it is close, but not exactly the same.
So solving now the Korn-Sham equation, or this one electron equation that is so central for density functional theory, I can get eigenvalues E from the second equation. And I get wave functions psi, and I have a full solution to my quantum mechanical problem. And this is what then allows me and others to calculate energy bands, and I'll come to that in a second. You recognize this when you read textbooks like Ashcroft and Merman. Here's an example of the energy band structure for BCC iron. This is now a calculation that is done in a spin polarized mode. You allow for exchange interactions to come into play. It is a natural component of that purple medium. It is not a mysterious aspect of that at all. And then you see now that for a material like iron, bulk iron, BCC, there is a disproportion between spin-up electron states and spin-down electron states. There are more spin-up than spin-down. You see that because all electron states that are below this dashed line, the Fermi level, are occupied, and all the states that are above are unoccupied. And if I now look at this band structure for spin-up projection and for spin-down projection, I can see that I have more spin-up than spin-down. You can easily identify that, for instance, by looking at the band structure at the gamma point. Here, for spin-up, both these guys are below the Fermi level, but in the spin-down channel, only the lowest one is below the Fermi level being occupied, and the other one is unoccupied. If I now sum up all electron states in the spin-up from minus infinity to this Fermi level, and I do the same for spin-down, and I multiply that with the electron G factor that turns occupations into a magnetic moment, I get the value of 2.2 from theory, which agrees almost perfectly with experimental measurements. I'm going to come back to that, the experimental measurements, but one of the things that I wanted to share with you was that of structural properties. This is a theory that is fantastic in describing structural properties. And the first example I wanted to give is that of Hans Skriver, who published this paper quite some time ago. It is published 1985. Many of you were not born 1985. What Hans Skriver did is he asked himself the following question: can I, with density functional theory, reproduce the observed crystal structures of elements? And he went through the entire periodic table and compared the structural stability between different structures for all elements. And he basically reproduced everything that was known and is still known up today about the crystal's structure stability. The only element that he really failed for, where he tried and failed, was that of gold. So he got gold to be body-centered cubic. It is face-centered cubic, as we know. So that's the only system where he failed. Now, since then, our methods have been improved a little bit. We can do these things now more accurately, and we can also, with ease, reproduce the FCC crystal structure of gold. So structures typically come out with fantastic precision from these calculations. Another thing to bear in mind is lattice vibrations, phonons. Many softwares are now around when any one of you could pick this up and learn how to use it. You can calculate structure properties, you can calculate magnetic properties, you can also calculate lattice dynamics, phonon frequencies, phonon dispersions. In practice, that is done often by making a supercell, and then you calculate the force that you induce in all the atoms by displacing one atom, say at the origin here. The force constant matrix evolves in your supercell, and from there you make a Fourier transform to get the dynamical matrix that they diagonalize, and you get eigenvalues. So here's an example of what that looks like. These are now phonons of yttrium, zirconium, technetium, and ruthenium, the ones that have hexagonal close-packed structure. And over on the right-hand side, you have rhodium, you have palladium, you have silver. These are now face-centered cubic crystals. You see the theory as solid lines, and you see the dots as measured values. And so the precision is actually not bad. You can reproduce quite a bit of the, and this is a typical level of agreement. I have a little bit of a story on dynamically unstable things, but I think I'll skip that actually. And now we go back into the magnetic properties. So I told you that for BCC iron, all I have to do is sum up electrons that are occupied for the spin-up channel and the spin-down channel. I get the difference occupation number, and then I multiply with the G factor of 2, and then I get the magnetic moment. You can do this for any element that you want and any compound. So here I compare for you now calculated and measured values of some typical systems that we picked up. So you see so here I show on the x-axis the experimental moments, on the y-axis, let me go down a little bit, you see the theoretical moments. And so if everything is in perfect agreement, all the points should be on this straight line that is here. And you see it's pretty close to being all points being on a straight line. So this is now the calculated and measured moment of face-centered cubic nickel. We picked Fe2P because it has good magnetocaloric properties. It has 2 sites, a tetrahedral and octahedral site. You see these moments here and here. Here is hexagonal close-packed cobalt, BCC iron, and way up in the corner there it's gadolinium. So this is more or less a routine agreement between theory and experiment. The story gets, of course, more interesting in the cases when points deviate. So when points are lying here or here, we get more excited than when they lie on the line. Another example that I always like to show is also calculated spin moments of the iron cobalt alloys that can be stabilized in BCC, FCC, and HCP crystal structure. These alloys between iron and cobalt, they are stable really in the body center cubic structure. You can stabilize them in a metastable structure also as thin films or as inclusions into an FCC matrix like copper. But what you see now here on this graph are the measured magnetic moments of these alloys in the BCC crystal structure. That's the purple circles there. And so you start from 2.2, you reach the top of that curve, and you come to what is called the Slater-Pauling maximum, and then you, after this top, you go down again. The calculations are cutting through these measured points, every single measured point. That's the solid line here. So again, theory and experiment are in excellent agreement with one another. This is an interesting system for practical reasons also. There's no element, compound, alloy known to mankind that at room temperature has a larger saturation field than this point up here. So the Slater-Pauling maximum has withstood challenges to be overcome. Other systems, we have tried to identify other materials, other compounds, but we have failed. It is simply a very, very strong magnet in terms of saturation field. It's a record has stayed for I think 80 or 85 years. It's really is an interesting system. But you also see that this is a system that has other interesting aspects to it, and one of them is that of the face-centered cubic crystal structure when it can be stabilized as thin films, because there, depending on alloy concentration or depending on structure properties, you have very sensitive magnetic properties, and so I'll point to it. So this line right here. So you go from non-magnetic to strongly magnetic by changing the concentration a little bit, you can go from non-magnetic to magnetic by changing the structure a little bit. At least that's my speculation, because if I start from FCC and going to BCC, you get a huge change in the magnetic moment. Good. So that's a little bit now of the story of the size of the magnetic moment, and the examples I gave you were that of ferromagnetic materials, but of course not all materials are ferromagnetic. There are many that are antiferromagnetic or non-collinear and spin spirals. And so the question we and others have asked ourselves is if that's also something that is available to us and from these kind of calculations. And so we have had the excellent member of our research group, Jaroslav Pashnin. You see his face up in the upper right corner. He helped us to make such calculations available. The theory behind this was published, that's the reference down at the lower right-hand corner, by Liechtenstein and Katznelson, that started in 1987. And our work came in much later, 2015, is the Fisher B article there. And the strength of the interaction and also the sign of the interaction, whether it's ferromagnetic or antiferromagnetic, we are all accustomed to describe that in terms of an Heisenberg Hamiltonian. And so the strength of the interaction between two magnetic moments on site I and site J provides the exchange interaction. That's also something that is clearly available to us from density functional theory, from electronic structure calculations, and it's a rather simple, or at least straightforward, equation to solve in order to get that interaction. It has four components to it, actually two really. One is the local exchange interaction delta. That's simply the splitting between spin up and spin down states. And then there's another guy, Gij, and that's the Green's function of the electronic Hamiltonian. The Green's function here is the most complicated part of this equation. But it's basically the inverse of the electronic Hamiltonian. So I've written down the definition of it down to the right here. So once you have the Green's function and once you have the exchange splitting, you have in principle a way to evaluate and calculate Heisenberg exchange interaction parameters. So let's see how that looks like. Here I've written down the Heisenberg Hamiltonian. This is now something that describes the spin excitation spectrum, the spin energetics of a system, of a material. The sum over I and j here goes over all pairs of the whole crystal, and you don't know how many pairs you should take into account before you've actually done the calculation. If you look at the lower right-hand part of this figure, I'm showing you our calculations of exchange interaction parameters for FCC nickel, phase center cubic nickel, and you see that the nearest neighbor interaction is dominant. But interactions that go further out are also needed, and so it is not a good idea to truncate this interaction only after nearest neighbor interactions. You have to go out all the way out to, I think here we have 1, 2, 3, 4, 5, 6, 7 nearest neighbors before this really looks like it's deviating. Now you're asking yourself the question, well, how good is this really then? What can you do with it? Can you explain and reproduce things? And so here all interactions for FCC nickel were positive, and with our definition of a Hamiltonian with a negative sign in front of it, that means that for a ferromagnetic alignment you get the lowest energy, and that's in agreement with the ferromagnetic state of nickel. We get the same result for BCC iron, and for BCC iron we also calculated other properties that you get from a statistical treatment of this Hamiltonian, for instance the temperature dependence of the magnetism. So this graph here shows from this Hamiltonian with calculated values of S's and calculated values of J's, all properties here calculated, what the resulting temperature dependence of the magnetism. So that's shown here, M over M0. And you see that this curve then dies out at around 1000 Kelvin, which is in good agreement with the measured Curie temperature of BCC iron. That's also something that we now are accustomed to reproducing with, say, an error seldom exceeding 10%. Another example that I have here is the spin wave dispersion spectrum of, well, I could have picked any, many compounds or elements, but I picked gadolinium. Gadolinium is a rare earth element. Here I'm showing the excitation energy to create spin waves, collective excitations in this system. The measured values are given by red dots, and our calculated values of the spin wave excitation spectrum is given by the black curve in the background. And so this is again data that relies critically on the value of the exchange parameters. If the exchange parameters would have been drastically different, this curve would have been drastically different. But you see that the experiment and theoretical values are in rather good agreement with one another. We miss a little bit some places. There, for instance, and also here up here. But overall, the agreement is pretty good. So we can calculate a lot of things, but let me now come to things where the situation is a little bit more complicated, that of the correlated electron systems. I'll tell you what we mean by that. So the quality of these calculations, they rely basically on the quality of that purple medium that I drew on my second or third slide. So if that medium is not the right one, there's no chance to do it. And there's some system where we simply know that you cannot, with a one electron picture, describe the electronic structure. Some systems that are simply refused to be described in that way. Nickel oxide is an example of that. And the reason is the following. Suppose I have now atomic nuclei positioned out in a lattice as such. And suppose one electron now is coming through this lattice. It's spinning around one of these nuclei. It is following quantum mechanical laws of motion. It jumps around because the kinetic energy is lowered when it jumps around, and it's situated on this atom for a while. Imagine now that it stays here for a little bit. As that has happened, another electron comes, and it comes from up here, jumps over here, and jumps onto the same site. And all of a sudden I have two electrons with negative charge that are repelling each other. And if they are now confined to be forced because of the wave function of this atomic site where I am, if they're now confined and forced to be close to one another, then I cannot replace the true Hamiltonian, not with any realistic parameterization and a realistic purple medium, so I have to do something else. And the something else that we then would like to do is to add a Coulomb U, and that's the second term on the right-hand side of this equation, the one down there. That equation simply says that there's a penalty for this system if two electrons are on the same site. This is referred to as the Hubbard Hamiltonian. He wrote it down for the first time, and we still have no good way to find a solution for this Hamiltonian straight off for a realistic case with many orbitals per atomic site. So we have to again try and figure out something clever about it. And one way to do that is to adopt dynamical mean field theory. And dynamical mean field theory says, okay, I know I have two electrons on the same site here, but I don't care where they came from. The only thing I care about is that they are sometimes on the same site and sometimes they're off the same site, and they jump off and on. So I can replace this true system with an auxiliary system. That's the fluffy cloud to the right. And the only thing that auxiliary system allows is for electrons to jump on and off the same site. And if they're both on the same site, I have a penalty of that Hubbard value U. And that could be of the order of 2, 3, 4, 5, 6, up to 10 electron volts. So, so how this works, we made implementation in one of our electronic structure codes, but how this works can be maybe best illustrated by one of the mixed valent materials that we were interested in, the ytterbium, indium, copper 4. So here I am showing on the right-hand side the experimental photoemission spectrum. The photoemission spectrum simply shoots in photons of certain energy and kicks out electrons, and you analyze the kinetic energy of electrons as they leave the sample. That gives you a feeling for the band dispersion, what the binding energy is of those electrons. So you see on the right-hand side, you should focus now on the spectrum that is marked B. That is the measured valence band spectrum of ytterbium F states of this compound. So that's what any good theory should aim to reproduce. And density and functional theory gives for that spectrum this result. So one peak and nothing that it looks close to the measurements. But dynamic and mean field theory that I just described to you gives you this spectrum. So basically every single feature you have in the measurement down to the right is reproduced in this spectrum here. The peak positions, the number of peaks, the values between them, everything comes out correct. This is not a terribly expensive calculation to do for us now. This is something that we can do rather straightforwardly. I have some more examples of correlated electron systems. This is the photoemission spectrum of nickel oxide. Measurements are given by the open circles, and theory is given by the full black line. That's the data, the part of the spectrum that is projected down to nickel 3D orbitals, and then the dashed red is that of the of oxygen p states. We had some discussions on oxides this morning. Here is the X-ray absorption spectrum of Fe3O4, magnetite, the first magnetic material that mankind identified. Experiment and theory, again something where dynamic and mean field theory does well. Extramagnetic circular dichroism. That's this guy here. Again, theory and experiment are in good agreement. So now you say, fantastic, you can calculate everything, but not so. So here is, for us, an outstanding problem. And in principle, it should not be. This should be something that is very, very straightforward for us to do, and would be very good to be able to do, and that's to calculate a phase diagram of this form. Any phase diagram of this form. So this is now a phase diagram. I just took one out of many that are available, but many of you experimentalists really work with and look at. So the total energy, it should be available for us for this system, for the aluminum 203, and for whatever I had up there, silicon dioxide. And so I should be able to compare total energies, and I should be able to compare total energies for all these phases and tell you that we can reproduce your phase diagrams. But our functional is not accurate enough. Here is where we fail. And there's no, as far as I know, there's no obvious solution in sight for this one. So I have to humbly bow my head and say that we can't do everything, but we can do some things at least. And so with that, I think I have come to the end of my talk. I have a conclusion that I hoped we could fill in together. I'm going to ask you what my conclusion should be of this talk, and it's a way to check if you were paying attention or not. So thank you for your attention. Shukran.
Thank you very much, Professor Ola, for a nice presentation. And now questions. We need a couple of questions because the time is limited, so we can start with.
Thank you for the presentation. I think it's very interesting that you can calculate and understand how is the band structure and density of states. But my question is, if one wants to understand how is the valence band of a particular compound, how long does it take to have to have a result with the DFT and all the calculation? Like timing in months?
It's a relevant question.
Thank you.
So this is a question. This is an experimental. This is a spectrum that may be of interest to you, right? And so X-ray absorption, X-ray magnetic circle dichroism is something that synchrotron radiation facilities measure. So when you go and see the Sesame synchrotron tomorrow, this is, if it's designed to do this, I don't know, but it's available for synchrotron radiation facility to make these measurements. And so this is these are curves I have waited for 1 year, and I have waited for 1 year not because the calculation took 1 year, but we recruited a student 1 year ago. The student learned the theory behind it, Felix, and he learned how to run the codes, and he learned how to. You have to learn a lot when you're a student, but now this is his result. So I'm very happy. So for him now that he's a full-fledged trained person, if you came with a similar system to him, in 1 month he would give you good data. Yes.
This is X-ray absorption.
This is X-ray absorption, yes.
Yeah, it's with the photon electron spectroscopy. It is
it's the same. My answer
okay.
would be the same, exactly the same, yes.
Okay, thank you.
Any questions?
Yeah.
Abanoub, yeah, you can ask.
Yeah, sorry. A simple question. So your Schrödinger equation did not have any time dependent. It's like this is always ground state, or you get excited states, metastable states.
These are excited states. These are excited states.
Yeah. So metastable also is metastability.
Well, if I now make connection to Ike's talk, to calculate the structural stability of compounds or elements, maybe not hydrogen, but for silicon or for carbon or so, and to get the right structural stability as a function of compression is an easy thing to do. So we can calculate that for carbon you have the graphene structure is lower in energy and the diamond is above at ambient condition, and then as you compress it, they change place. That is something that is reproduced very well in these kind of calculations, and even the barrier in between.
Okay, any more questions? Yeah.
Thank you, first of all, for the talk. You were showing us how to calculate also Heisenberg exchange.
Yes. Another question is,
how hard is it, or how good it is in comparison to also include other types of exchange, for example, Kitaev or Dzerzhinsky-Moria?
Yeah. In a more general form, you can write this equation as a matrix equation with a J. Here is a 3x3 matrix, and that 3x3 matrix would then contain Dzerzhinsky-Moria and symmetric anisotropic exchange, and if that became a Kitaev Hamiltonian, if the parameters were of that kind, it would become a Kitaev Hamiltonian, we can do it. It is maybe a little bit more complicated, but we can do it. I say that with some certainty because there was a prediction, not by us, but by the Budapest group of a system where they calculated the Dzerzhinsky-Moria vector, and they could from that predict the asymmetry and the magnet dispersion relationship in going in plus Q and minus Q, because they are no longer symmetric in that case. And they made a prediction how big the asymmetry should be before experiment confirmed that prediction. So that's a strong thing from theory to do, to predict something, and they did that, and so it was correct.
Thank you.
Okay, last questions. Last lady.
If we'd like to calculate not only exchange parameters but also predict some real ground magnetic state, I mean, not only exchanges, but also directions in the order state of magnetic moments. For some complicated structure where there are a lot of exchange interactions, we have to guess ground states and then compare the energies, or there is some algorithm how to do it. I mean, for non-collinear structures.
Yeah, so it's of course tricky, but basically if I start from a collinear arrangement, say ferromagnetic, and I get J's that are a mixture of ferromagnetic and antiferromagnetic ones, I can then try and estimate what is that non-collinear structure. I can get an idea, but the whole electronic structure machinery that I showed is also designed, I didn't show that in detail, it's also designed to handle non-collinear magnetic configuration. So it is also available. And so there's a very nice book by Jürgen Kübler who describes a lot of this actually. So there's a good textbook that you can also look at. And so it's clearly available also, absolutely.
Okay, we thank the speaker again. Thank you very much. The next speaker is Professor Rodiger. He received his PhD in 2003 from Aachen University, and since 2010 he is Professor of Experimental Physics at Heidelberg University. Professor Rodiger published more than 240 papers in high impact factor journals. And let me to welcome to Professor Rodiger again, please.
So good afternoon, ladies and gentlemen. I'm happy that I can be here, and I particularly thank our today's host. There he is, for the kind invitation. So I'm going to talk about this title, or in a nutshell, so if you heat up this thing here, it will be larger, become larger. And this is called thermal expansion. And what I'm going to tell you, I'm trying to convince you, is that we can learn something from these measurements, from measuring this thermal expansion, on magnetism in the system. So in particular, the title of the talk is How to Study Spin Lattice Coupling and Magnetic Anisotropy and their Relevance for particular kinds of ferromagnets. And this gives the outline of my talk. I will talk about spin lattice coupling, magnetic anisotropy, and introduce the materials. So before I start, I tell you where I'm coming from. This is Heidelberg. This is a rather small town, more or less in the center of Germany. The good thing for me is that it hosts a university, which is the oldest in Germany. It's from 1386, and we have quite a good physics department, and I'm a member of this. So, having said this, work which I will present has not only been done in Heidelberg. There is a collaboration with Dresden guys who made a crystal with Sai Aswatam, and also collaboration with our host, and also the guy which you showed just some minutes ago who provided excellent data from excellent numerical data. So the problem is as following. We are looking at a material, and the material is an organization of atoms into a crystalline structure. So, of course, the lattice plays a role. And the next thing is we have more than the lattice. There are electrons, and electrons have obviously charge. So charge has to be taken into account. Electrons have spin. Spin has to be taken into account. In a crystalline environment, an orbital degree of freedom is related to the electrons, so orbitals are relevant. And the point now is, in our kind of research, that all these degrees of freedom are interacting. So there's an interaction between the lattice, the charges, the magnetism, orbitals, and much more, depending, of course, on the kind of system. So now what can we do as experimentalists? We can apply external fields, like a voltage, an E field, playing with one of these parameters, and then looking what the rest of these properties is doing. Or now coming more to the topic of my talk, for example, we can apply a magnetic field. If we apply a magnetic field, the spin structure can switch. Here I took out the example of an iron, ferromagnetic iron nanowire. You apply a magnetic field and change the magnetization. And this is, of course, what we like to do, changing the properties by external magnetic fields, here magnetism. And another not so common external, external field is strain. This is somehow visualized in this cartoon. Imagine that you have a lattice and press it in one direction, apply uniaxial pressure in order to provide the associated strain, and then the lattice will be compressed. Or the unit cell will be compressed as sketched there in this, for this perovskite structure. And obviously, all the properties which depend on the interaction between the atoms or the electronic properties, the overlap of the wave functions are changed because the distances are changed and the bonding angles are changed. So having said this, it's obviously reasonable to measure associated properties, and the examples which I will present here are examples which are called layered van der Waals materials, namely two examples I will present, chromium iodide and chromium germanium telluride. Van der Waals materials are essentially materials where you have layers of hexagons which are arranged in a rather loose pattern along the third axis, the so-called C-axis, and the interaction along the C-axis is weak, van der Waals interactions, while in plane the interactions are strong covalent bonds. And the associated motif is a hexagon in the layers, or this tripod, which I showed in yellow, is another kind of looking at the structure. So this is a material problem which we are looking at. Having stacked honeycomb lattices where all these sides, these lattice points, which are the grayish points or the edge points of the hexagons, are chromium 3+ ions, so spin 3½ So why, again, looking at strain and magnetism? Here I took a picture which I adapted from a recent review article on such materials, showing that many degrees of freedom play a role, similar as I tried to motivate in the introduction. So we do have different possibilities to realize spins at the lattice. They can have different natures, Heisenberg, X, Y, Ising natures, just telling a little bit about the dimensionality of the associated local spins. We can dope it, for example, by electrochemical doping. We can arrange these things we can twist the layers a little bit, forming moire patterns, and strain, as shown by this hump, also plays a role, obviously. Again, let's look at data also from the literature, why this is so interesting. So this is data showing magnetic properties of a monolayer of chromium iodide. This was a paper already published 5 years ago, quite influential. You see on the left-hand side the so-called Kerr signal, which is proportional to the magnetization of this material as a function of external magnetic field, and you see it looks like a ferromagnet. So there's a spontaneous magnetic moment at low temperatures, and if you look at the right-hand side plot, you can see that the magnetization of the spontaneous moment decreases with temperature. It vanishes at around 45 Kelvin, so this is a ferromagnet below 45 Kelvin. And the famous, or the thing to note is this is in a monolayer of this material. So we have a material which is ferromagnetic down to the monolayer. Why I emphasize this? If you, for example, look at a theorem, Merman-Wagner theorem, which is usually cited in this field, It tells in 1 or 2 dimensional system, continuous symmetry cannot be broken spontaneously at any finite temperature. Now we see that the symmetry is broken. With other words, this is not a spontaneous symmetry which is broken. Now this brings me again to the title of my talk. If this is not a spontaneous symmetry, there must be anisotropy relevant. So it's important to investigate magnetic anisotropy, and of course strain is also here on the slide. So this is what I'm going to show. Now let's look at data. We didn't investigate monolayers. We investigated bulk crystals, bulk single crystals provided by Mahmoud. And you see on the left-hand side, you see a magnetization curve versus temperature. And as you can see, Tc pops up at around 61 Kelvin. So this is a ferromagnet at a slightly higher ordering temperature, but essentially also a ferromagnet. So, and this is what we studied. And the reason is seen on the right-hand side. This is data which Jaroslav Kwashnin published already earlier on, not with us. The reason is there's ferromagnetic interaction between the layers, providing bulk ferromagnets. On the other hand, you see a small feature in the magnetization curve, which shows antiferromagnetism at around 50 Kelvin, telling us at the surface the stacking of the layer is a little bit different, so that the interlayer interactions are antiferromagnetic. About this transition, I'm not going to talk. So now, how to measure the response of the lattice? And I said thermal expansion is a quantity which I would like to concentrate on here in this talk. As I said, this is the length change of the lattice as a function of temperature, or as shown on the right-hand side, also as a function of magnetic field B. So the length can change if you heat it up or if you apply a magnetic field. And the respective thermodynamic response function are the thermal expansion coefficient, this alpha. This tells us, I take the series stick. So this tells us that the length changes if you change the temperature, thermal expansion. Or the length changes, dl, if you change the magnetic field, magnetic restriction. And why this is interesting? If you apply Maxwell relation, thermal expansion is proportional to the pressure derivative of entropy, ds over dp. S is entropy, p is pressure along a given direction. So what does it measure? It measures, we press along a given direction, and we measure how the entropy, which tells us about the degree of order of the system, is changing. And the same with magnetic restriction lambda. It tells us how the magnetization changes if we press in a given direction. So the last equation, which is important for my talk, is a so-called Ehrenfest relation, telling us if we measure alpha, thermal expansion, and the heat capacity Cp, then it tells us about the pressure dependence of the ordering phenomenon, or the pressure dependence of J, the magnetic couplings. Okay. The point here is we have to measure very precisely in order to draw conclusions. And the position which we need and which we can achieve is around 0.1 angstrom. So if we measure something of this size, we measure length changes of a tenth of an angstrom, so hundredths of a nanometer. And this is a challenge, of course. How do we do this? We use so-called capacitance dilatometry, where we put a sample which is in the middle of this. I didn't make a red circle here. In the middle of the cell in the scheme, and on the left-hand side of the picture, this is a sample we put into a piston, and we translate via the piston the length changes into the changes of the distance of a capacitor. So the length changes and the capacitance changes of the system, and capacitances can be extremely well measured, and this is what we are going to do. Unfortunately, life in layered materials is a little bit problematic. So the samples are not as nice as seen here on this picture on the left-hand side, but they are as ugly as seen on the right-hand side. So these are millimeter-sized samples which have a thickness of 0.06 millimeter. And putting this into such a dilatometer under a finite pressure is, of course, an issue. Okay, people can do this, and one of the people who did it sits in the auditorium, has a poster today or yesterday, and this is the result. This is the thermal expansion coefficient of chromium iodide measured for 2 different directions as indicated by the cartoon on the right-hand side. And as you can see, there's an anomaly, and the anomaly has a different sign telling us that if we apply pressure along the black direction, which is the z-axis, Tc is going up, and if we measure along the red direction, which is in plane, Tc is going down. And as I said, we have to compare length changes and heat capacity. So we took heat capacity data here from the literature. So in order to compare it, we have to separate the background, which is indicated by the dashed lines. If you do this, you get this one here. Left-hand side, thermal expansion along C, B, and specific heat scale to each other. And the scaling gives you the pressure dependence, and this is nearly 2 Kelvin along the C-axis and nearly half a Kelvin along the A-axis. So this is not very, let's say, it's not great. But this is the result, and this result we can compare with theory, and we did. I will come to this later. Now, second example, and of course I took also an example where we see a little bit more. This is chromium germanium telluride. This is here the length changes, so the thermal expansion, not the derivative alpha, because here we see much more. And we see also in particular, we see, I try this now. Oh, it doesn't work. Come to my stick. We see in particular an anomaly here. This is Tc. There is something happening here. But there's a large regime here at higher temperatures telling us that in addition to long-range magnetic order, there's something above, and this is short-range magnetic order. And this extends up to 200 Kelvin. At least the response of the lattice to short-range magnetic order extends up to 200 Kelvin. So again, we look at the derivative, left-hand side alpha, right-hand side specific heat, the same as before, so I can skip this and just show you data again. Comparison of specific heat and alpha, now scaled for a second-order phase transition, so we need to scale it versus alpha T. And now we get some results, 25 Kelvin for pressure along the C-axis per gigapascal and minus 16 for pressure in plane. This is already something. So we learn if we apply pressure in plane, Tc is going down. This is not what we want to have, but if you now think about the monolayer, you grow it on a substrate. You can apply negative pressure by this. You can apply strain in order to tune Tc up to high temperatures. And this is now why this data are important. So why do we need to know this? The third point is we need high temperature applications, and we learn how to tune Tc. But number one is probably, for me, even more interesting. We can identify different mechanisms. And for chromium iodide, with the help of Yaroslav Kvashnin, we managed to say that the in-plane interactions are driving the long-range magnetic order, which at least for me, coming from the field of quantum magnets, is a little bit surprising. And we can test, of course, predictions of dJ over dP for uniaxial pressure. Okay, so this is the lattice. But now what about magnetic anisotropy? Why do we need it? We need to investigate why the system orders at all. Or with other words, so here I phrase it a little bit differently, anisotropy yields a gap in the excitation spectrum, and this gap hinders in the end quantum fluctuations which destroys the long-range order in a Heisenberg system. So how to measure it? We measure it with EPR. So we shoot photons into the system. This is seen on the left-hand side. This is our setup. We shoot microwaves through a system of tubes. Red is a sample, and look at the transmitted microwave radiation and study amplitude and phase. Phase is important. It's also important that we cover quite a large frequency regime. This is between 13 and 1,000 gigahertz. And all this is done in an 18 Tesla magnet. So if you do so, you get the following results. This is on the left-hand side. These are the spectra. The spectra for different field directions. And if you see there are resonances, anomalies, telling us at this frequency and at this field, we excite a magnon excitation, a ferromagnetic magnon. Then you may want to follow this with frequency and magnetic field, and then you get what is seen on the right-hand side. This is a full spectrum. In green, red, and black, these are our data. There are a few data from the literature before. These are the blue data points, and 3 or 4 data points, as you see in violet and light blue. So the first thing which you now can see, the lines which are plotted are describing the problem very well. And this implies, or this indicates a mean field model solution. With other words, the problem is solved by a mean field model for a ferromagnet, but you have to include domains, and the domains have to have particular properties. On top of this, you learn that there is this gap indicated by the orange arrow. This is the anisotropy gap. So we measure very precisely the anisotropy gap, which is 85 gigahertz here. And in particular, we can follow this anisotropy gap, and this we did, left-hand side, we follow this above TC, and it's not vanishing at the ordering temperature, telling us even above TC, there's enough, there are enough quasi, or the fields which we see, short-range ordered fields, are quasi-static on the time scale of the experiment, of the Muse-Air experiment. It does not vanish on a microwave frequency. And this is proven by the other data set on the bottom left. There are quasi-static local fields below 80 Kelvin. So then the next question is that the short-range magnetic order which I was talking about? In order to look at this a little bit more in detail, we just measured magnetization. Magnetization versus external magnetic field on the right top. And all of this is above TC, so in the paramagnetic phase. And all these curves are not linear. A usual paramagnet should have a linear field dependence in this frequency dependence, in this temperature dependence, telling us we have short-range order. And just by fitting the curvature, we get an idea of how many spins are short-range ordered to explain this. And if you do so, you get the data on the bottom right. So the number of spins per cluster. These are the field data points above TC. So there is some order, some short-range order above 200 Kelvin, which is much more than the 80 Kelvin which we saw before. And if we apply, in the end, a purely 2D model in order to translate this into the correlation length, which is probably correct at higher temperature, which might become incorrect in the very vicinity of TC, we even can deduce the in-plane correlation length. This brings us to the following picture. So we have a system which orders long range above, below 60 Kelvin, and this order is driven by anisotropy, or is due to the fact that the system is anisotropic. At very high temperature, we have a short-range ordered phase where we do not see any anisotropy gap. Then the system cools down, anisotropy becomes important, and the long-range order develops from the anisotropic short-range ordered phase, telling us again that anisotropy is relevant in the system. So this brings me to my summary. I've shown you that first of all, we can measure thermal expansion and magnetostriction in such a system, which was something which I didn't believe before I saw it, and I don't know other groups who managed it. Secondly, we can obtain uniaxial pressure effects and can quantify them by this method. We measured the magnon excitation, which I described by a mean field model, gives us a finite zero field gap even above TC, and this implies different regimes of short-range order in the system. And all of this can be seen in the 3 publications which we just submitted or published in the last months. With this, I thank you for your attention, and I'm happy to answer questions as good as I can.
Thank you very much for nice presentation, Professor Rodiger. And now questions. Professor Arafa, please give him the mic.
Thank you, Professor Rodiger. Have you studied the chromium dichloride or bromide?
So the chloride has been studied, so EPR has been done. the chloride we are working on with the thermal expansion. Yes, we studied it, but nothing is yet published. And the CGT, yes, EPR has been done by others. And bromide, no, we didn't touch it yet.
Okay, thank you.
Abanoub, questions?
So did you measure single ion anisotropy for this compound?
How should I do this?
Sorry, you mentioned that you obtained the anisotropy. Is it a single ion anisotropy?
No. This is supposed to be, so from our data, I would say this is not single ion, but it's anisotropy of the J's.
Yes. Thank you for the presentation. I wanted to ask about the ESR. So you can measure the magnon excitations using the ESR. And in this case, do you see any signature of the short-range correlation?
I would say yes. So what we are measuring is the anisotropy of the fields. And the fact that we see anisotropic quasi-static field means short-range correlations must be there. The long-range order is at 60, as evidenced by entropy. So this is a clear indication of short-range order. If you ask, for example, whether we see some evolution of magnetic fields at higher temperatures, so you would have to use a resonator, which we didn't do. So we didn't look at this, at least as far as I remember. Either we didn't look at this or the signal vanished. This I don't know, I don't remember.
And one more thing. So in case if you are using the ESR for measuring like a conventional magnet with a spin wave, what will you see in this case? Will you just see waves or it will be just signals? Because
no. So we measure the magnons. So of course, this is a magnon excitation like you are doing it, but we are restricted to photons, Q equal to 0. So in this sense, it's much less information because we have no access to the Q space. Maybe we are a little bit more precise at Q equal to 0. So we are, but no, it's not comparable to your data.
Thanks.
Okay, Professor, Professor, here, please, in the front.
So can you go back one slide? So this is the short-range order information you have here.
Yeah.
Is that unique compared to, say, a 3D a magnetic system that is a 3D magnet? Is the amount of short-range order higher here because it's a 2D magnet or quasi-2D? How unique is this information?
In a normal 3D magnet, the nonlinear M versus B curves are restricted to a few Kelvin above the ordering temperature, let's say 5 Kelvin. So this, in this sense, it's unique. If you talk about, for example, lanthanum cuprate, there you see things like that because you can, again, you have nonlinear parts and then you can deduce something like a correlation length of that. So it's an antiferromagnet, it's not comparable. I do not know any ferromagnet which shows such behavior. Of course, in the manganites, this is a good example. Ferromagnetic manganites, you can follow the nonlinearity also above TC, looking for the orbital polarons which form there, and also measure the let's say the size of these blobs in the ferromagnetic phase. So it's not unique. So now I have one example. Manganites do something similar.
But you can also see short-range order with mu-SR, right? And so mu-1s will also get short information about short-range order above the...
This I don't know here. I didn't
no,
check
but
it.
I know for gadolinium they have measured it, and I forget actually how far out it.
I would say muons are not perfect, not so sensitive to short-range order. EPR is, I would say, usually better. NMR is also more sensitive.
Okay, we thank Professor Odegaard. Thank you very much. The next speaker and last speaker in this session, Professor Alexander Vasiliev. He is got his PhD from Moscow State University, and currently he is the Director of Low Temperature Physics and Superconducting Department of Moscow State University. And his research mainly focused on the Spain liquid state of matter. Please, welcome. Let me to welcome to Professor Alexander to start his presentation.
I'm asking your permission to make this presentation. I'm asking permission to make this presentation just from this place sitting. It's okay?
It's okay.
Well, and I also ask Artyom to help me to switch between view graphs. So, Artyom, please show. Okay. Being at this conference and at any other conference, I understand that there are many exciting issues in physics which deserve attention. But time is limited. So, if you concentrate, I address students, this message to students, the sooner you find your own important question to be answered, the better. I'm not far from students. I restricted myself to narrow question. What is the ground state of matter? And there are few ground states. And some people say that ground state of matter is liquid. If you speak about superconductivity, superfluidity, it's liquid. It is liquid. And I was thinking, what about magnetic degree of freedom? Can we find situations when magnetic material behave in a sense like a fluid, like a liquid? And to understand it, we should choose a proper object to study which will allow us to realize this liquid-like state. Because usually when you cool down magnet, it arrives to a kind of crystal. It is magnetically ordered state. Can be either ferromagnetic, antiferromagnetic, no matter. But it is 99 and something else % that it will be just magnetic solid. To avoid this solid state, we have two tools. We can reduce dimensionality of the system. And we also can use so-called frustration, competing interactions that prevent formation of long-range order. I am not alone in this search. There are many people working in this direction in this relatively active research field during last, I don't know, many years. So I decided we have to restrict ourselves even more because endless amount of new compounds are suggested to us by chemistry, by material science. So most frustrated situations are triangular magnetic system. Magnetic interactions compete with each other, and so on the first view graph I show some two-dimensional patterns which are in a sense triangular. On the left side there is a so-called honeycomb lattice, and wonderful Kitaev physics belongs to these lattices. Another one in the middle, it is kagome. It is hexagonal voids created by triangles of magnetic ions, or simply triangular lattice shown on the right. So what I am going to speak about today, it looks like a strange because my first word is square, not triangular, but square Kagome. So it is depicted here at the bottom of this slide, but please turn to the next view graph. I presented several cases how magnetic triangles can be arranged within layer, and this picture was taken from paper of Van den Brink and co-authors published maybe 10 years ago or something like that. So Kagome, it is shown here, I don't know what to add. You see that there is corner sharing triangles with hexagonal voids. Then one can invent number B, it's called Sorel net, when 3 corners meet at one point, next one will be 4 corners met in one point, and finally on the right there will be this so-called square Kagome. You see that it is also corner sharing network, but how to understood it? Just make a square, then make triangle on every side of the square and connect this triangle. So it will not be Kagome. It will be something similar, but voids are square and octagon. So the question is, what could be ground state of this arrangement of magnetic ions? Usually when people discuss this frustrated system, they eventually arrive to spin liquid state and start to discuss the question whether it has a spin gap in the spectrum or it is gapless. Please show next one. In fact, this question is a difficult question because even despite, I am afraid to be wrong, but 1,000 paper on Kagome compound, the main question, whether it's gapped or gapless, in some sense depend on how you interpret your data. Here are the results of measurements of a famous compound. It's Herbert-Smithite. It's Kagome two-dimensional network, and people use the same measurements, nuclear magnetic resonance. They use a similar system for the study. And if you read the title of the paper published in Science, it is evidence for a gapped spin liquid state. And the recent paper published in Nature Physics, it is gapless ground state in the same compound. So instead of continue to develop my own vision concerning Herbert-Smithite, we choose another system, a square Kagome. Please show next one. It is a rare case. Artyom, please, can you give me just water, because дай мне бутылку воды. It is a rare case when it is possible to establish precisely when this concept appeared. 20 years ago, in Physical Review B, a paper was published which introduced the idea, the concept of square Kagome. It is written by George and Siddharthan, and they considered this network. They said that the property of this network will be very similar to Kagome. And they made predictions which are very nice for experimentalists. When theory guide you and said you could, whatever, observe some features which follows from theoretical consideration. And they predicted gapped ground state, and they predicted funny special behavior of specific heat. They said that there should be broad maximum, which is standard for any low-dimensional system, it's so-called correlation maximum. And there must be additional feature at low temperature at about 10% of exchange interaction parameter at this temperature. There must be additional singularity, additional peak in specific heat. So during first 20 years, there were only theoretical papers, many of them, and not any attempt to attack this problem experimentally. And theory was developed quite well. So it was only time to find suitable material. Please show next one. Next one, I just once again show what are ground state. It can be that is this so-called resonant loops are the ground state of this compound. It can be square, it can be pinwheel, and it can be excitation into another configurations, but it is it can be so-called singlet transition, endless amount of various combination of singlets. This paper was published maybe 7 years ago, and now let us see what we have from experimental point of view. Next one. It is not yet experimental, it's prediction. It is predicted the energy of ground state. It is predicted temperature dependence of specific heat measured in Kelvin in exchange interaction parameter scale. And it is predicted 1/3 plateau in magnetization for this type of system. Okay. And also Toru Sakai invented special name for this type of lattice, also Japanese name, shuriken. It's ninja ancient weapon. So we have kagome, Japanese term, and we have shuriken, also Japanese term for this. So next one, please. Well, once again, I even difficult for me to go into details due to limited time, but this diagram, it is a measure of how which states are formed under magnetic field, and also dependent on the ratio of two exchange interaction parameter. In this square lattice network, one can determine A-B exchange interaction. Maybe go back, Artem. Maybe go back one more. No, here. It is two sides in the crystal lattice of this parameter, A and B. And they should not be equivalent. It will be JAA and JAB. So one can treat the system as a function of ratio of this parameter. So different quantum ground states are predicted for different ratio of this exchange interaction parameter. So it's a seemingly simple system, in fact rather deep. Okay, so go, okay, so it can be some valence bond crystal states. It can be 1/3 plateau and 2/3 plateau. ferromagnetic ground state is predicted for some ratio of these two exchange interaction parameters, and also counted ferromagnet. So the phase diagram looks rather complicated now, but please go to the next one. But triangles themselves can be not equilateral, but it can be with different sides. So there will appear 3 different exchange interaction parameters in the game, which makes everything almost impossible to comment. Because if J1 is not equal to J2 and not equal to J3 within triangle, many different ground states can be realized. Simplest case is when we have classical spin liquid or nail states or up, down. So I better not comment it because it will take all my time and I make everything too complicated. Let me turn next one to what we have experimentally. Experimentally we have 4 minerals which possess this crystal lattice structure, and chemical properties of these minerals are written here. And to create this square Kagome system, one needs 6 copper ions. But in some of these compounds, you may notice there is copper 7. Sometimes it's copper 6. Sometimes it's copper 7. 7 means that there will be some extra copper ion outside of square Kagome lattice. So, and there exist also 2 artificial compounds, synthetic. One of them is just synthetic analog of atlasovite, where iron is substituted by aluminum to remove magnetism of iron. Another one is just brand new, created in our university, which is synthetic, not analog in mineral world. I show here pictures of mineral on the left, and what we obtain in laboratory, it is green color, artificial, thin crystal growing. Okay, next one. Next one, let me go, what was observed by Japanese group when they investigated first experimental investigation of square Kagome system. They used almost every possible technique, including muons, neutrons, thermodynamic measurements, everything. And to come to conclusion concerning this work published 2 years ago, they arrived to conclusion that ground state is some kind of gapless spin liquid. They obtained this conclusion from muons and from it is no long-range order, and it is no gap in magnetic excitation spectrum. It was kind of disaster because 20 years of theoretical research, it was claimed that there must be a gap in magnetic excitation spectrum. First experimental study resulted in absence of this gap. Okay, let's move to the next one. Next one was our research on this compound. And you see there is network Kagome lattice, and there are isolated copper ions, so-called number 7. They play not efficient role in the properties, so we measured basically specific heat down to 50 millikelvin. We observe uprise due to nuclear specific heat, but we see no indication for the spin gap in our compound also. So, two first research experimental on square Kagome system led us to conclude that we deal with gapless, or we cannot exclude tiny small gap. Well, it is not disaster, but it is contradiction between theory, between 25 theoretical papers and 2 experimental. Next one. Next one, it is new compounds which we synthesized recently in our university, and it is slightly better. Situation started to change in good direction. Let me just comment thermodynamic properties. When we measured magnetic susceptibility, we observed nail temperature at about 3 Kelvin. It is not good. It is, we expected spin liquid state, but nevertheless, we have indication for long-range order at about 3 Kelvin. Then we measured specific heat. In specific heat, we see tiny, very small anomaly at nail temperature. It is even not seen here. It's difficult to see. It is shown here, and it will be shown better on the next slide. But long thought anomaly in specific heat predicted 20 years ago appeared above nail temperature. When we apply magnetic field, we immediately suppress antiferromagnetic order, but this anomaly, which ascribed to spin singlet triplet transition, is robust. It remains. And here it is shown that blue color ions, it is square Kagome, and red one, it is ions which are out. So now it looks like the following. We have 2 coexisting systems in the compound. One of them is this isolated red color ions, which are able to create long-range order. On the background of this sea of spin liquid state represented by square Kagome, and above that it is nail order of small number of magnetic ions. How they interact between themselves? They can interact through excitations from the ground state of square Kagome. Next one. Next one, probably here one can see better what I am speaking about when I say that we see 2 anomalies in specific heat. And at 3 Kelvin it is this nail, which is easily suppressed. And at 6 Kelvin it is robust, strong anomaly. So our next step was to ask people who can use electron spin resonance to check where ESR spectrum change from paramagnetic to antiferromagnetic. And our recent observations are that antiferromagnetic spectrum appears only below this 3 Kelvin. So in this case, we are forced to say that this second peak in specific heat predicted theoretically, we probably observe. Okay, next one. Next one, please go back. Go back. Now we have compounds with rubidium and cesium instead of potassium. So we will get more and more information about ground state. But the question is important, whether it's spin liquid or what is that. So next, it is crystals and so on. So summary. Basic properties of studied compounds allows considering a quantum spin liquid as ground state. We have controversy concerning presence of a gap in quantum ground state in these two materials. In experiment, it is gapless, or it is gapped in theory. So we should continue this research. Broad peak and specific heat of gallium copper 7 at low temperature is indication for the presence of singlet triplet gap. So we have contradictory results. I don't know what will be future, but it is contradictory. From some data, we say that we have gap between singlet and triplet. From low temperature specific heat, we say gapless. We have controversy in our own data. Next one. So it is written in few languages. That is nice goal to pursue, and one of questions to be answered. So last one, please. Thank you very much.
Thank you, Professor Alexander, for nice presentation. Sorry, due to the limited time, we need only one questions. Only one questions. Do you have? Okay, so please.
Can I ask you, the theory is made for a 2D material, I guess, but your experiments are, unless your crystal planes don't see each other at all, it's for a 3D material. So maybe that's part of the reason why there's a difference between prediction and observation.
Yes, I have answer. I hope I have answer to this question. Any material, any material is three-dimensional. It depends how you estimate interlayer exchange interaction. So from my experience, it is enough two-dimensional to be to allow comparison with theory.
Right.
Interlayers effects come into play when we see this nail temperature, and it is only one of compounds where we see it. In other cases, it is no long-range order, which means that long-range order is not established. In two-dimensional system, you do not have nail order in pure. Well, so I don't think that our problem are with the situation that theory consider purely two-dimensional, right, and we work with real materials.
Right. Thank you.
Okay, thank you very much. We thank the Professor Alexander again. Thank you very much. And Dr. Mahmoud Abdul Hafiz want to announce something, please.
Thanks for the chairman. So I have a short announcement. After the short break, we will have two panel discussions, and at the end we will have a closing ceremony, and we have a small gift for all students who presented poster. So please to try to be present during the closing ceremony. And before we go to the short break, I would like to ask all invited speakers to come here for a group photo. So if you don't mind, just come here, and later all students can join also for another photo. But let us first ask the invited speaker to get a photo.
No, it's here. Stand here. You didn't have to look back.
باشا بس في حد يجيب لنا مي للسبيكر.
مرحبا، كيف حالك؟ الحمد لله.
تفضلي معنا.
اعطيني اخر وحده انا شو اسوي؟
انت معنا
So welcome everyone to the first panel discussion in the afternoon. So the moderator of our panel discussion today is Professor Mu'tazem Saidan, who is a former Minister of Water and Irrigation, and currently he's a full Professor of Chemical Engineering at the University of Jordan. So Professor Saidan, throughout 2016 till 2018, has led a multidisciplinary team of experts in the field of water, energy, and environment, Nexus. As well as Professor Saidan coordinate research project funded by EO, UNIDO, and several funding agencies. So welcome, Professor Saidan. So please, the floor is yours.
Good afternoon, everybody. I would like to welcome all of you in our session regarding climate change and solution. And let's try to shift you from micro and nano scale, dealing with material and all of these analysis, techniques, to another global, I would say, level of common problem regarding climate change, which is a transboundary problem. And let's also delve into differentiated responsibilities according to the country, economic, I would say, capabilities, and other solutions dealing with this topic. This topic, as you know, it is full of debates, of argumentation. Many schools with climate change, others with not. They do not agree with that. Regardless of this debate, we as environmentalists, we know that there are a pollution, and we know there is a global warming in the earth temperature influenced by atmosphere with dynamic air change. And we see on the ground some areas they are now droughting, others they are suffering from floods. So whether we are with climate change or not, there is a change. There is something driven by pollution, which is made by human beings. It is an anthropogenic, I would say, effect. And because of that, we, on different levels, we should respond. The response started in 1992 by Rio de Janeiro summit, and they put some targets for Annex 1 countries, developing countries, and this will be shared and cooperated with non-Annex 1 countries, developing countries, and they need to get back the emissions as it was in 1990. But still, we have some problems. Some countries, they are capable to do this, reduction. Others, they are not. We are trying to stabilize the political term or objective in all of protocols and multilateral agreements. They are using stabilization, not elimination. And even we are trying to stabilize, but still it is a suffering process. And there are many political, I would say, influence and economic burden behind that. But we as experts and scientists, at the end of the day, we are the tool. We should, offer solutions for translating this political objective into technical and physical change on the ground. That's why it becomes as a multidisciplinary sphere and field of research. You can find different, backgrounds of scientists. They are trying to cooperate, to talk the language at the end of the day, to reflect this objective on a materialized reduction and to protect our global earth, I would say. A week ago, I have been participating in a webinar in Open University of Catalonia in Barcelona, and the title of this webinar was really scaring everybody. The title was, "It is really too late to respond to climate change." And I have been, teaching in this field since 15 years, and I used to tell my students that in order to get everything, into the baseline as it was before the industrialization, I would say, stage, we have to respond 10 years before. And now we are more than 30 years since 1990, and still we are giving, you know, some scaring statements that we are too late to respond to climate change. In this session, you will be hearing, you know, different, I would say, inputs from different scientists and from different backgrounds, in which we are trying in this short time to share with you some solutions, some facts, some, you know, challenges and solutions to such, you know, a global problem. And in this session, 4 speakers will be participating. Until now, we are having 2 speakers, and we will start with Professor Dr. Ayan Stewart. He is from Al Hassan bin Talal Research Chair. He is Al Hassan bin Talal Research Chair in Sustainability at the RSS, Royal Scientific Society, and he will be talking for 10 minutes about his insights. Then we can open, you know, discussion for questions, or we end once we end this panel, we can also open more time for discussions. Please, Professor.
Thank you very much. Thank you. Shukran. So, yeah, hi. This session is on solutions for climate change. But as we all know, the solution for climate change is to reduce our carbon emissions. These are the carbon emissions that have been going instrumentally recorded since 1958 on Mauna Loa Observatory in Hawaii. So we know that the carbon dioxide increase is what's driving global warming, and we know what's driving the carbon dioxide increase in terms of society, because it's driven by economic growth and it's driven by rampant accelerating material consumption. So I got a feeling we're not going to solve the solutions to climate change in this session, because if we look at the latest intergovernmental panel on climate change, the expert view now is that we have 5 years to start reducing carbon emissions. If carbon emissions are not going down in 5 years, then we're increasingly getting into the territory of dangerous climate change. And the longer we leave it, the more extreme that gets. So if you think about that, 5 years is the time that it takes an average person to go through university. So in the time that it takes someone to go through university, we have to completely reconfigure the global economic and financial system. Every sector, every organization will have to change, and including universities. The academic institutions will have to completely radically change, like all of the other organizations, or else we will not make it. So because of the impossible, intractable issue of solving climate change in the session, what I've decided to do is look at one small aspect, which I think is important, and it's about communication. It's how we communicate climate change, how we communicate the problem. This image shows the first time that an international global leader talks about burning fossil fuels and driving climate change. And it was Lyndon Johnson in 1965. February 1965. I was born in November 1964. I was maybe 5 months old when the first president of the United States says that the science is good enough to be showing that we are changing the climate of the planet. And yet, as has been highlighted, here we are 55, nearly 60 years on, and we are still got a problem translating the science into action. And it's action that we absolutely need. So I'm interested in this. Why did it take 50 years? In the late 70s, we had the Charney report, we had the Jason report. If you look at the results of that, it's a climate science reports, they say pretty much exactly what the Intergovernmental Panel on Climate Change says now. Talks about amplification of the temperature in the poles, talks about sea level rise of about 0.8 at the end of the century. It talks about many of the same aspects. The science has not changed in 60 years, and yet we still can't get it across to the public. So the issue that I'm interested in is how we convert scientific and technical knowledge into public action and policy action, because that's the thing that we need to do. It's not scientists that are going to solve this problem. It is the public and the people who will solve this problem. And so we need to kind of help them there. I talk about the public. The public are a strange bunch. This is a slide showing what's called the 6 Americas, but you can do the same thing and look at it. I've seen it done in Europe and the UK and lots of other places. This was done in 2011, and it looked at who is it, what do people think about climate change, or global warming as it was called, 2011. And you'll see that there's a small percentage, 10%, 12%, that are concerned about it in 2011. And the other side, there's a same amount that's completely dismissive, and most people are in the middle. Most people are confused. They're in the middle because it's complicated. This stuff is really complicated. But if we move forward to, I think this is 2019, this is America as well. This is the new 6 Americas, and you'll see it's changed dramatically. There's still 10% on the right that think it's a load of rubbish, think it's a scam, think it's about taxis. But actually, most people now, if you look at the alarmed and concerned, more than 50% of people, the majority of people, let's say, are now in the USA, which had previously been a very skeptical environment, are now worried about climate change. Something should get done about it. But why is it? What has changed then in the course of the year? Is it the science that's made this happen? Is it because we've got better and better science? Each of the IPCC reports comes out stronger and stronger and stronger, but is it that? I think it isn't. I think it's this. I think it's the groups of other people who have picked up the baton, that picked up the challenge from science. The science is important for providing the fundamental basis, the foundations. But it's other people who have picked up from the scientists and ran with this to the public. So religious leaders of all faiths have got statements now on climate change. So it doesn't matter if it's Muslim, Christian, Judaism, Taoism, or whatever, there are religious statements about the need of earth stewardship to protect our planet and not to pollute it. The celebrities. There's Leonardo DiCaprio, making films. We've got films about climate change. It's making it into the public consciousness. Business leaders. I mean, Elon Musk is certainly a divisive character, but many global businesses, global corporations now talk about that climate change is a driver for unsustainability that is affecting the business bottom line. It's an economic argument to that. Perhaps more importantly, though, has been the social movements on the street. So Greta, started a 17-year-old schoolgirl, goes around the world, and basically re-energizes the whole of the climate science. I don't know a single climate scientist who's not been completely transformed by Greta, which is extraordinary to think about. And then the movements that have risen from this is Extinction Rebellion in the UK. We've got even more radical ones now that are taking direct action for climate change. These are the things that science have spawned, have produced, but are now being much more effective in the public domain than scientists. And one other one, the people at the sharp end, the people who are actually facing climate change. This is an Inuit hunter in Greenland who goes out onto the sea ice there. This is my photograph of him. The sea ice in that area, Ilulissat, is now melting 1 month earlier than normal, so his whole life has had to change. But we're seeing this again and again and again. First it was in the outer reaches, in the South Sea Islands or in the Greenland. We're now seeing it in the heart of Europe. People are seeing climate change, and it was referred to here. I think people in Jordan now sense climate change. They feel it. That's really, really important. So what are we doing about it? Well, I think there's different aspects. So a lot of my work has been, I'm a scientist, I'm a geoscientist or scientist, but a lot of my work has been making television documentaries with BBC Science, communicating. This was one on climate science that ran a few years ago. So the use of media and communication is absolutely key. 2 years ago, I was the advisor on Attenborough's 7 Worlds, 1 Planet. And this is a quote that David Attenborough made just before COP. That saving the planet is now a communications challenge. We know what to do, we just need the will. This is a critical thing of how do we get the political and the public will to do the actions needed. That's the challenge there. And on that basis, one of the things I think we're going to have to talk about in terms of a Jordanian context is, well, how do we do that? How do we communicate climate change and sustainability in the Jordanian or the MENA context? What are the narratives that we need to reach? What are the ways that we can connect with people? What are the channels? And in that context, there's a bigger question for the scientists. What is the role of the scientists in all of this? Do we still need to go out and collect more data on climate change? I think we know enough. I think the challenge is how does the science community, the academic community, become galvanized and catalyzed into helping communicate this to this wider public? And on that point, I'll leave it. Thank you very much.
Thank you, Dr. Ryan. If you like, we can open the way just to receive some questions. Any question? Bad session. Okay. Thank you, Dr. Ryan. Thank you so much. Now to the next speaker, Professor Dr. Mohammed Matouk from Al-Balqa Applied University. He will be talking about some facts about climate change and solutions. 10-15 minutes, Doctor. Something like that. Inshallah. Inshallah.
Start?
Yes, please.
Thank you very much. It's my pleasure to be here. I will not talk about science and policy. We just want to introduce for you what will going on if we keep in this way about the climate change. As you know, the climate change concept is not new. Basically, people, when we are talking about, when we say climate change, basically we are talking about CO2. CO2 is the main contributor for the global warming, and the cause of the global warming is the climate change. And let's say our planet has been, after the Industrial Revolution, we start to face about the increased emission of CO2. I will talk on this slide. As you can see, if we backed in after the Industrial Revolution, we can see that in 1990s, which is marked the first alarm of global warming in Rio de Janeiro Earth Summit. At that time, we start to know the concept of global warming has been started. And as you can see, the temperature, if we go back to 1850s up to 2020, let's say 2020, the temperature almost only 0.2 degree. You cannot feel it. If you see 8 degree, 1 degree Celsius is not measurable, and you cannot feel it. But in fact, the impact on the world will be very much. According to the Intergovernmental Panel on Climate Change, IPCC, greenhouse emission has been increased since the pre-industrial era, driven largely by economic and population growth, and are now higher than ever. This is the main contributor of the climate change and the cause of the global warming. Greenhouse image, when we see that CO2 or carbon dioxide, it's the main contributor of the global warming, CO2. Also, we can see methane, gas methane, and nitrous oxide. What does it mean, the climate change? The changing climate has a target of impact on the environment, impact in the ecology, and there are some physical impact in humans, including extreme weather events. And this is the main factor that we are going to focus and talk about. Extreme weather events, such as in Jordan recently. We have a talk that summer has been passed very, very quickly. We didn't feel it because we can see 4 seasons in 1 month. You can see spring, winter, hot within the same month. So this is extreme weather condition. Another impact, floods, drought, storm, and heat waves. This is a new concept to start about when we talk heat wave in Europe, America. Now there's a new concept of climate change impact heat waves. Before it was, I will explain later in the next slide. So what we have to do? We have to do to reduce CO2. Can we reduce it or not? The good thing that scientists has been making modeling, simulation, and they found that the CO2 concentration, carbon dioxide concentration, can be reduced. But the fact that it can be reduced, but you cannot see the effect within 5 or 10 years. You need a decade to feel the impact or the reduction of the CO2. And believe me, when I teach to my students, I told them that people with the age of 30, 20, if you told them there's a climate change, no one will believe you. But for us as 50s or 60s, when you say the climate change, yes, it's completely different 30 years before and 20 years after. So people in the young generation, they cannot feel it. When you say climate change, nobody will be, what's the meaning? So they already in the problem. But we, as not young generation, we can feel the difference. Before 20 years and 30 years, we can feel there's a difference. So this is the fact. The climate change, you cannot feel within a short period of time. This is the actual concentration of CO2 800 years before the Christ and up to 2020. If you can see, the concentration basically was in the atmosphere 200 ppm. And now we are about 400 ppm. It's almost twice the concentration. Annually, if you can see, we have been contributed up to this moment about 35 billion tons of CO2. Please remember this number, 35 billion, because later on I will talk about economics. So we are about 35 billion CO2 emission per year. There's another gas or green gas emission like methane and nitrous oxide, but still in, let's say, part per billions, still lower than, but the CO2 impact is higher. So you can see here also in this figure, this is from World Data. You can find it in the internet. It's very good and nice simulation. You can see CO2 emission per capita. Every population, you can see North America, Europe, China, and Asia, let's say Asian country, they are emitting the about, let's say, 10 tons, about 10 tons, but low-income countries, they don't have high emission because they don't have industry. This is the equation that we will talk about. So the emission below 1 ton per year, and this is according to the data 2020. And you can see Australia, North America, and Middle East country, we are in the range of between 1 to 2 tons per year of CO2, which is a big amount. You can see this is the summary for all the world. Asian country contribute about 53% of the global CO2 emission. We are Asian country. China contribute 27%. India, Japan, Saudi Arabia, Thailand. So you can see about 53% of CO2 emission in the world comes from Asia. North America, Europe contribute about 3.5 billion. USA 15%, and Europe 19%. African country, they don't have industry, they don't have such a big emission. So if we can see this figure, you can see what's the main contributor of CO2. Basically, we are coming, the CO2 emission coming in these countries, I mean Asian country and North America, from fossil burning, oil, energy. So you can see this is the contribution for each country, how much they contribute to the world for CO2 emission. As I said before, 35 billion tons per year. So what we have to do? The last conference, let's say Paris Agreement, recently, the world has come to, we have to sit down, we have to reduce in order to return back at least 2 degrees, 2 degrees Celsius. This is according to the Paris Agreement that we have to work together in order to reduce only 2 degrees. But there is a big negotiation argument that we cannot reach the 2 degree, we have to reach 1.5 degree. So what will happen, we have now 2 scenarios. We are currently in 2020. If we keep on, there is no climate policy, we don't have any action, we'll go into 4.1, 4.8 degree increase in temperature. If we go for the scenario, now keep a policy, we can reach 2.5 to 2.9 reduction. If we work very hard, we'll see how we work very hard, the target for 2.1, by 2100, all of us will be not in that time. So we will return back to the CO2 reduction, hopefully by 2050, 2070, we can reduce if we are working with this agreement and commitment to this agreement. What kind of working? There is a concept what we call net zero carbon emission, or zero carbon emission, sorry. Zero carbon emission means that you have to balance. Now we are producing 35 ton per year. We have to reduce it 25. So 10 billion ton per year, you have 10% reduction. Fortunately, some countries like America, European, and in Latin America also, they are going to have the concept net zero emission, which is really very appreciated. African country, we are still no data available. Some country, they already achieved net zero carbon emissions, and other still working or in policy. So if you can see, the green one is in law, blue one is achieved, and the gray one is we are going to something promise. In fact, these countries already have been achieved net carbon emission in order to reduce carbon dioxide emission has been achieved in this country, basically. And I'm very happy to see that from Arab countries, Saudi Arabia is included. And you can see in the south of Africa, because these countries are really facing the climate change, flood, hurricane, everything, sea level, so they really adopt this kind of zero emission. So if we keep in this net zero and carbon reduction, what we will have? We will have, if we are going to implement concept of only 2 degree reduction all the world, we will, by 2050, we will go back to reduce from 40 billion tons of carbon dioxide to about 18 billion. This will be achieved by 2050, 2030 and 50. But if we are going to work on 1.5 degree, we will have that by 2030, we can reduce 15 billion tons. This is the changing point for the scenario if we keep 4.5 degree. The question, can we make a progress in reducing emission? As we said, yes, we can. But the fact, it's something like carrot and stick. You want to reduce CO2, you will lose the GDP. There is economy. You have to reduce CO2, no energy, no power supply. So it's some kind of complex equation. You have to make a balance. Rich countries, they have standard living, GDP high, but also have high level of emission. Poor countries like Africa and other, that they have level of emission, but poor standard of living, but GDP is. So you have to make some kind of balance between these. Some countries have shown signs of a progress, like USA, United Kingdom, France, Spain, Italy, and many other countries, they are having a good balance between the GDP and the carbon dioxide emission. Still, we are off track. We have a target 2 degrees. All the world, we have to collaborate to reduce for only 2 degrees, but still, it's signed agreement. Action is needed. What is our definition of fast enough? We are working for reaching 2 degrees in reduction, but still we are not fast, we are slow. So we can make a progress, but it's currently too slow. If we do the progress, we cannot see within 20 or 50, 30 years. We need large-scale acceleration and efforts across the world. All the world, they have to work hardly in order to reduce this kind of carbon dioxide. How we can make a progress? Progress in energy. This is very important because energy is the main contributor of the climate change and global warming. Food and agriculture. You can imagine that climate change, food is included as the main contributor of the CO2 emission, and improving our efficiency of energy use and low carbon alternatives. And these can be summarized in these figures. I will pass because I think I need 5 minutes only. Okay. You can see here fuel energy, fossil energy, is the main contributor. Before we are relying coal, but nowadays we are relying crude oil. Recently, natural gas has been introduced, and the other industry has contributed for the major energy contributor. You can see in this figure, 73% of global green gas emissions coming from energy. 18% come from agriculture, forest, and land use. 3.2% of global warming come from waste, industry, and other factors. So you can see energy is the main contributor of our CO2 emission. Food, when we see food means that contributing 26% of global warming comes from food. How? Land use, fermentation, crop productions, emission of methane, CO2, livestock, you mean cow, producing the high percentage of methane gas. When I was in Japan 20 years before, the Japanese was thinking to have some catalyst inside the stomach of the cows in order to reduce the CO2 emission. So at that time they were thinking to reduce methane gas produced by the cow. Sometimes they have to reproduce. So livestock produce like sheep, cow, goat, and cows produce high percentage of methane. And supply chain, transportation of the food, also consider one of the main contributor of that. The last thing we are talking, what is the disaster of the climate change? As you can see, this is from 1919, up to 2020. You can see we have a lot of natural disaster, drought, floods, earthquake, volcanoes, storm. These are typical natural disaster. But we have a new terms, as I told you before. Now we can see extreme temperature included. Before, we don't have extreme temperature. You can, yesterday in Jordan, 43.5 degree was the temperature in Al-Baqura. So it's high temperature. So this kind of disaster, new type of disaster we are facing of the climate change. This is start from, let's say, 1980. This is another typical figure we can see in USA in 1990s. They start to have heat wave. So before they have typical flood, winds, lightning, hurricane, but nowadays we can facing this is natural disaster or disaster impact of climate change. And this is the world global rain. You can see now increase the rain from 1990. The amount of precipitation has been increased. This is good for like Jordan, we have water scarcity, we can say, yes, it's good we have rain. Yes, you have rain, but it's not going to the right place. The rain goes to the desert, rain goes to the sun, not agriculture area. So a lot of amount of work, but bad distribution. It's not God-made, it's our made. I mean, distribution by nature. And this, as we said that sometimes you have to pay for mitigation, prevent the disaster, not to pay for the compensation of the disaster after it happened. So this you can see how much we are paying for disaster reduction and mitigation. After having the disaster, you have to pay, for example, hundreds of billions instead of reducing that. This is very important figures I want to talk about and finish my lecture, what we call McKenzie chart abatement. McKenzie is very optimistic. He have introduced us with a very good chart. You have a negative and positive chart, sorry. This negative and positive chart, negative means you can save money. Positive, you have to pay. Large parts mean that this area we can reduce and we can make reduction in CO2 emission. And you can see here, as I told before, remember this number, we are producing about 35 billion tons of carbon dioxide. The cost of this 60 euros per ton. And you can imagine how much we are paying for that amount of CO2. And you can see, for example, using solar energy, efficient transportation, hybrid car, electric car, this kind of proposed kind of CO2 reduction, and you can save money. So if we keep in this way, we'll have our climate change in danger, and the Earth will be in more heat, and we will facing more and more problem. And thank you for listening.
Thank you, Doctor, for this interesting lecture. And I would like to just open the way for receiving some questions. Yes, please.
We have what is the time constant for decay of the temperature? So assume we could reduce all CO2 emissions to zero, and we have an exponential decay. What is the time constant for this? Is it known?
Excuse me. The question is, again, I can't do.
What is the time constant for the decay of temperature to some equilibrium? And I said, assume that you put all CO2, all emissions off to zero. How long would it, what is the, and we have exponential decay. What is the time constant?
Yeah, this is a very good question. This is what we are thinking about. When we reach this even point, let's say, this is the even point. If we are thinking about 2-degree reduction, we'll reach it 2050. If we think about 1.5, we'll reach it 2030. So this is still its simulation and modeling. If we are keeping and commitment to the agreement, but unfortunately, we may not reach it. This is the bad news, because we don't have what the reduction amount if they work together. And we really, you mean sometimes people, they don't believe that the climate change is happening. So still some countries, they don't, I don't want to talk, to mention the names, but you know, some countries still, they are not committed to sign the agreement. After Kyoto Protocol in 1997, up to this moment, some countries, they are not thinking of even to sign. Sometimes we are saying that climate change and policy is something that working together.
If I just add something, I do agree with Professor Muhammad, Dr. Muhammad. But again, politics are behind, you know, the drivers to reach equilibrium. because when we agreed upon curbing against climate change, we bought a record and a reference to be 1990. The problem started in 1960. So we agreed that the 30 years between 60 to 90 were the main cause for the climate change. But equilibrium is to reach the emissions or the concentration in 1960, before the industrialization, I would say, revolution. Now, politics, they are driving us to 1990, which means only 5% of the emissions that were before 1990. By assumption, we are accepting, a high concentration, relatively high concentration of CO2. So we will not reach equilibrium. That's why the best and the most optimistic scenario, you will end up with 1.5 degree as an increase in temperature. This is an average. An average degree, an average increase in temperature, maybe in Jordan it will be 1.5, but in the Antarctica, for example, it will be 12 degrees centigrade, and we will be suffering from the consequences of melting of the frozen, water there. So I would say I do agree what you are requesting, at what we are aiming as an environmentalist will not be materialized, will not be the case that can be achieved. We will accept a certain oscillation, I would say, with CO2 emissions to a level in a best scenario that will increase in 2050 a 1.5 degrees centigrade as an increase in temperature. It is a political, I would say, driver behind this.
Can I add something?
Yes.
I don't have the. I don't think
You have to click it on.
I'm not a climate modelist. I don't know the answer to your question, your specific question, but I know that the climate modelers have got an answer to that. But I wanted to add one other dimension to that, which is that even if we switch off all carbon emissions tomorrow, one of the biggest problems of climate change, sea level rise, will continue for centuries, because the temperature increases in the ocean is starting to move down for superficial waters down into the deeper one, and that is going to lead to the ocean expansion factor. So even if we stop tomorrow, if we're looking at it's likely that expansion factor will go on for centuries. 2 centuries is already locked in. So coastal cities, most coastal cities, are already looking in 100 years, 150 years at several meter scale sea level rise, even if we do nothing.
I have one more question, if I may.
Yes, please.
From one of the charts that you showed, if you look at the time period from 1940 to about 1960, basically the temperature was level. Was this due to World War II?
No. That global cooling is a masking effect of pollution in city pollution. So it's a very high sulfur content. What happens after the 50s comes in is that a lot of the stuff around improving air pollution in cities, cleaning cities up, and we lose that high sulfur content and then global warming kicks in really. So it's there in the background, but it's masked.
Also, I can add something that last year, 2019 and 2000, CO2 reduction has been marked as a very good reduction in the world because of the COVID. There is no transportation, and also this is, as you note in the figure, some drop in CO2. Fortunately, we don't need another pandemic, but hopefully we need another reduction.
Maybe that's a solution, you think? Another pandemic.
Yeah, any questions?
Yeah, thank you. So I'm a poor scientist from a rich country. So I wanted to actually express my disappointment that we need influencers actually to make awareness in the population. I mean, scientists already made a prediction like 40 years ago how it's going to be, and politicians don't do anything. So I don't think scientists have to take the role of trying to, we do as much as we can, but you spend most of the time in the lab, Another thing is, I'm also disappointed that everything is ruled by business as usual. I mean, the COVID was amazing how fast they solved the problem. Why? Because they could profit. I think I have a huge hope in the potential of humankind to solve this problem, but there is no profit. There is no clear profit, so no one is going to do it. And as Greta said, I mean, it's a lot of blah blah. And it's still in my country. After the COVID, I go to the airport, and it's packed with people going for holidays. They don't care. I need my holiday. And Ryanair is still having low prices. How comes? So just to show my my very sad perspective on all this. No question actually.
I want to add something to your comments.
Yes.
We have a good teacher, but we have a bad student. Scientists, they roll on teaching us and introduce what scenario, and they put the solutions. But the student, they don't want to take this homework. Maybe it's difficult for them.
Can I add one? Oh, sorry, you
yes,
can. No, please. Yeah. My point was going to be really around that, if you like, culpability of the scientists in all of this. Where does the role there? And I think if we've had a culpability, it's that we've not really understood how people make decisions. Our assumption has always been that if we get the data right, the technical information right, and then just put it out there, everything then will fall in line. And what we're seeing, and we see it with COVID, we see it with other things, is that it's not just about that. You have to have good data, but then a whole set of other things have to come in as well. And so I think this is a key point about the role of scientists. Is our role just to provide that technical data and then go, halas, stand back, and let other people do it? Or is our role to prosecute it further on, to continue on and carry on? And if we're going to do the second, we have to learn how people make decisions and how to influence people. If we're just interested in the first, we can just stay in the lab. It's fine.
Yeah, but you cannot do everything. No, it's not like that the way I see it. I think it's just a matter of profit. If there is, when the laser was shown, we say, well, this is how it works. Bam, we went home and continue. Someone took it over and make a lot of money.
So one of the arguments now for trying to get society to change is the green economy, the Green Deal. So it's framing climate change as an economic benefit. So that is a narrative that works for some people. It doesn't work for other people. We need multiple narratives. The question is, what is the role of scientists going to be in that? That's the interesting one. Do we just stay in the lab, or do we find a responsibility and a role outside? This is the new question for science. We've not had to deal with this really in the past, but we're now going to have to deal with that, I think.
But if I can reply to that, these are again made by policy makers. I mean, why I do my science? Because there is typically a quantum program which is putting a lot of millions on that, and then I say, well, I go there because the money is there. They could do the same. Put more money on where it should go. I think scientists will provide an answer if the money is there to do the research. But
yeah, let me just
talk more. I disagree with you. We could talk more.
Let me just make it brief, and I will tell something that when we started with the climate change tackling a problem, we started in Kyoto. So, and it was after Russia has signed the protocol. So politics behind that. Then they gave tools. They are economic tools. That's why the unit of CO2 equivalent reduced from $35 to 35 cents. So everybody took the benefit of this protocol economically, and they reduced by supply and chain and demand and supply, concept and economic. The price of CO2 reduced to 35 cents. It was $35. So politics behind that. Economically, they played in in this model, and now we are ending up with we cannot control the country, we cannot impose the countries to stick with their targets. And recently, after Russia invasion to Ukraine and shortage of gas, some companies and some countries now, they are planning to shift again to the coal plants and to get back to the petroleum derivatives as the fuel for their energy sector and industrial sector, and we end up also with politics, making our what you are demanded, getting as it was before, and this will hinder, I would say, the process for a climate change campaign. Professor.
My question, we didn't talk about there is still a role for science, I think, because there is a new field of science saying about the CO2 captures. So we can do something as a community, as a science. We have to, we can concentrate on this topic, that even if the politics and cannot support us because of the economy, the science is still there. How we can increase or put the more shadow in this kind of research to be really practical and go to the public and really capture the CO2. This is might help. If we cannot reduce it, we have to capture it.
Yes.
But we didn't talk about this day, maybe in the next semester.
Can I come back on that? Because I think I agree with you completely. In fact, let's be clear about this. We will not reach the Paris Agreement if we do not have negative emission technology, and carbon capture storage is the most impressive. However, I see no action on carbon capture storage. I talk a lot to the oil and gas industry. They see it as a way of continuing what they do and making money by a quarter twist. They see an economic benefit in it. But they're not putting a lot of money into it yet. They're doing a lot of small amounts, but not big. Governments talk about it, but they don't do anything. Environmental groups are very worried by it because it's the green light for fossil fuels to continue, because it's fossil fuel technology, we need to do this. So this goes back to this problem about how do we motivate change in the public and policy realm? How do scientists motivate change? Because CCS is the technology that's essentially there, but doing it at scale will take huge investment. And that means the public have to want, and the politicians have to want to have CCS, and I don't see any evidence for that right now. The science is there, but the danger is it stays in the lab. The science stays in the lab and climate keeps on going. That's the danger.
Let me say that always I'm saying that there's a big, I think, very known story about the frog and scorpion. Does anybody know about it? The scorpion and the frog. You know it?
No.
Yeah. This is always I talk that there's a frog and float. The scorpion want to cross the river from one side to other side.
Yes.
And there's the Cairo and the Cairo in Japanese. Sorry. The frog. The frog offered the scorpion that to give him a pack, right?
Yes.
And just to cross the river, and he promised that he will not make any bad thing. But in the middle of the river, he just bite the frog, and both of them they died. This is our Earth and us. The Earth is the frog. We are the scorpion.
But you missed the key point though, didn't you? Because the point was, as he stabs him, the frog says, "What are you doing? You stabbed me. We're both going to die." And he says, "What do you expect me to do? I'm a scorpion."
So this is the fact we have to know, that if we don't really work to keep our nature, our Earth, we will destroy it. Earth. It's exactly the frog and the scorpion. That's it. Thank you.
Any question, please?
Good afternoon, everybody. Now, correct me if I'm wrong regarding the using the CO2 industrials here in in the fire extinguisher factories. So this using by the fire extinguishers as pressurized extinguishers using the CO2 for extinguishing the fire. Is it possible that, if I'm not wrong, to try to collect this kind of amount of CO2 and put it in cylinders and just only simply bury them under the ground? Is it possible, or we are talking about something else?
Yes, it's not simple as it, because there's different research that we say that the ocean and the sea can absorb CO2 from the atmosphere. But the problem that sometimes it's not enough quantity, this is one point. Also, we have what we call in the world CO2 sink, because the forest, Amazon, and this kind of nature, as you know, that the chlorophyll methodology of a planet, they absorb CO2 and they give you CO2, oxygen, O2. But the concentration of CO2 in the atmosphere is almost not such a big quantity. You have to collect and put it in the fire extinguisher. In the case of CO2 powders, I mean. So yes, there's a different scenario, but unfortunately, in 1990 they start a lot of research that they capture the CO2 and they put it in the sea and the ocean, and even some injection of CO2 under the mine, crude oil mines and wells, they can inject CO2, but still this is not a good solution.
Excuse me, sir. Another thing, that what about the CO2 that's been used in the soda companies, that's like Pepsi or Coca-Cola? So they are using it and to have it in actually the soft drinks that we have. So is it true that the CO2 sometimes is going to be useful?
But they bring CO2 from the atmosphere. It's not something new.
But it's actually pressured in big tanks, which they're going to return it back to liquid, and after that, when you use it, they will just turn it back to gas.
You know the carbon cycle?
Yes, sir.
Yes. So the carbon cycle, it can balance.
Just add something with the process. We don't only suffer from CO2 as alone. We have another 6 gases which have more impact on climate change. Sometimes 35 times, and sometimes 250 times than CO2. When you talk about methane gas, for example, which is from the landfills and from the waste dumping sites, or if you talk about nitrous oxides from the wastewater treated plants, the emissions of one unit sometimes 35 up to 250 times impact than CO2. So many I would say effects. Now, on scientific basis, yes, we have what was called carbon capturing and sequestration. So we can capture and, encapsulate it, I would say. But the volume is playing a vital role in that. So putting them in a jar, you need huge volumes. Now we are trying just to close the cycle of carbon cycle, for example, capture them and put them underground, then it will be becoming a part of the natural cycle of carbon. Many, I would say, but still the source is emitting. So until when you are dealing with the symptoms of the problem, not on the source, you need to solve the problem on the source, to use the right fuel, the right, I would say, system to reduce the emissions. Please, you have a question? Yes. طيب شو نعمل؟ يعني في ناس just 2 questions and we end up.
Thank you very much.
After. Yeah.
Okay, I would like just to comment on the picture that Doctor mentioned, that about the frog and scorpion, and also Alejandro mentioned that the people that would like to go to their holidays and so on, they do not care. Here I would like to refer to Prophet Muhammad hadith. He said that the people like the people who get on board of a ship after casting lots. Some of them are in its lower deck and some of them in its upper deck. Those who are in its lower deck, when they require water, go to the occupants of the upper deck and say to them, if we make a hole in our bottom of the ship, we shall not harm you. If they leave them to carry out their design, they will be drowned. But if they do not leave them to go ahead, all of them will remain safe. So I think here we need regulations. The government and all of the nations should work together to serve the world. Thank you.
Thank you. Thank you.
We agree with this, and all countries now, they are having their strategies, regulations, and we hope that we can do something. Last question there, and we because we promised here just to receive a question, please.
Okay, thank you for the presentation, and the topic is very important. And I think that, of course, we cannot, as a society, we cannot really solve the problem. It's more political, and comes from oil, and it started from oil, and they knew that this problem would have been in the future. But my question is more from the society point of view, because I watched the David Attenborough documentary on Netflix, A Life on Our Planet. I think it's beautiful, and he said that he's a vegan. So my question is more general, asking what can we do? What is the most which of our action can be better for the environment, and the role of veganism in the change of our behavior?
I'll keep it very quick. The most important thing that we can do, the most important thing, is talk about climate change. Because unless ordinary people are talking about it in the street, the politicians won't do anything about it. So that is the key. There's lots of different ways. There's meat-based diets. There's, in relation to behavioral change, it may be that you don't have a car or don't have a family. The worst thing you can do for the planet is to have a child. Because the point is there's lots of different ways. The most important bit is to talk about the importance of action in climate change. And it's then that the politicians realize that there's a real energy about this, and then you've got policy change. So that, to me, is the most important.
Okay, so thank you so much for your questions. We know it is a debatable topic, and we need much more time just to tackle all of the aspects of this, initiative and the problem. So, on behalf of you, I would like to thank Professor Ayan, Professor Matouk for their contributions, for their presentation, and thank you also for your questions. We hope next time we will meet again here in this university, and we will, give more time for this topic just to be tackled from different perspectives. Thank you so much. Thank you.
So now we arrive to the last panel discussion. I would like to invite Professor Dr. Ashraf Bani Muhammad, Professor Dr. Abir Al-Bawab, the University of Jordan, and Professor Yusuf Abdallat. Okay. Faculty of Engineering and the University of Jordan. So it will be very short. So this is a short panel discussion. And the Mrs. Luma Fawaz.
دكتور عبير البواب.
اكيد كمان اسمع لا انت
الا على تروح سيدي اوكي هيك احسن شيء. أنا بتخيل الناس نامت هلا مبدئيا. Sorry, I will try to speak. I have to speak a little bit in Arabic because maybe some of our students have to learn something about more into about what is innovation, how we manage innovations into becoming a startup or a spin-off from the university. I know most of the professors know a lot about this. So. We'll try to mix Arabic and English as well, okay? First and foremost اسمحوا لي أرحب بالبانل عنا. أنا لكي لأنه بجوز أنا البانل الوحيد اللي معي 2 ستات صح؟
لو سمحت.
I was very much okay. فأنا very much lucky. ست لما بتدير لما فواز بتدير Oasis 500. Oasis 500 is the let's say one of the first oldest venture capitals in Jordan. So we are very much pleased to have you. معنا معلمتي وأستاذتي Professor Abir Al-Bawab. She was one of the most active researchers and research managers in Jordan. She was running the صندوق دعم البحث العلمي Scientific Research and Innovation Fund, and really very much proud to have her today. She's a chemist, فبدنا نحاول يعني ديروا بالكم لما نحكي بالكيمستري معها. ومعنا أستاذنا ومعلمنا الدكتور يوسف العبداللات، الأستاذ الدكتور يوسف العبداللات. Professor Yusuf Abdullah, he's the manager of the national programs called Faculty for Factory, which was a pioneering program since like 10 years. So if you allow me, I will ask each one of you to introduce his background and what is he doing now. And Luma, you will tell us more about Oasis 500. Dr. Abir, you will tell us more about research and applied research funding and management in Jordan. Professor Yusuf, if you allow us to know a little bit more about, Faculty for Factory program in Jordan. Luma, please.
Sure, thank you so much. إنجليزي ولا عربي حيرتنا. English or Arabic? Sure.
Professor Ishaq, he originally from Arab, from Halab. Maybe you know little Arabic.
You know Arabic, doctor? Professor?
So maybe I'm...
Holy curses.
So maybe I'm the only non-professor, non-PhD candidate here or panelist. My name is Luma Fawaz. I'm the managing partner of Oasis 500. Oasis 500 is an investor and accelerator. So we believe in not only giving financial funding, we also help all of you guys monetize. So the important aspect is, you do all your research, you're sitting in their labs and doing all this, theoretical research. We help get that to life. So commercialization is an aspect. We look at things in a completely commercial way. When we invest, we want to make returns, but we want to create impact. And today there's this whole revolution that talks about you could create impact and minimize and help the environment and be socially aware and make money at the same time. So we see them as they're not mutually exclusive. They work hand in hand. We've invested in 180 companies so far since inception. Our inception date was 2010, so we've been out there for 12 years almost. And we've exited 4 companies, and we have a potential pipeline of 10 exits as well. And when we mean exits, is when we invest and scale the company and then sell our shares from that company. So this is, in a nutshell, this is where we are. Happy to take any questions.
The size of the fund nowadays is we are talking about?
So we started off with 10 million, and now we're raising our $30 million fund to be invested in.
The ticket size is 150, I think.
Absolutely.
150.
It can go up to 400,000 if needed, and it really depends on the use of funds. And it's not R&D. It's after the R&D, and once you wanna prototype and go to market. So this is the stage.
Thank you, Luma. Professor Abid, can you tell us more about there is money, and we have the challenge of research management and how we commercialize this process. From your very long experience, running the Deanship of Scientific Research at the University of Jordan and later the Scientific Research and Innovation Fund, how many did you see more applied research, more commercial research, and what are the challenges there?
I will talk from another point of view than Loma. Loma, she say after the R&D. What I really was managing and doing all these years of my life, before the R&D. Yes. We're doing the basic research that is very important for the applied research, for the ARD. So we're funding and we're encouraging not just the academical, the young generation, the graduate student, even the people from the outside of the academia to do that research, but from the beginning to think openly about this research, to see that there is a possibility of this research to be applied and to be commercialized, like you said. This is very difficult because we didn't train ourselves to be in that position. So if we are in the university, if we are in the schools, if we are in a graduate student, most of them, they're doing research, but they don't investigate very well how this research will be go on, and if they have the potential to handle this research, the funded the really good research to other people to upgrade it, to upscale it, to make it more customized. I think in Jordan we're still in that developing stage to do that. There is a huge gap. Luma talking about something, and we are as a researcher in the academia and other side. But I'm optimistic that there is a young generation, our student, they think that they, with that new opening with the social media and everything, they think in another way. I can see some of my students really try to do that double, but the number is not very encouraging, but we are in that stage, hopefully.
In terms of, you are still, a professor at the University of Jordan. What do we need in order to bridge this gap? In order to make, you are now supervising, PhD and master students. How would we, do you think that we need to look backward and, try to do more demand-driven research?
I'm still traditional, like Professor Isaac. I'm still studying that the basic research is the most important. We cannot say we don't need it, but we have to encourage our student to think in to look in another window. And I think I'm trying to do that, me and myself and other professors, but the problem, the funding. The basic research need a little fund. The basic occupied or beside the applied need more and more and need more time. The number, you asked me about the number, or what?
As a percentage.
As a percentage, it's difficult. This is your field, not my field. My field, I'm looking for a good research that's good for Jordan. We have a problem in Jordan, try to solve it. Now, beside my work as a deanship, in the deanship and in the research management, I am happy to be the chairperson for the reinforming education. We adopt some way of education from Europe and try to apply it in our schools. And this is kind of education. Mainly, I'm concentrated on how to teach our student, or lead our student in the innovation thinking and entrepreneur way in the futures. Whenever now in any end of, I have one of my students, Fida here, my question in each defense for my student or other, if you have a chance to do a company, this research to be developed with company, what you recommend to do? And I leave her with this question in the conclusion of her thesis. And if she's have that commercial thinking, I will tell her I will be with you in that company. Let's do that company. And I end my story with that, the thesis in that way. Thank you.
So thank you. And I think this is really very much important, how we communicate innovation and applied research inside the universities. I think here is doing really a great job there. Professor Youssef, Faculty for a Factory was a great idea and a great program. Can you please just brief us a little bit more about what you are doing? You are trying to bridge this gap. What have been done there? What is your future plans in this national program, very important national program?
Thank you, Dr. Ashraf, and thank you, everybody. I'm really so glad to be with you in this nice evening. Actually, it's the national program, as Dr. Ashraf, it's called the National Program Linkage Academic Institute with Industrial Sectors, or as a branding name, it's FFF, Faculty for a Factory. This is a program just to bring narrow the gap, or as a bridge between academic and industrial sectors. When we mentioned industrial sectors, we mentioned in the comprehensive meaning of industrial sectors, not just pure industrial sectors as a chamber of industry. We believe in comprehensive industrial sectors, even tourism as industrial sectors, even education itself, it's industrial sectors, to focus on the production, either human or capital or whatever. And we focus in applied science, okay, not just research. So we believe, the research, it's a basic, but not like school of research science. But we focus on the R&D and I, research, development and innovation. We start from at the beginning from University of Jordan, especially from School of Engineering, and now this is program become national program involve all universities in Jordan, private and government universities, with all sectors even, and we believe by triangle pillars, government, private sectors, with academic and NGOs. Yeah. Our output now we cover all sectors in industrial. Those in Jordan Chamber of Industry, the classification 10 sectors. We cover them all with a lot of success stories with agriculture, and the output with agriculture. Industry companies and staff professors. We got something. It's amazing, really. Even we going to some of them even patent with innovation and invention idea.
Is it also open for students? So you dispatch, the program basically dispatch professors from the university, any university in Jordan, to an industry or a factory or also the service sector. So dispatch one,
Sure.
Students are also...
Yes. Actually, a student with their professor, it will be like strengthening even the application. You know, they applied for us, it's the dynamic system, either from industry, from professor, from Chamber of Industry, whatever. The impact or to strengthen even the application if the student involved. And this is issue we believe by sustainability and will impact, it will more effective the student involved, because you know the philosophy of this program to let the industry open the door for the academic people to solve their problem or to development their product or whatever. A student, as I mentioned, it's something like it's important, and we encourage them to involve the student either final year project, yes, master.
They will get more hands-on experience.
Sure.
So I promise that to keep this short. So. I have to stop here. I know that we have been discussing a lot about this, but as you can see, you have now, we have the money, we have the research, and we are trying to build the linkage. So it's your call. Please ask our distinguished panelists today. So the floor is yours all. So please feel free to ask any question that you like.
They want to go home.
Your Excellency.
Thank you, Doctor. Thank you, everybody, for this, important insights on how to build a sustainable communities. I would say, based on my experiences in R&D and in research, applied research in Jordan, I would say we lack the driver. We lack somebody who should drive our state-of-art science and applied research in order to achieve a sustainable community. This driver should be, I think, the market or the industry, because they know their needs, they have the money, and they have the social responsibility, and we are the tool as researchers and scientists, and we should be oriented to give and to deliver, something useful that can be translated the second day into a product that can achieve, or a tool that can achieve this sustainability. But we don't have it. And sometimes if we have it, the process is based on bureaucracy to the limit that we abandon, to participate in such, a cycle. And sometimes if we have a good momentum and to reach the end and get the product done, we end up with the problem with the patenting, So I would say we need all the players to sit together, to be driven by the market. We are the tool, and we need to reach the outside, market in order to market for our, inventions and our patents. Based on this, I would like to hear from our speakers their inputs or comments on that. Thank you.
Thank you, Your Excellency. Luma, please.
I'll talk about that. Okay. Thank you, Your Excellency. I just want to say that, we we've received 17,000 applications so far. Let me just talk about the market and let me talk about the applicants. Maybe that at least answer part of the question. One, education is part and parcel of our candidates. The applications that we receive usually are very, very theoretical, and we do sit on it, at least we think we sit on the right table to discuss with various stakeholders, including innovation hubs and innovation centers at universities, to talk about, what happens there and the sort of projects that are graduating from these incubators. And unfortunately, you can't do academia by itself. Business has to interfere. So in that factory, getting all these educators to understand business, or maybe not even, maybe getting a part-timer that's a business person that comes in and tries and helps these students commercialize, is the answer to get at least some of these projects. Patent is important, but not everything is patent worthy, and not everything needs to be patented. If it's commercialized, we can worry about the patent later, as long as. And I just want to also talk about maybe innovation to business. When it comes to business, at the end of the day, if you're not doing business, then your invention is not really worthwhile. And the issue is, we concentrate on patents, and we don't want to go to, we don't want to talk about our idea to anyone because we're scared somebody will take it. It's about the how, it's not about the what. So it's about how you apply it and how you implement it. And if you don't want to do that, maybe we can help you get a team member that could actually take this idea and maybe get you royalties fees or something. So that issue of yes, we're sitting on the table, but the implementation is very, very slow. And maybe I'll leave it to the other panels to talk about the other aspects of.
Dr. Abdul, do you want to elaborate?
يعني معالي خلينا نحكي بالعربي. عم بحكي شو الدرايفنج فورس وشو الاشي اللي ممكن نعمله very practical. احنا لسه عم نحكي على المشاكل زي ما هي، لسه بنحكي على البريدج اللي مش عارفين نبنيه. يعني انا من الاكاديميه بقول الطريقه الوحيده اللي احنا نبدا نعلم طلابنا الجيل الجديد to think in innovation and in entrepreneurial way. And this is what Europe and state is beginning to do. The young generation is different from us. احنا الأكاديمية, we have our way of thinking and doing research, even if we claim that we do apply. It's not apply. It's not apply. في الأكاديمية احنا كليتنا بنعمل research is different. هلا البريدج هذا ساعة بنقول الأكاديمية بدهم يجيبوا لنا إياه، ساعة بنقول الاندستريال البزنس، ومرة بنحكي الاندستريال. احنا we have to admit we are not industrial country as a Jordan, right? Other Arabic country, they are leading in this field a little or more than us. هلا احنا still we are figuring out. يعني نجتمع هون بconference، لما بتحكي إشي أنا بحكي إشي، الدكتور بحكي إشي، بيجي حدا من industrial حدا من commercial. It's not sitting on the table. I think it's need like a strategy, like a really governmental plan.
I totally agree, but I hate the word strategy. In Jordan, we are very much good in writing strategy. Let's say we need a governing, schema that have to be an action plan that have to be implemented, right?
يعني أنا I have experience about the fund, the national fund, اللي كان فيه million، وكنا نعطي a lot of fund for. Not a lot, يعني few. Fund لل big project ولا small project, basic science. We thought within 10 years, 20 years we will be somewhere. But still the number is not with us. This foundation of research and company and industrial relationship need not a few years, need a lot of years. Need a trust from the academia, from the company, from the industrial. This has to be a triangle that force us all.
This is the triple helix.
Yeah. You triple, I have triangle, whatever you want. But still, we are not.
Professor Youssef.
Thank you. Actually, I will talk from my experience, but something to answer His Excellency Dr. Mu'tasim in a different point of view. First of all, what you mentioned, Doctor, we have to take it really as action plan, seriously, as a culture. We have to focus, and this is as a culture, to start in this is issue, either innovation, research, commercialization, whatever, even entrepreneurship, you mentioned as well, as a culture to start from preschool, not just to going as for a professor or in the higher education, bachelor, master, or PhD. We have to go back to preschool to start, and this is issue, either innovation as a culture, entrepreneur as a culture, career counseling as a culture, to start from preschool, and this is issue. This is the first thing. Other things also, to be something clear in the all things, in the government with private sectors, some issue to be clearly. Okay. Other thing, we talk like, commercialization. I love to be, and this is to use this issue, but really we are weak in commercialization aspect to start, with all aspect. In our idea to start to be like outreach, to use the professor or academic people to go to industry. What we found, something is amazing, even in the industry, they have something academic we need it. I'm focused to talk about applied science and some cases like some case studies, okay? And academic, the good in the theoretical things, but actual applied implementation, what is available in industry, in the private sectors, even we need it in the university. So now, to make another culture or aspect, we'd like to mention the strategy. It's not just outreach, we need inreach to start with something, not just commercialization, in our academic issue, to use industrial professor, or what we mentioned Arabic like Ustaz Mumaris, to bring them from industry to the universities. So whatever. It's
I think
like
HTU have already started this, and I think it will be cascaded all over.
Before HTU to start, this is the first experience was in JJU, German Jordanian University, and the implementation was not excellent, even the applied science like in architecture, and even business, finance, management, engineering. They have experience, industry, we need it as experience. Other thing is to open the link. Even many of them, they come to know what's going in the universities. Help us in the classes, in outreach, to help us in the courses, certain courses, even to open the channel for employability of our graduate, our student. Actually, many things we can make it benefit from win-win situation.
Thank you. Professor Muhammad, you have to wait because I have, I want to invite you for something. The كريني باسمك. the كريني باسمك انت. سديل صح؟ we have to admit that we have very much brilliant students. I was looking all over today at IEEE guys. You're amazing. والله العظيم. فعن جد الله يعطيكم ألف عافية. طلاب IEEE. جد. Sadil is one of the more, brilliant she's from the University of Jordan. Please.
Hello everyone, Sadil from the University of Jordan. First of all, I really want to thank all the professors today because they did an amazing job, really. I can't even speak words. I just want to say, as a new generation or the people that we are working with, as young adults, we are thinking every day, we want to start a new business, we want to make something, we want to change the world, we want to do something, just give an impact, and we believe that it became a part of our identity and with exposure. I just have the mix here, the research, the fundamental, and how are we going to make it, and the money that we need. But there is still a fear of failure, a fear of not being able to even start. We have these doubts, and I don't think we have the courage, should I say, or some hands to help us get out of our shells. So I think most of my generation is still hiding. We are seeing new opportunities, but we're too afraid to even catch them. So what's your advice about that?
Thank you, Zadil. I think the best one to answer, Luma, you have to.
Okay. Thank you so much. I mean, yes, obviously it's scary. I'm not an entrepreneur, so I don't know how it is when you're on the other side of the table. I'm an investor. But let me tell you this. Today, you guys are lucky. You know, there's the internet that, you know, leveled the playing field. You know, people with extra resources don't have an advantage anymore because you guys have everything, you know, all the information, you can get all the information. But what I can tell you is this: today the ecosystem in Jordan is very much developed to be able to address this issue in particular. Why? Because we have so many, you know, mentors. We have so many supporters that could really, really help you. All you need to do is reach out. I'll give you my email, reach out to me. I could always connect you with somebody that could give you the time and could give you that encouragement to start. And sitting with people that did it and were able to start off a company and now have, you know, some sort of success, really helps, right? So just, you know, associate yourself with like-minded people that could really help you. And I promise that, you know, the ecosystem is there to support you. You don't necessarily need money at this point, but you need all these, you know, mentors around you to help you, and never be scared to ask for help. You know, that's how you can advance in your life. So, I mean, that's my 2 cents.
So I have to finish, but I will end with a case study. Sorry.
To answer Sabil, yeah?
Sadil,
okay. You mentioned, like, I mean, fair, okay, scary. Actually, I would like to add for your students sometime, or for the beginner or to start up, it's a fair. Another thing also really we have to take it like a fair خوف. The other thing it's unfair. Sometime even with those, it's not issue of the money, okay? We don't have problem of the money or a fund. Sometime unfair, this is problem as well, really. And this is issue because it's a mentality of those in charge, and this is issue. It's they use themselves, they are afraid, or they use the very old mentality. They didn't match it with those startup, new generation. They believe by something new they believe still by very old style. This is issue also. It's like, I mean, didn't help to go ahead.
Just one point. I cannot be silenced with this. Before going start up, before you have to do any company, you have to have an idea. You have to have an innovation. Innovation cannot come without research. You have to start with the basic research or applied research. You have to start with the university. Look for a good advisors, for a doctor that he really published, do research, applied, active with the student, involved with him, be like a daughter for him. We are a professor, we need a brilliant student to work with us. Small project, small idea, and then you go on. But don't go for the money before coming to us, okay?
True. Yeah, but the idea is really clear. I would like to thank you, but before we finish this panel, I always have a case that I am very much proud of, and I think he's our host. Professor Muhammad is a scientist who made it and have a company, and I would love if you can give us just 5 minutes. Tell us about your story. No, 2 minutes. But in order, you guys all, you have to know that, okay, you can start with research and then do the patent, and then you will have the money, and it won't be an issue. And this is just a real case of commercialization from Jordan. Professor Muhammad.
Thank you. I don't think money is the problem. I believe there is money, but what we lack is a complete ecosystem. Innovation, we will make it when we have laboratories in the University of Jordan or wherever that is sponsored by Hikma, for example, or sponsored by high-tech company, or sponsored by a water company. You want to make it, you want to make good research, you want to keep these students, these brilliant students at our university, you don't have to make them pay tuition fees for graduate studies. Our problem is the best quality students in Jordan go do their master and PhD degrees abroad because they have scholarships there. You want to keep your brilliant students, you have to give them tuition fee waiver for graduate studies. There is no innovation, no research without graduate students. Even the most brilliant scientist we have here, Professor Silvera, he wouldn't have made the research he made without his team, without his students, without his PhD students, without his postdocs. One hand cannot clap, right? So my point is, what we need to generate in Jordan is a complete ecosystem. The industry should participate. The regulations should be updated. You know, our regulations, our promotion, we need to publish 5 or 6 or 7 or 8 or 9 papers, right. You know, and after we promote it to the full professorship, you know, that's it. Shut down, no? So we will make it in Jordan when we have really the industry sponsoring labs. In every, again, but if you look at broader view, there is now, the money is driving the research. And wherever, for any grant you want, it has to be an applied research. When was the last breakthrough in fundamental science occurred in the world? I don't remember, I don't follow as much as Professor Ike maybe follow, but I believe that we still need to fund basic research to make breakthroughs. In Oasis 500, you sponsored many high-tech company. How about deep tech? Deep tech is the game changer. Yes, but I know it requires more time, more money, and it could be 5-10 years funding, and it might fail. But a game changer in terms of water or in terms of energy can really save a lot of lives. Not only money, lives. When we're talking about water or food security or stuff like this, you're saving really lives. I was from the lucky ones to have some investors who believed in me, but you know, that's 1 in 1,000. It's complete luck. It's complete luck, to be honest with you. But you worked in the Ministry of Higher Education, you Professor Loma, we need to communicate to the universities, to the higher education, that graduate studies in Jordan should be free. Should be free. To keep our most brilliant students here so they can achieve and do the research that we want. We always hear about success stories of Jordanian, Egyptian, many Arab people who made it outside because they got the scholarship outside. That's all. That's my point. Thank you so much.
Thank you, thank you. Again, thank you, Professor Muhammad. Thanks to the Arab Open University for hosting us. Thanks to my panelists, Ms. Luma, Professor Abir, Professor Youssef. Thank you all. Have a great evening, and I think by this we end the conference. Professor Mahmoud, thank you.
Thank you all for being with us through this couple of intensive days. And I thank everyone by his name for his contribution to the success of this forum and this summer school. We met a lot of brilliant students, a lot of inspiring scientists, and a lot of role models. I hope you enjoyed your stay in Jordan, and you will have good memories about being with us. And I would like to apologize for anything, any mistake happened here or there on behalf of the university. Now, I would like to honor our speakers. But beforehand, I would like to make a short announcement. It's 6 o'clock now. We might need 10 to 15 minutes to finish. We'll go to the hotel to rest, and by 7-10 minutes, everyone should be in front of the hotel to take you to the venue of the dinner. There will be no belly dancer, Professor Ike, today, but there will be some singer with oud and stuff, you know. So I would like to invite Professor Mu'tasim Saidan, His Excellency. Professor Muhammad Ma'touq.
الدكتور أشرف بن محمد. سيادة الشريفة لوم الفواز. أيان أرنث. أيان students أيان مستر أحمد الغندور.
Now we're handing the trophies for our future, the summer school participants, and we wish them best and to make better research than what we did and avoid our mistakes.
لا من هنا. يان أرنث سير. أحمد الغندور. حنا أبنوب. سيف. ستيفانيا ريفا. مروة حسين. مهران عدنان. سلمى حناوي. آية علي. شريف ديما. موسكن آرتم. موسكن كاتيا. ارتم وكاتيا في الاثنين. هاي دكتور محمود كاتيا. كمل. أيمن أبو روعة. أيمن شو موجود. فدا عضايلة. فدا. محمد الحراحشة. محمد موجود؟ لا. نور النعيرات. نور. أحمد عوير. دكتور شكله دكتور محمد. دكتور شكله الأردنيين مش موجودين. ستودنتس الأردنيين مش موجودين بعدين. 4 أسماء ذكرناهم ولا واحد؟ وسام القطاوني موجود. وسام. أنس الكلش. أسيل الشطي مش موجودة. حنين الحروب موجودة. لبنى القرالة. تبارك. نور السرايرة. مش موجودين الأسماء. مؤمن الشمالي. سبعة دكتور ثبت فيها 7 الحرب. بنغل الباصات كل الباصات بسيارة يكون جاهزة على أساس الحرب. هلا معصر. هي كاتية.
خليها تيجي.
يلا ست بس خلاص انت روح.
We have to